newest choices can only be seen at wiki.evid.com. Go there now and search for pocket microscopes, or simply click beneath this video. At number 2, the Carson Optical X-Scope is a cool 2-in-1 model that kids are sure to love. It offers the properties of both a telescope and a microscope, so whether children are trying to view objects near or far, it can do the job. It features an integrated fold-out magnifier, an attached compass, and a whistle for signaling friends. And taking the top spot on our list, the Carson Micro Bright Plus 60 times to 120 times is extremely powerful for such a small tool. It features an aspheric internal lens system that brings everything into crystal clear focus, and an integrated LED that you can turn on and off as needed. It feels solidly built and includes a lanyard loop, along with a lifetime warranty. Our newest choices can only be seen at wiki.evid.com. Go there now and search for pocket microscopes, or simply click beneath this video.
Okay, so today we're going to be reviewing the Carson Microflip microscope. It's a 100 to 250 high power microscope is what they have. It's a pocket microscope labeled by them. You can see the magnifications there, 100 to 250x magnification, LED lighting, UV flashlight, smartphone adapter clip. It's supposed to come with all sorts of features. And you look at the image in there, it's a very clear image of frog blood. It may not pick it up on my camera, but on the packaging it has a very clear image, so I'm kind of skeptical about that. This microscope was $15 off of Amazon, so I don't really have high hopes for this. I just want to see if it was worth the money of what I paid for it. So let's go ahead and get into this thing. So I have a foam clip right here. It comes in a little paper, a little plastic bag. That's the foam clip that you clip to your camera, and then that clips to the microscope. So it doesn't work out that well. The spring's really stiff on it, but it probably should be a little bit stiffer. I have a iPhone 11, and I noticed that the images was just coming in and out, and it was really hard to stabilize it. You could just set the microscope down, so it's something that they can improve there. So pulling out the microscope, it's coming out in this little plastic bag, and it comes with this lanyard on it. I'm not really all about the lanyard, so I went ahead and removed it. But you can see there it has UV. It's got a little slide dial for 100x, and that coarse and fine adjustment, it just is labeled focus. So that's kind of what you would use. It goes all the way up to a 250x, and you see the LED button there. And it's made in China. I took that sticker off. I just don't like stickers on products. So I went ahead and removed that. This microscope operates off of a AA battery, and so I had a little AA battery from a little case that I bought specifically for this microscope from Amazon. I'll have that link down in the description. But it's a pretty good case. There are some issues with it, but we'll see that later. So right now I'm just fishing out the little AA battery that I have inside there. I really like that case. It's very small, compact. It's a pretty good case. If you hear some background noise, it's because I'm at my university, and of course there's plenty of things going on. So that's that lanyard. I removed it because I'm going to be carrying it in the case, so there's no reason for me to have that lanyard on there. There's already one in the case, so I just went ahead and removed that lanyard. Okay, so we get a second look at it there. You see the UV button on there, and it can't be turned on while the slide base is down. It has to be flipped out of the way in order for you to be able to use that UV. Then the LED light, it's able to be used with the slide base down and open. And you can see those little, I guess, light refractors that would change the direction of the light to put it underneath the microscope slide. And that focus has a little bit of play in it. And what I noticed in the images that we'll see later, that we'll see later, is that the image has a tendency of moving with that focus knob, which I'm not a fan of. But yeah, fairly clear optics. It doesn't seem like they're using So here we're setting it up to look at a slide. I have a couple of pre-made slides and one prepared slide. Some of them I just made myself. So the clip just snaps in and it's fairly steady. You can still twist it and put the phone on it, but of course I'm recording with the phone, so I can't show you how unsteady it is. I wish I could, but unfortunately I can't. So once again, I'm just reaching into this case to, in that case, it's an $8 case or $11 case. I didn't pay too much for that case, so I don't have too much high hopes for it. But you can see it's a pretty good case. It has a little zipper pouch there and a couple of places I'm assuming to put the cover slips. So I'll put a link down in the description. I can actually fit quite a bit of stuff. I can fit all those slides, those tweezers, and the pipette. Now, I did have to cut that pipette down, but it does fit into there. So right there, we're going to be looking at onion root tip, right? So a lot of cells in there are performing mitosis. And unspecified pollen grains that I just pulled off of some flour a couple of days ago. And then a finch feather that I also prepared. Now, I prepared these slides just by throwing some tape across the top of it because I didn't want to try to find a cover glass and use the correct compound and wait 6 weeks for it to dry and all sorts of issues. So I just went ahead and just threw some tape on top of it, and it works for temporary purposes. So we're going to start off with looking at the feather, and we're going to clip in here and try to get everything focused up. So this is the imaging that we get out of it. It's fairly blue. I don't know why it came out that color. In real life, it's more white than it is blue, but you can see that it focuses on the lowest power. It focuses fairly well. It's hard to keep it in focus. You can see it going in and out of focus. I'm zooming into 250 power. It's hard to keep it in and out of focus because of the plastic base that I will show you at the later in the video. It has a tendency of moving, and it makes it very difficult at that high magnification to be able to focus really well with it. So I'm not sure how you're supposed to combat that, because you can't just pick up the entire microscope and hold it in your hand, because, well, the slide would be falling all over the place, and it just makes it very difficult. So you see on the very bottom of that, you get a black shadow occasionally. That's because the phone is shifting around in the phone mount. Like I said, that phone mount would be probably a little bit stiffer to screen. I did have issues trying to take pictures, but you can see, and you'll see with the very last one too, that this is not at all the type of image that was portrayed in the advertising. The image here, it's not very clear. It's very hard to focus. The slides are very hard to keep steady. They slide all over the place, and it's just very hard to focus, stay in focus, and move the slides we want. Because anytime you just barely touch the microscope, the slide will shift to the left or shift to the right, and make it very, very difficult. So this is the pollen grains off of I believe a dandelion, or a small weed that was just growing outside. The siren was just going to raid its privacy and pull off some of the pollen from the anthers. And so you can see those there, quite pretty. You can see fairly good detail with this microscope at 250x. Not bad, honestly, for $15. Now, is this a Leica microscope? Is this a Zeiss quality? No, absolutely not. You're not going to get that good of quality. But what I bought this for was to be able to go out and see if there were some things interesting enough that I wanted to take home for me, to where I could use it on my Leica microscope and hook it up, and then from there take further imaging and what needs be. So for the purpose of what I bought it for, this does very well. So now we're looking at the onion root tip. Once I can find where in the world it is, it's very difficult to find the specimen. And once you do get the specimen in your field of view, you'll notice the field of view on the low magnification is very, very small. And of course, I have a lot of issues with trying to get this larger slide to balance onto the stage. I guess improvised stage. It's a very small stage. And you've seen I'm having issues with that orange dot. I'm having to hold the phone and the microscope at the same time while trying to manipulate the slide. It is a little bit tricky trying to get everything to work just right. It is possible, but it's not preferred. So here we're zooming in on that onion root tip. So now we're at 250 times magnification, and you can see the cells, you can see the nuclei and the individual cell walls very faintly. Like I said, this is not a Zeiss or an Olympus microscope, but it does well for the cost, which is insanely low of just $15, and the case itself is only $11, I believe. So with the total package, I'm only paying $26 after taxes, maybe just round it to $30, and you can see fairly good detail for that cost of microscope. So yeah, so that's the microscope. There's that base wobble that I was talking about. That's why it's very hard to stay in focus and keep shifting in and out of focus, because that base will wobble, and you can see that whenever it's setting down, the microscope itself will still pivot on that base and just throw you completely in and out of focus. So it makes it very difficult to see the very small details without consistently. But yeah, so that's that's the microscope. The foam clip on the top there, like I said, it could be stronger, but they are using plastic components. So it can't be too strong, or else it'll break the foam clip. So they kind of working with what they have. The ultraviolet light, I'm not sure what that's for. It's not able to be used while the stage is down, so you can't use it for any sort of fluorescent specimens or anything like that. So I'm not quite sure what the ultraviolet light is there for. Maybe if you have some fluorescent microorganisms that you could shine on, but you wouldn't be able to see them through the microscope, because when the slide stage is in the position to do slides, the UV is not able to be used. So overall, not a bad purchase for $15. It's a very good microscope. I forgot to show this in the unboxing at the very beginning of the video. This was the slide and a cover slip that I forgot, that I didn't see in the box once I tilted the box over. These came falling out. So it's a very cheap, very small plastic slide and an opaque cover slip. I'm not sure why they would do that. I didn't know whether or not there was some sort of tape or some sort of protecting material on the cover slip, and it appears to not be anything there. I guess that just is the color of the color slip, which doesn't make much sense at all, because you will see in a second that the slide is very clear. You can see any sort of microorganisms or any sort of plant life perfectly through the slide. And once you put the cover slip on, it's just you'll see right here, it just completely blocks all clarity. So I don't think that you would be able to actually see a microorganism through that cover slip. Nonetheless, it's not bad. You know, if you have your own slides and you have your own cover slips, and you have that case, you have a place where you can put your slides and cover slips. So it wouldn't be that bad of a deal. Or if you just do what I do, I just take some tape and put the organism, whatever organism I'm dealing with, whether it be mainly for dry organisms, not dry organisms, but for like pollen and small specimens, just tape them onto the microscope. Now, for living organisms, obviously that might not work well with tape if you're doing a wet mount, if you want to look at pond water. But nonetheless, it's seems to be a fairly good deal. So this is the instruction booklet. This also came in there. It shows you that we indeed did do the correct steps to try to maximize the image quality. We still did not get that good of image quality though. So that's the review for the microscope and the case itself. I'll just go ahead and throw in the case while we're reviewing it. You can see I'm putting everything up in there. This case was made specifically for this microscope. It's on Amazon. It's about $11. I'll link it in the description, but it holds holds the microscope securely. The only beef I have with it is so hard to pull out that divider. That divider, it's just, you see, I have to use tweezers just to pull it out because it's very, very difficult. So as far as the zippered portion goes, you can see there at the very, very top, might be some issues with quality control. Zipper seems to be separating, already brand new. I just got this thing in today, actually, or maybe yesterday, so. But it's a pretty good sized case, holds my tweezers, the pipette. I completely missed that because I was looking at the camera while I was trying to put the pipette in, so. And the slides, fits plenty of slides in there. And the clip, the foam clip will fit in there too, so. I'm throwing in that little plastic. It's a very, very cheap plastic slide. I'll probably end up just carrying glass slides around with me and either tape or plastic cover slips. But I really don't like that cover slip. I also keep a little razor blade in there just in case I want to try to make cuts of plant stems or plant roots to try to see the internal structures of them. So I also keep a razor blade in there. And I keep a little specimen jar, but that's kept in my backpack. That does not, unfortunately, fit inside there because the specimen jar that I have is too large. I could get a smaller one, and I could probably get it to fit inside, but all in all, a good deal. So, thank you guys, and we'll be with you next time.
Hey, what's up, guys? This is Doug from Carson Optical, and today we're going to check out the MicroFlip. This is a high-powered pocket microscope that can zoom from 100 power to 250 power. It has some high-quality optics, and on the side is a cool base plate that folds out so you can view different slides. Inside the kit, you'll find a blank slide and cover slip to get you started. Included with the MicroFlip is an adapter that attaches to your smartphone and allows you to take photos and videos of your research. When preparing your own slides, it's a good idea to use a cover slip to get better results. Check out how cool something like pond water looks. It's amazing how many things there are that you just can't see with the naked eye. When you're not viewing slides, remember to flip back the base plate. If you enjoy looking at different types of plant life, the MicroFlip can give you close-up details that you didn't even know were there. It's an awesome device for any sort of quick inspection. I also like how versatile the MicroFlip is. With the LED light turned on, you'll be able to get crystal clear results in any lighting condition. When you flip out the base plate, the LED lights will automatically change to a setting that's ideal for viewing different slides. Built into the body is a cool UV light that will allow you to see things like hidden print on currency. The MicroFlip uses one AA battery. I love this thing. Having such high-powered optics and a pocket microscope makes this a lot of fun to use. And the best part is it fits right in your pocket. I'm Doug from Carson, and I'll see you next time. Hey, what's up, guys? This is Doug from Carson Optical. Today I have with me a digital microscope called the eFlex. With this, you can look at microscopic images, or you can take pictures and video. And there's a lot I like about this product, so let's get started. The eFlex works on your desktop computer or laptop. The setup is simple, and you only have to do it once. Just head to carson.com, pull up the eFlex page, and at the bottom you'll see downloadable software for both Mac and PC operating systems. The eFlex has a really impressive magnification range. You can choose between 75 and 300 power. Once you've chosen your positioning, rotate the focus wheel to bring out the sharpest image possible. If you hold an item right up against the lens, you can get a view of up to 300 power. With something this powerful, you can see details on any type of plant life. At this distance, you can also view your object at 75 power. Just rotate the focus wheel until your object is sharp. The eFlex plugs right into your USB port. When you open the software, the eFlex will automatically be activated. If not, just click the Settings tab, go to Devices, and select the latest USB driver. There's built-in LED lights that can be adjusted to your preference or even turned off. Having the ability to control your lighting is a huge advantage because that means you can use the eFlex in any lighting condition. you plan on taking this item outside, sometimes there's no need for additional lighting, so that's awesome because you can actually turn them off. The suction cup at the bottom can clamp down onto many smooth surfaces, but works really well with the included base. With this, you instantly have yourself a complete observing and measuring station. Sometimes you might want to go handheld, so we've made this microscope detachable. You can get some really great close-ups of jewelry or anything that has small details. While observing a specimen, you can document your research at any time. Just click the camcorder button to record video and the camera button to snap a pic. You can even press the top of the E-Flex for an instant photo. So with a large magnification range and adjustable hands-free convenience, E-Flex has got it all. And most importantly, this is the most user-friendly digital microscope I've come across. I'm Doug from Carson, and I'll see you next time.
Specifically from a company called Dynolight. I met these guys at the RFIC IMS trade show, and I was immediately impressed by the variety and the quality of their products. They had some really neat demos set up at their booth. And I've been in the market for a USB digital microscope myself, and they were kind enough to send me a whole bunch of different models so I can demo them here for you guys, so you guys can also see what these things can do. They also sent me two different kind of stands which I've assembled behind me, and I'll talk about those too. These digital microscopes have some unique features that makes them very useful for high magnification situations. It doesn't have to be electronic components, but for us, for electronic components, and I'll show you what these unique features are. You also have a really long working distance, allowing the microscope to be quite far away from the subject that you're trying to look at, which is all, of course, very handy when you're working under those situations, so the microscope is not too close to the subject you're looking at. So I have a whole bunch of electronic circuits and really interesting tiny components that I want to look at under the microscope, and in the process of that, we will learn about the features of these, and we will evaluate the quality as well as the software and the hardware to make sure everything is good, and then you can decide whether this will suit your application or not. Well, I've been quite happy with them, so let me show you what's going on. So this is one of the two microscope stands. This is model MS36B, which you can find on their website. And the first thing I noticed after opening the box before assembling it was that every single aluminum piece that's in here is really well precision machined, and this is even more so for the other model, and I'll show you, which means that things don't wobble and things fit really snugly and well together, and there's no freedom when you move them around. They don't shake around, which can be very annoying otherwise. So I'm impressed with the quality of these as well as the other stand. This thing has quite a few degrees of freedom that allows you to move the microscope and place it in a whole bunch of different positions. Of course, the front, which is the unit, this unit is made of plastic. This is the part that holds the microscope itself. So there's nothing to it really, it's just a screw, and then allows you to attach it to this rod right here. So then this itself gives you a whole bunch of degrees of freedom. And then there is this large screw here, which by turning you will loosen and free this rod from moving back and forth or rotating completely 360 degrees. So you can imagine a scenario where you have something that's vertically this way and you want to look at it in this direction, you can easily get that orientation of the microscope. And if you pull it long enough, then you can have a complete degree of freedom. And you can see a little tiny attention to detail. Right, there is a little aluminum piece that gets screwed to the end of this rod, which prevents you from pulling it out accidentally. So there is quite a bit of attention to detail, which I really like. And then whenever you tighten it, it will stand quite firmly in place. And on this side, you have the main screw, which allows you to lower and raise the entire unit up and down. And once you're satisfied with some position that you want it to be in, then you have the focusing knob, which then, of course, raises and lowers the microscope by a little bit at a time. This has a nice firm feel to it. There is no give. It really stays where it's supposed to stay. And finally, at the bottom, there's a ring. And this ring allows you to set a minimum distance. This can be very useful. Usually, microscopes have this. It's because when you're paying attention to the image, when you're not looking at the microscope, you can actually lower this too much. For example,
QTT, Qtatio, reporting revenue down 14.6%.
both side by side. So let's look at the other one.
to 965.5 million RMB, sees Q4 revenue of 850 million to 900 million RMB. That's Quebec Tango Tango QTT.
Well made as the original one that I showed you, and in fact it has some really nice features that I like. First of all, it came, of course, in multiple pieces which you assemble yourself with 4 Allen keys at the bottom.
WMT Walmart Verifique launching on Walmart Marketplace.
It's a really solid unit. I mean, this piece is precision machined and attaches to the base quite well. It has the same working
Cannabis detection test.
36B model that I just showed you, and then it has a couple of pieces that separate. So in the front is the microscope holder.
Whiskey Michael Tango.
It's of a higher quality. Again, if you look, every little screw has the metal threading inserted in it, including even the one that is used to tighten the microscope grip. So these things are going to last for a very long time. And it has 2 inserts here, so you can place a microscope at different distances in there. And then you're similar to the other model. Once you place it in, you can rotate it around. And even, I don't know if you can tell on the camera, but let me remove this. Even the insert metal here is serrated so that the screw really catches it. So there's no way for this to slip over the surface. So there's a lot of attention to detail. You can see the precision machining that I was talking about. So even when you place this here, it is flush with this piece completely, not on a curved angle. It also has this groove here, and this groove locks with the screw that is in this piece here, allowing it to be set to a vertical position very easily. But then if you don't want it in a vertical position, then you just loosen the screw a little bit more, and then it becomes free rotating. So it has again a lot of attention to detail, and I like that. And it also comes with an extender arm as well, which you can use to further increase, for example, let me stick it in here, to further increase the range of motion that you can have with this. So now you really have a whole bunch of different angles that this thing can take. I mean, you can rotate in almost every direction. So usually for electronics work, this piece isn't entirely necessary because you'll be mostly looking vertically down. But if you have a vertical board again or some weird angle that you want to look at, then you can have this as an attachment. So this is a very useful extra piece that comes with this. And as far as going up and down, by rotating this screw, you can raise and lower, like so. You can raise and lower the main microscope. And let me put this back here so you can have an idea of what I'm talking about. And it has this other feature that I really like, because most of the time you'll be changing magnification and you want to move up and down quite a long distance. This is usually intended for mainly getting the focus. So it has a little button here on the side, and by pressing this button, you can easily raise and lower this very quickly, and then it locks in place. And I can tell you, this thing feels absolutely smooth. There is no give to it. Even when I press this button, it really is. I'm pressing quite hard and trying to rotate it, and nothing. It really stands in place. Very high quality. It also, of course, has the protection like the other one. You can raise and lower this as well, which would set the lowest position the microscope can ever take. So it looks really nice. So I'm going to set both of these units next to each other, and then I'm going to connect 2 different models microscopes and to the computer, and we can take a look. But first, let me show you the microscopes close by in close inspection, so you can see what the actual microscopes themselves look like. And there's also a bunch of other Velcro accessories that allow you to tie the microscope cable to it and so on. So we'll get to see that. So let's look at the microscopes themselves. So here I have all 3 models lined up. We have the AM4113 ZTL, the AM4515 ZTL, and the AM4815 ZTL. Yes, the model numbers are really long, but on the website you can sort and select by feature, so you don't have to remember the model numbers. But the difference between these models are quite straightforward. This one, they're all part of the H series, so they all have the enhanced imaging sensor, of course, built into them. This one has a basic polarizer, so you can adjust the polarization of the light that comes from the microscope, which can reduce glare and reflections, and we'll see that. Moving up from that to the 4515, this one has the automatic magnification reading capability added to it as well, and it comes with more accessories. And then the 4815 ZTL has the extended depth of field as well as the extended dynamic range imaging capability also that the software can take advantage of. So this is kind of the order of the models as they get more and more advanced. They all offer the long working distance, so they all have that extended working distance, which is very useful. I'm not going to go through unboxing them or anything like that, but just to take a quick look, let's look at a basic model here. The microscope is, of course, we'll take a closer look at that separately. And it comes with a whole bunch of little accessories, you know, all nicely, neatly packaged in there. And it also comes with, for example, the Dynolight calibration film, which allows you to calibrate the distances because the magnification is adjusted manually. You can use these fine lines. It's essentially a ruler that allows you to calibrate your image to know what your exact magnification is, and therefore then you can use the software to do precise measurements of distances and radiuses and so on. So it's all nicely packed together. You can take a look at their website for the accessories. I don't think that's too interesting for me to show you here in detail, but we'll take a look at it. So this is the basic model. You can see that the microscope body is made of plastic. They also have metal body microscopes as well. You can take a look at that. And it has a couple of different neat features. So here's the polarizer. So by rotating this front cap here, you adjust the polarization. The magnification is adjusted by this rotation here, and you can see there's numbers written there right on the microscope itself. So, you know, it maxes out here at about 100 or so, and then it has a minimum of, you know, it goes below 20. So it actually rotates almost completely to the other side, which is essentially the normal working distance. So about 20 to about 95 or so is the magnification of this particular model. It has a magnification lock button, so you can lock it in place so that this will not turn anymore. But I have to say, this feels really, really nice. There's no give, there's no loose section. The dead zone in here is very, very smooth. You won't accidentally rotate it by touching it. Very nice, really good feel to it. Also, the same with this one as well. So I really like the quality of these things, and in a nice and compact size. And you'll see the lights when we turn it on. You can see again. The thing that I want you to note is that the magnification is all optical. So there is no the software supports digital zoom, of course, but then all the magnification is done optically. So the image quality really remains quite well. You're not sacrificing resolution at higher magnification. So this would be the AM4113, and then we can look at, let's say the higher model. I can have open. Here you go. This is the highest model that I have here with me. This is the AM4815ZTL. So this has all the bells and whistles. So you can see it looks slightly different. Very nice construction, nice color too. But the polarizer here, this one is actually marked. By rotating this, you can adjust the polarization. You can see it rotating on the inside. Everything else feels the same. Nice solid feel to it. The magnification also nice and solid. Again, this one goes from about 10 all the way up to, you can see, up just under 150 magnification, which is fine for electronics work. Really, at 150 magnification, you're looking at dies and, you know, wires on ASIC, so you don't need something that high for soldering, for example. But for lower magnification, it's perfect. The same thing, it has a lock button here, and both of them have this soft switch here. Is a capacitive touch, and then by touching it, you can tell the software to do different things. You can tell it to take a picture, you can tell it to turn the light on and off, or a couple of different functions. You can completely disable it. So if it's standing somewhere and you want to take a quick picture, you just tap this and it will take a picture, and you go somewhere else and you tap it, you take another picture. You don't need to go back and forth between the computer. So all nice and everything. Again, these are plastic. They do also have metal canned bodies, versions of different, slightly different versions of these that have a metal body. That's also nice if you need something that's a little bit more sturdy. Otherwise, all nice and good. Again, this one also optical zoom, of course, built in. So let's set two of these guys side by side and look at some interesting stuff under the microscope. So here I have both of the microscopes set up. This is the 4513 model, the Dynolight Premier, and this is the 4815ZT, the Dynolight Edge series. Both of them have long working distances. I have set them to two different magnifications to look at two typical things that you might be interested in. On the left, I'm looking at an analog devices board with an ultra high speed 2.5 gigabits sample per second ADC on it. It has a lot of really small components, 0201 footprint surface mount components on it, which would be quite difficult to see with the naked eye. For example, the components in this region that I'm actually focusing on, I can't really see them. Let me zoom in here a little bit with the camera so you can appreciate the board a little bit better. So we'll be looking at these really, really small components that you can see there. And on this side, I have a PIC microcontroller, a UV, let's see if I can get this to focus, a UV raisable microcontroller here that I've put on the microscope as well. So it has an opening window for UV raising, of course, which we can see the die. So we can look at it pretty close and see the die of the microcontroller. That's a PIC 16C774. It's a reasonably older model. So I have connected a board to the computer, and I'm running the dyno so. Let me get here two images side by side. Here you can see the nice thing, one of the nice features of the Dino Capture software is that if you have multiple microscopes, you can set them all up side by side, and these images are live. You know, I'm shaking my finger in front of me, you can see they're live. So let's take a look. So on the left side here, this is the ADC board that I showed you, and you can see there's quite a bit of glare on it, and that's normal because the surface of the sill screen and the solder mask are quite shiny, so the LED light reflects back and you get a whole bunch of glare, so you can barely see that there is, you know, text written in here and so on. So I can adjust the polarization by adjusting the polarization rotator here by rotating this, and we can take a look and see what happens to the image and how much more detail we can get out of this. So if I rotate the polarization, you can see there's the sill screen writings here which are barely readable, and I rotate that and you can see a whole bunch of detail coming into view. So by rotating this, you can get the different kind of detail come and go into view depending on what you're interested in. So now we can see better, for example, the traces. You can see the very nice dark contrast between the different traces. You can see all the component numbers and all the O201 resistors and capacitors that are connected to it. This is an unpopulated IC. It's supposed to be a synthesizer that's not populated on this board. On the right side, I'm looking at the microcontroller with the Dynolite H series. You can see that on this there are some extra icons here visible that allows you to do the extended dynamic range and the extended depth of field, which you cannot do with the Dynolite Premier, but the polarization controller you can. And there's a whole bunch of other features here you can do. For example, turn the light on and off. If you have external light, if you have light coming in an angle, then it's very useful to be able to turn this light off completely, because you can get some other colors and other wavelengths incidents onto the board, which can be very useful. There's auto exposure. You can turn that on and off. You can change the different levels on the exposure again, which can be very useful. Again, you can see you can bring a whole bunch of detail by changing the exposure yourself manually. All of these are very beneficial when you're trying to manipulate the image and get the best image quality. And you can also change down here. You can see the brightness, the contrast, the hue, everything, every possible thing you want to change about the image you can do, and you can get the optimum image coming from this way. And I'm not going to play with it too much. You're most likely familiar with the capabilities of these things, and this software provides all of those. Now here we can see the die really nicely. It's the die of the microcontroller. You can see all the wire bonds all around it. Very nice image, and these glowing areas that you see are the reflection of the LEDs from the opening window, the glass window of the die. So if I were to change the polarization here, you can see a whole bunch of new details will come into view. Remember that having some reflections off a particular surface can actually be useful to bring out some detail of the die, like we have here. But I can also change the polarization, and if you look at the camera will readjust. Now you can see more of the different type of detail. You can see the bottom of the package. You can see the epoxy that's used to hold the die. The wire bonds are even more clear. And you can see this is the pad on the inside of the package where the wire bonds jump onto. So very nice, quite good detail. And you can maximize this, by the way. So you can maximize this image like so. There you go. Now you have a gigantic view of the die, and it's really clear. You can see this is most likely some memory over here. You can see the drivers next to each of the pins here, and again, a whole bunch of different synthesized logic. And we can zoom in further, of course. So I can go ahead and zoom in further, and then bring the microscope down back into focus. So I'm now lowering the microscope back down by rotating the top now. I should be lowering it really with a quick release, but I'm sitting at output angle. There we go, almost into view. And here it is. And I can see quite a bit more detail on the die itself. You can adjust the polarization. You can get even more. See, by even on looking at a die like this, by adjusting the polarization, you can get even more detail. So it can be really quite beneficial, and the adjustment and the focus is really precise. I really like that stand, and it gives you this kind of detail. And you can capture an image, of course. You can, like I said, I have mine set up to turn the LED light on off the capacitive touch button that I told you, but you can of course just do whatever you want. You can tell it to video record. You can record a video. You can take a time-lapse video. You can take an extended depth of field image and so on. You can record anything. You can save anything. You can cover everything. It's very easy, pretty straightforward. So let's
APOG, Apogee Enterprises, reported 63 cents Alpha Papa Oscar Golf.
You can see the image quality is really nice. This is really zoomed in, I think, almost at the maximum. I should be able to zoom in even more.
The estimate was 53 cents.
This is the maximum amount of zoom I can get. And the image quality, even at the
Revenue of $334 million is a beat for Alpha Papa Oscar Golf APOG.
see here some very periodic, most likely some memory here or some memory here from. I have to look at the exact architecture of it. But you can see, if I come to this corner, you can see how the wire bonds are done.
Yandex announcing completion of its taxi group assets.
Physical pressure that attaches them to these pads. These pads look like to be aluminum to me, but you can see again the drivers here. There's some writings. I wonder there should be at some point in here somewhere microchips numbers. I don't know where they usually put their numbers on these guys, but anyhow, you can see a fairly good view. Now the frame rate is 30 frames per second. So 30 frames per second isn't great. I mean, 60 frames per second would be much better if you're doing live work. You can see if I were to move this back and forth, that you have that kind of jello-y, jiggly feel to it, and that's because, of course, the frame rate is 30
That's
frames per
Yankee
second.
November Delta X-Ray YNDX.
Other microscopes that offer higher frame rate, or even microscopes that have direct connection to the PC. So instead of going through USB, you can actually directly go through DVR and connect it to a monitor directly. That way, the latency is even smaller, and they have 60 frames per second instruments as well. But these are more in the price range that might be of interest to professionals and hobbyists and so on. But also, I wanted something with a USB that I can easily capture an image on the computer. But again, it looks very nice. So let's look at some more interesting things. So I have two other things under the microscope now. On the right side, I have a horn antenna. I think I showed you this in one of the earlier videos. This horn antenna is a 325 gigahertz horn antenna. So it has a very, very small opening. I can't remember what what number this is, but it's intended to be at a very high frequency. I want to take a look at this on the microscope to show you the extended depth of field capability of the microscope. So that's the first thing. On the left side, I have an RF probe. This is a composite probe, and take a closer look at it. And this composite probe has a whole bunch of DC needles, and then it also has one RF input that I want to take a look at. This is supposed to be a 150 micron pitch probe, so the needles and the tip should be about 150 microns apart. And I wanted to verify that just to make sure that it is indeed the case. And I have what I've also done is that I have replaced the microscope, the 4113 model with this one, the 4515 ZTL, which includes the automatic magnification reading feature, which the 4815 doesn't have. And that's something that I don't really fully understand why, because from the perspective of these two, they look identical to me. And I wonder if that limitation that this one doesn't have automatic magnification reading is an artificial limitation, or is really something to do with the hardware. It'd be something interesting to ask them. I'm curious because it's a little bit annoying that this one doesn't have AMR also included, because it's the higher model, so I would expect it to have all the features of this one, plus the extended depth of field and the extended dynamic range. But anyhow, so let's take a look and see what we see on the screen. Again, I've done the same thing, and I have put the images side by side, and as you can see, raise this a bit, the image quality again, once again, is quite good. So we can talk about two different things here. So on the left is the probe, and you can see how nicely all the needles are visible. This piece that you see here, this is a yellow, red tape that you see here is copper, connecting all the grounds of the capacitors, which are here you have the extended dynamic range and extended depth of field, but you don't have automatic magnification reading up here. But if you look here, it tells me that the magnification is 123.6, so it reads it directly from the microscope, most likely from a potentiometer that's connected to the magnification reading control. But I don't understand why it doesn't why this one doesn't have that. But anyhow, since it has them, but don't worry about the fact that this doesn't have this, because you can use that ruler I showed you and calibrate the distances here. And once you calibrate the distances, then you can easily get magnification value from here too. But anyhow, I haven't done that. So here we can see, so this, I remember I said that these are supposed to be 150 microns apart, and this software has a whole bunch of tools that you can use. You can draw all kind of shapes on it, and these shapes, and there's even more here. And then it will tell you distances, and there's a whole bunch of grids and circles and anything pretty much you can imagine. I'm just going to use the most basic thing, which is just to draw two lines. So I'm going to draw a line starting from here, and let me go back in here. I don't know if you can see my mouse or not, but you will see it once I click. So I want to measure the distance between that pin and that pin. So I connect this person, and you see now I have a free-forming number, and it's giving me the length. So if I go further and further, the length of this line goes up, and I go right in the center of this guy right there and clicked again. Oh, actually, there you go. Look at that. I wasn't even looking at the number. So 0.15 millimeter, which is 150 micron. So the distance between these two pins is exactly 150 micron, as it is supposed to be, as is the design specification of this probe. So you can do precise measurements like that, and you can also change the focus plane, of course. And if I go up, you can see the cable becomes into focus. So now this cable is the ribbon that I was telling you, the copper ribbon is now in focus. Now if I go further up, of course everything is out of focus. So I can go through different focusing levels to get that. So, and I'll show you why. Now this is annoying. Why is it annoying? Is because, well, I cannot have this in focus at the same time as the needles. And the reason for that is, of course, because depth of field is a function of distance to the subject. That's an optical limitation. It has nothing to do with these microscopes. So on the right side, the 4815 model has this ability that allows you to capture multiple images, and the software will automatically reassemble them together and give you an image that has a much higher extended dynamic range, extended depth of field. So here, for example, you can see that I am focused on the outer circle of the horn antenna. So this plane of focus is now in this distance, but the background, the screw and the waveguide holes and so on, they're all completely out of focus. If I want to get that in focus, then I just change the focus plane by moving down like so, and eventually I will get the focus on that plane, and keep going there pretty much. You can see that now I have this part in focus. Now this part is out of focus. So if I go back all the way to the highest plane of focus that I want to achieve, which was here, like so, there's a button here called extended depth of field, and if I just hover on that, you can see how it goes up and down. It changes the focus field for me automatically. So there's some optical components in it that move and change the depth of field for me. So I can also change how many images I wanted to take. Like I even can go even further down. So if I would just simply click on this, like so, it will take a whole bunch of pictures and it will start processing them. You can see that it's now, this symbol here means it's processing. And once the processing is complete, the image will appear here. And I will open it and I'll put it side by side with this one so you can see the difference. So let me move this out of the way. And open that. There we go. I'm going to put it next to this one. Now we can take a look. Look at this. You can see the difference quite clearly. Here, everything here is completely out of focus, but look how sharp this image is. Not only is this screw completely in focus, but also the tip of the waveguide is also in focus, whereas here the background is completely out of focus. So now we get an extended depth of field image out of this one. I can also take an extended dynamic range, although in this case it doesn't really matter too much because everything is pretty much within the dynamic range. But if I click on that, it will take multiple images at different exposure levels and combine them to get an extended dynamic range image. Although here again, this one doesn't really matter because everything is already in focus. I have to show you a better example of that. Well, anyhow, this one doesn't really do it justice, but let me erase this one so we don't need this anymore. But extended depth of field. Now I'm going to put the probe on, I'm going to take this probe and put it under this microscope so you can we can see a really extreme case of the extended depth of field. So here I've placed the probe under the microscope that has the extended depth of field, the 4815, and I want to capture the details at the top of the connector while simultaneously capturing the details of the wire that's underneath it. So let me show you like so. So there is quite a bit of distance between the surface of this connector and the cables that are underneath it. So I can do that. I have actually brought up the image. There we go. Completely on the screen. So I've maximized it. So you can see that the microscope is looking. Here's the connector that I was showing you, and here are the cables that are underneath it. So it's a very nice big image, and they're at a totally different height. So this is much higher than this. That's why this is out of focus and that's in focus. And I can actually manually change the focus from the top to all the way to here. So now you can see this a little bit slowly. This one will come into focus like so. So what I will do is that I will go to the top of the image and get the top of this surface of the screw in focus like so. Perfect. And now I can go ahead and click on the extended depth of field button, and I've set it to manual. And this manual function is very useful because you click on it, now it gives me this little window, and this little window I can tell it exactly which images to capture at what depth of field, what plane of focus, and then it will combine them. So I will say, okay, well, capture this one. I click on capture, so there's one capture in the queue, and then I go forward one more, and I say capture this one too, and I just increase it until I'm satisfied. We can see that the focus plane is changing, and I continue capturing more and more images. There we go. Maybe one more, and one last one. There. So I've captured a whole bunch of images now, and I can say start processing. I click that, and it will continue to process for me, and then it will be, once it's done, we can do a quick comparison between this image and the one that's live. This is a live image. You can see I can put my hand in front of it. So this is a live image, and I'm going to do a comparison. So here you go. So processing is completed. I will open and maximize. There. This is the image after extended depth of field processing, and this is the live. You can see I can go back and forth. The difference is quite dramatic, and this is not even the entire focus range it has. I've only used a small portion of the depth of field that it has. It can go even much further, capturing details at a much larger range of distances, which can be extremely helpful, especially if you're looking at situations where you're doing wire bonding, or you're creating something that you need to really make sure that with a single image that everything is in focus. This will definitely do it for you. So the last thing I want to look at is this Quinstar PA. This is a PA module that has K connectors at the input and the output. I actually couldn't find a data sheet for it right off the hand, but this is a broken unit. I wanted to show you what's inside it. The top cover comes off. These things are all, by the way, manually hand assembled. So you'll appreciate how much work goes into it once I get this thing open. And you gotta always be very careful opening this, even though this is a broken unit. So the cap just comes off, and inside you can immediately see there's some circuitry and so on in there. But the top of it is covered with this material. Now what that is that these are RF absorbers, and it's very common in a microwave module like this to have RF absorbers everywhere. And the reason for that is it's not a coincidence that this looks reflective to our eyes, because it's reflective to EM frequencies that our eyes can see, but it's also reflective to the EM frequencies that's within the operation of this amplifier, just like the 40 others. If you don't put EM absorbers in the strategic places like they've done here, then you can actually create cavities and resonances and reflections within the package that can cause all kind of problems. Not only can it result in the response of the amplifier to being different, but it can actually cause oscillations, because signals can jump from the input to the output back to the input of the amplifier. Because if this is a PA putting out a whole bunch of power at the output, it can actually reflect off the surface of the lid, for example, and then bounce back to the input and cause the feedback that causes instability.
TRMB, French Railway Authority, SC and SNCF, Rousseau bases Enterprise Common Data Environment on Trimble Collaboration Software, Tango Romeo Michael Bravo, TRMB, SJ, CyanJoy, and Hero Gallery jointly announced NFT Blind Box project with artist Julie Harvey. That's Sandy Julie, that's J. ARES, Aries Management, acquires 11.9 million square feet of industrial assets. That's Alfa Romeo Echo Sandy. ARES. APOG. Disregard that was out already.
I'm going to go through it step by step, and then you can see the clarity and also the quality of the picture. So here we go. So this is what we're looking at here is the input of the PA. So you can reason this out. Again, I don't know the data sheet. I haven't seen the data sheet for this. I couldn't find it. I did a quick search. So I'm just going to tell you based on my observation what this is doing.
OTIS, Otis reaches agreement for Eurosins to tender its full stake in cash tender offer for Zardoya Otis shares. Oscar Tango India Sandy.
Process because otherwise the PA is going to be overwhelmed by frequencies that are out of band. This is most likely some narrow band filter. It could be maybe from 20 to 40 or so. And you can tell right away that this is a microwave filter, of course, and these lines, the distance between these lines and the shape of these lines will determine the frequency response of this filter. It looks really weird if you haven't done microwave engineering, but this is a fairly typical type of filter. Underneath this is the ground plane. So these are all combinations of microstrip and transmission lines and so on that make up the filter characteristic. This material, it looks like to be ceramic, so it's a very high quality, low loss dielectric material that you can make a nice filter out of. So you can also see that there is no DC connection. So this filter not only gives you the filtering, it also gives you AC coupling, so there's no current, so you don't need to isolate the input with a capacitor anymore. So going forward, and also by the way here, let me show you what happens if I change the polarization. If I change the polarization from, I can get quite a bit of different amounts of detail. So this is the real colors. If I change the polarization to the other extreme, you can see all the other details of the bottom of the package become visible, and also you can see the reflection of the surface of the shiny transmission lines and so on are more obvious. So there we go. So let's leave it like this, and let's slowly move forward. So coming after that, after the filter, we have the first stage of the PA. Now let's take a look at this. So this is the PA driver really, because they cannot have. You want to have a certain amount of gain in the PA, so you have to make sure that you're able to give the last stage of the PA, which is the main stage that provides the output power, with sufficient input signal. And this is what most likely this ASIC is. This ASIC is of course in the signal path. You can see the input of the filter has got 3 wire bonds that go to the input of the PA, the pre-PA driver, and then from the output it gets coupled out. These lines provide DC signal. These are ribbons. They're using ribbon bonds here for, in this case, they're using ribbon bonds as opposed to wire bonds because they want to increase the current handling capability. So this is a line that provides a lot of current from the DC, and you can see that it's coming around and getting distributed. These are resistors provided for biasing, and you can tap. This is a clever way of doing this type of layout. You can see the gold bonds in between these black lines. Those are resistors, so you can tap off from different locations. Let's say I want, I don't know, 50 ohms, then let's say each of these is 5 ohms. I take 10 of them, and if I want something else, let's say I take a different amount. So you can see they've tapped off here, so they're using this portion of it. There's actually 2 different resistors, I believe. So here you can see the snake pattern here and ends here, and there's another one that ends here, and there's the ground connection at the bottom. So there's a bunch of different things you can do with this type of material. Everything is on a ceramic board. All of this is manually hand assembled. What a nightmare. That's why these are sold by units one at a time. They don't make many of these. You have to ask for them. This is most likely a gallium arsenide substrate. I believe this. I think it is. I'm guessing it could be some other technology. It's most likely either gas or indium phosphide. But I believe it's gas. So this is the first PA driver. We can continue going forward. This is just, I believe, some interconnect. I don't think this really does anything else other than just connecting from the input to the output. And there is some more. These are spacers. Again, they're just doing this because they have no choice. The package size is limited. And then they go into another transistor here. So this is the first PA. The main big PA is transistor. It looks like a gas transistor again. We go from the input to the output, and it has the biasing and various things connected to it. And here's the main PA. And this main PA uses power combining. So here is a power splitter and a power combiner. So here it splits the power into 2. So main detail. And there you go. Now you can see this one. The reason this is glowing and this one is not is because this has a slightly different angle. It's probably not completely flat, and therefore it's not reflecting the light in the same way as this one is, but you can see the details of it much better like this. So the signal comes in, gets split with this microwave splitter, goes through the two final transistors of the PA, and then it combines them together once again and goes to the output like so and connects to the output. So the output of this looks to me, if I'm not mistaken, to be DC coupled, but again, I don't have the data sheet, but I don't see any AC coupling in this path anyway. But you can see so much beautiful detail from the microscope here. And let's look at some of the biasing circuitry. Here we go. This is this section of the IC has some biasing circuitry in it. It could be most likely a voltage regulator or some other. These are they look like to be a whole bunch of transistors all aligned here. Probably some regulation going on or some resistors here. Not sure what this is. It could be a capacitor or a resistor. It's also I cannot tell what that is. Actually, could be even a diode. So there you go. You can see a whole bunch of again details. These are of course capacitors, and here's another capacitor right there. There's a whole bunch of this probably is most likely a diode, protection diode right there. And here's some more resistors. You can see some more ribbon wires at the top. This is again the PA at the input. So I hope you enjoyed this reasonably quick look at the Dynolite microscopes. I have the catalog here, and of course you can find the catalog on their website. Go take a look. They offer a really wide range of products, all kind of different types of inputs and outputs, including, like I was saying, HDMI and VGA and DisplayPort and so on. So you can get, depending on what your application is, really quite a wide range of stuff. And they also have microscopes that put out a particular wavelength for photoluminescence experiments and all. And sometimes you want to excite a particular material which only gets excited with a specific wavelength. You can use filters and LEDs that have a calibrated wavelength output. And also again information about how their calibration mechanism works. You can easily calibrate your microscopes even if it doesn't have the amplitude reading out directly. You can calibrate it out. And there's a whole bunch of accessories and different magnifications, uses for not just limited to electronics, of course, using for biology and other kind of fields and so on. So go ahead and take a look at their website. They have a whole bunch of demos also themselves, and I hope you really enjoyed it. And as always, if you happen to purchase something because you saw the demo here on my website, just let them know where you saw the demo, because it always helps me have a good relationship with the manufacturers. And again, I usually tell you exactly what I think about the product. I like these. My only complaint is the low frame rate, which makes it a little bit difficult to work live under the microscope. But other than that, everything looks really good, and hopefully they can come up with more products in the future that would allow you to have a higher frame rate at affordable prices. So go ahead and take a look and ask them for a code or prices. These units that I have showed you, they would range with a standard about $1,000 or so. They're a little bit pricey, but again, they do a pretty good job. So take a look. They have a wide range of prices, and let me know in the comments what you think. And well, until next time. interesting test that we can do on the scope to push it to its limits and to show you what an incredible instrument it actually is. And then finally, at the end of the video, I also have a complete factory tour, because these scopes are built and assembled here in the United States. So I can just drive there, and they were kind enough to invite me over to do this whole episode for you guys. So it's pretty awesome. It's the world's first look at really looking at the internals of the 100 GHz oscilloscope. So let's start with Pete, who's going to explain to us exactly how it works, and then we're going to go through the experiments and so on. And don't forget to watch the end of the video, which is going to be the factory tour. So let's go.
Hi, my name is Pete Popolakis at Teledyne LaCroix, and I'm going to briefly speak about how a 100 gigahertz oscilloscope is designed. So to start with, I'm going to describe first how a 36 gigahertz scope channel works. So basically, in an oscilloscope, we have a signal coming in, we have a front-end amplifier, these generally in an oscilloscope we design a front-end amplifier and signal chips. We call this FSH. Takes the data, it actually has its package, it has a coaxial connector, so there's coax coming in and then it's on the package to maintain 36 gigahertz band, and coming out of the MSH multiple attracting outputs. These all go to an ADC. The ADC in our current parts is a 40 millisecond per second ADC.
The design are the triangle node amplifiers and ADCs different individual ICs connected on the PCB, or are they single monolithic ASIC part?
So this would be a single part. The ADC is a single part. And two of those single parts. The MAMs would be many such parts. All of these parts in an oscilloscope, and I'm leaving out one piece, which is the MTT. The MTT controls the time base, basically controls the acquisition system, and also supplies the trigger. So there's something that comes out of here supplies the trigger. All of these chips are not publicly available. This particular part is EHP, process. These parts are 7HP, these are a combination of some process,
STC, Stewart acquires Greater Illinois title. That's Sandy Tango Charlie, STC. OMI, Owens and Minor, reporting achievements of first 6 months. Looks ahead to 2022. That's Oscar Michael India, OMI.
most of those applications are narrowband applications. Might be AC coupled applications. In an oscilloscope channel, we have to maintain DC. It's very broadband, so it goes DC all the way up to the bandwidth limit. And the signal fidelity requirements of an oscilloscope are probably most other types of electronics, since it's supposed to be a TV set. So now I'll erase this and show how that channel is implemented in a 100 gigahertz design. So basically what we have is take a 36 gigahertz oscilloscope. I'm going to draw what I drew before for a square channel. It's just a square. This square represents what I just did.
So that square represents a 33 gigahertz bandwidth, 80 gigasample per second ADC. What we do in 100 gigahertz design, what we've done in many of our designs since about 2005, is we put a microwave front end for this. And in the 100 gigahertz oscilloscope, this microwave front end, the first thing it would consist of is a multiplexer. A multiplexer is a device that can pass multiple frequency bands out of its outputs. So in this particular case, this multiplexer has many rough numbers here from DC to 30. The other bands, go through a down converting stage, which I'll just draw stylistically as some kind of a mixer here. And those come out here. And so this band, which is taking the 33 to 66 gigahertz, would have a local oscillator set just above the band edge, like let's say 67 gigahertz. These aren't the exact numbers. And so coming out of this IF port of this down converter would be 1 to, let's say, 34 gigahertz. It would actually be flipped over in frequency content. So you would take the band that would be, let's say, 66 and place a local oscillator up here, and what you would see is this. So this band now that's been down converted is within the bandwidth capabilities of this channel. So that gets digitized. And similarly for the 100 gigahertz band. This point out these three bands that come out in the oscilloscope channel now require some amount of processing to put everything back together. And so the first thing we would do is draw this. This is all done digitally, software. So those are DSP-based mixers, basically. So here you're trying to undo what you did in the analog domain in the digital domain.
Now, some of the challenges.
ANIP, Annie Pharmaceuticals, announcing FDA approval and imminent launch of Refabulant capsules, USP. That's Alpha November India Papa ANIP. BDX, BD acquires Scanwell Health to expand and scale digital at-home testing. That's Bravo Delta X-ray BDX.
There are a lot of group-to-light distortion, especially around the band edges, and that all has to be restored out here.
Terms not disclosed on that deal.
Light correction. Also, before the bands are put together,
That's Bravo Delta X-ray BDX.
phase is changing so rapidly throughout the band where the seam is, the frequency seam, there's usually a crossover phase correction that guarantees that everything sums up substantially constructed. Just so that it doesn't help itself. The other sort of technical challenge is that this local oscillator that is used to mix, these would be the same frequencies, this would be analog, this would be digital, need to be phase. So in some sense we need to know phase local oscillator. We've done that in many different ways in the past. One way that we did in early designs is we injected some dividing down this into some. So our first scopes were 11 gigahertz scope, mix of frequency was 11.5 gigahertz. That's all accounted for. It's all in a single acquisition. We have the same local oscillator phase. Other ways of doing this are to lock the local oscillator to the sample clock of the system. So what that means is that the local oscillator frequency would be derived from a reference which was similar to the reference used in sample those type systems, those are nice because you actually determine phase from something in the
What about the generation of the 67 gigahertz and the 1 gigahertz tones that are used for the mixers? How are those generated? Are they generated with internal oscillators that are multiplied up? How do you generate those?
So in earlier designs we used big tube oscillator, and again those were locked to use the same reference as the digitizing system. In the end, we found that we really needed, well, number one, it makes not is commercially available, makes not
You have to multiply them up.
and so we used most of this area of design is also very technically challenging and is also customizable. Most of the key components that
FTS FactSet reporting $2.79 Foxtrot Delta Sandy. The estimate was $2.99. Revenue of $424.7 million is above estimate. Adjusted earnings of $3.25. $3.25 adjusted. That is ahead of the $2.99 estimate.
And this DSP that happens on the data coming from the ADCs, that happens in FPGAs? The DSP, the mixers, that all your DSP processing, is that happening in the FPGAs?
That's a good question. It could, and it would be nice for that to be the case. But we typically do, one thing I didn't sort of explain about the scope acquisition system is because it has memory inside. Typically the way a scope acquisition works, even in a real-time oscilloscope, which, as you know, is different from a sampling scope or equivalent time scope. So the real-time scope
CUZ, AMZN, Cousins Properties announcing full building lease with Amazon at Domain 9 Development in Austin. That's Charlie Uniform Zulu, CUZ.
until the trigger system is installed. So during the acquisition of the data, really nothing has to be done to it. Once the trigger system tells it that it needs to stop, all of this data can be read out into a computer and processed in a regular PC. We've found that, in fact, using a multi-core, very high-speed
RPTX, Repair Therapeutics, dosed first patient in phase 1 clinical trial of RP6306 in combination with gemcitabine for the treatment of advanced solid tumors. That's Romeo Papa Tango X-ray, RPTX. KKR, BMG, and KKR acquire music interest of rock icon ZZ Top. That's Kilo Kilo Romeo. KKR. SLGL, Soljet Technologies, announced positive update related to FDA review status of Epsolay. That's Sandy Lima Golf Lima, SLGL. RAD, Rite Aid out with their earnings report. Rite Aid reporting $3.25. The estimate what? Disregard that. Rite Aid. Correction on Rite Aid.
Will the scope be able to trigger on signals that arrive on the other ADC in this architecture, or only the DC to 36 gigahertz?
Rite Aid reporting revenue of $6.23 billion. That's below the $6.32 billion estimate for Romeo Alpha Delta. GIS, General Mills, reporting 99 cents. The estimate was $1.05 for Gulf India Sandy. Revenue of $5 billion for General Mills is above the $4.84 billion estimate for GIS.
There are challenges with often getting the signal of interest to the edge of the scope, especially if it's 100 gigahertz signal. How do you deal with that in terms of, do you provide customers with calibrated 1mm cable?
LIAN, Lian Bio announced
From the edge of the scope?
in Frigatine approved under special name patent patient program for treatment of cholangiocarcinoma in pilot zone of Hainan province in China. That's Lima, India, Alpha, November. LIAN. FSII and Partis Biosciences move towards merger with goal of tackling COVID-19 via an oral antiviral for the treatment and prevention of SARS-CoV-2 infections. That's Foxtrot Sandy, India, India.
This information you're describing happens live. You have a spanner of the cable, you put it into the scope.
FSII.
You observe automatically has that cable de-embedded, so you don't even know what is. You don't have to worry about it. It's transparent to the user.
So there you have it, the basic design.
RAD, Rite Aid, sees adjusted net loss per share
Thanks for listening, and I hope it works on you.
Hi, I'm Alan Blankman.
between 49 cents and 4 cents in 2022.
Some of the components used in the LabMaster 10100
That's Romeo Alpha Delta.
Alright, so we saw before where Peter explained the block diagram of the entire oscilloscope architectures for the LaCroix lineup. So what is Alan going to do for us now is going to go and we're going to talk about the actual PCB design for every single component. That
The estimate is a loss of 52 cents
start from, if you remember the block diagram, from the individual
for Rite Aid
36
for the full year.
bandwidth, 80 gigasamples
Romeo
per
Alpha
second.
Delta
And
RAD.
from there, Alan's gonna stroke
Rite Aid
step
share is
by
moving
step
$12.98,
and then finally to the 100
up
gigahertz
58 cents now for
oscilloscope.
Romeo Alpha Delta RAD.
Okay, so here what we have is the acquisition module, the acquisition board for the acquisition modules of the 50, 60, 60.
IMV announced finalization of basket clinical study in collaboration with Merck. Reveals promising top-line data from bladder and MSI high cohorts. That's India Michael Victor
One of the input channels.
and Michael Romeo Kilo.
Signal is coming from the front panel, which isn't shown here, but it's coming straight into the sample and hold hybrids. Straight coax straight in so that you don't need to worry about sending that signal, high bandwidth signal through the board. Instead you have coax matched as closely as possible straight into the sample and hold.
So this input right here, underneath this is the ASIC designed by LaCroix, which will accept the signal up to 36 gigahertz into the track and host, which then will split into two.
Correct, that's the 36 gigahertz monolithic sample and hold channel.
So one other thing before we flip it over is that Alan wanted to point out the way the signals come out. So you were saying about the signal distribution?
Yes, so in the center is the monolithic sample and hold, and what we do is we split that into 16 signals, and 8 go to
CLSD, Clearside Biomedical, announcing safety results from Oasis Phase 1/2A clinical trial of CLS-AX for the treatment of wet AMD. That's Charlie Lima Sandy Delta.
and do digitization of those signals at 5 gigasamples per second each. So effectively we have two 40 gigasamples per second ADCs on each channel that are then interleaved together to get 80 gigasamples per second for the channel.
Yes, and then in fact you may not notice here, if you look closely here on the diagram, you can see you can see two of the traces, two differential traces here, but if you look at the edge of the connector, you can see the remaining ones come out. There's more than 8 here because some of them go, as you mentioned, go to the trigger circuitry, which is in the center, I believe, right here.
Also, this kind of interleaved approach is very common now in the industry. That's how you end up being able to get the very high sample rates up to 240 gigasamples per second once we also do the digital bandwidth.
Alright, so we flip the board over, so tell us what we're looking at.
Okay, so here on the other side, and you can see a lot of heat sinks, and we can see for each of the 4 channels, we have, in the center, we have the sample and hold. On either sides is that analog to digital converter monoliths. And then after we do the analog to digital conversion, we send those samples now to a bank of memory chips. So we design those chips as well. So we have what we call our MAN chips. So we can see here on these daughter cards, we have individual hybrids now mounted there. So each of those is going to be receiving in some number of samples from those ADC chips, so that we can get a total of about 512 megapoints on each of those channels digitized.
So there's a tremendous amount of data flowing through this board because you have 40 gigasample per second ADCs here. So there is on this board alone 8 40 gigasample per second ADCs, each of them at 8 bits. So you can calculate the amount of data throughput that's on this board, and you can see
individual power supplies that provide the appropriate voltages to each individual channel. So this is actually quite a modular design in that sense, because your memories are completely independent, designed to couple with your own ADCs.
Yes.
So this slice is independent from that slice, and the data can be then combined and converted and processed later on.
Correct. Part of the signal flow is to take the signal that's being taken into the sample and hold and splitting each of those signals and routing that to the trigger chip. So in the center here is our MTT trigger chip, which is now going to look at that signal and then make that decision as to whether or not the scope should trigger. So there are a lot of different trigger capabilities. You can trigger off of an edge, you can trigger off of a pulse width. So that's another one of those, another chip that is designed in-house that's custom built to give the oscilloscope the ability to acquire only the signals that you want to see.
And then you were mentioning also that the interface between this acquisition box and ultimately a processing unit and the display is handled through these connectors.
Yes, in the center, those four connectors, those are receiving all the data that the MAMs have stored, and then those are then taken through PCIe bus to the master control module.
And these memories, you were saying that they were coupled to the ADCs at 10 gigasample per second. That's the data flow rate that they're able to accumulate as the scope is running. So each memory module is coupled to its own ADC, like we were saying before, and then all the data is captured at 1/4 of the rate of each of the ADCs ultimately. And then you can collect all of that together and then feed it out through the PCI Express to the main box and ultimately display it on the computer. So now that we've seen this architecture, we now have access to 4 by 36 gigahertz of frequency that we can analyze between these 4 channels. So let's go ahead and take a look at how they use this to build a 65 gigahertz oscilloscope now by doing DBI technology, by attaching this frequency stitching in order to get the performance from that. So let's go ahead and take a look at the microwave pieces that go on top of this to accomplish that.
Here's the front panel of the LabMaster 1065 ZI. So here we have 4 connectors that are what we call the A inputs, and those are for 36 gigahertz operation. We supply crown connectors that connect to give you 2.92 millimeter connections for each of those channels. In the center here we have 2 inputs for the 65 gigahertz operation. Each one of those comes supplied with a V2V adapter so that you can put now in connect a V cable for your signals for frequency content up to 65.
Okay, and then how does the signal flow from those connectors into the instrument?
Okay, so when using it in 36 gigahertz mode, the signals come through a switch and then down into the board, straight into the monolithic sample and holds. For the 65 gigahertz operation, we have our digital bandwidth interleaving capability that we bring to bear. So that's going to take and use 2 36 gigahertz channels and do a frequency interleaving approach to get you a 65 gigahertz result.
So you can see that
NKLA Nikola confirms settlement with the SEC company to pay $125 million civil penalty in 5 installments over 2 years. Settlement resolves and concludes all government investigation of Nikola. Nikola remains focused on meeting previously stated key milestones. That's NKLA, November Kilo Lima Alpha.
This component here is receiving the signal from the front panel, and that's now a diplexer that's going to split the signal into high frequency and low frequency components. So the low frequency is going to be from DC to 36 gig, and that now is going to get routed down through switch down to the MSH,
right,
for digitations. The other path that has the high frequency content. So what we need to do with that now is to send it over to a mixer, which is going to be mixed with a local oscillator that's going to now bring that down. It's going to down convert the signal down to roughly DC, not exactly, but down to DC to 36 gigahertz. And now that's going to get routed now down to the board on the other channel of that pair, and it'll get digitized as as well. So now we're digitizing that input signal with 236 gigahertz ADCs. We're going to take the waveforms that we get out of those 236 gigahertz ADCs, and now use digital signal processing to up-convert what we previously had down-converted back up to the high frequency band, and then put that together with what we digitized for the DC to 36 gigahertz so that we can recover the waveform of the signal that was input to the scope.
Yes, and you can see that part of the complication of why there are so many components on this board is that it's not just a signal path that you have to take care of, but there are calibration signals coming in and out, which you have to switch in and out depending on what the scope is doing. But ultimately, at the end of the day, the simple message of it would be that a signal comes in, it gets broken into two frequency bands, and then they're fed down into the board from the back connectors we saw earlier, and then all of these things work together. And of course, everything you see here, all the connections and all the switches, all the interfaces are seamless. The user doesn't see any of that. The instrument automatically takes care of switching between all these modes, and the user just has to worry about applying the signal to the instrument.
And there's a lot of art in this. You can get these components and put them together, but that's not going to give you an oscilloscope performance that you need. You're needing to look to have good channel matching. You want to have the jitter reaching channels be as tiny as possible, so that you're looking to match not just path lengths of all of these cables, but also, for instance, to match SN1 or VWAP for each of these, so that you can really have a tight match, not just between channels in this one acquisition module, but the LabMaster architecture allows you to take many of these acquisition modules and put them together to form an oscilloscope with many channels.
So how
to
many
get that channel match?
Yeah, so how many channels at 65 gigahertz can you have currently?
You can have 40 channels at 65 gigahertz as one oscilloscope.
Yes, so you can have 40 channels of 65 gigahertz capture synchronized perfectly together in a massive analysis system that all come together. And because again, this system is built, the devil's always in the details.
Yes.
There's a lot of stuff that goes, a lot of engineering goes into making this happen. We're simplifying it by just explaining the functionality, but this is really is a work of art.
Right. So when you say the word perfect, that's a word that always makes me shudder a little bit. Nothing's perfect, but yes, as close to perfect as you can get. We have a 10 gigahertz reference clock that's fed to each of these acquisition modules, and so that actually is coming in to the oscilloscope and into this distribution box where we have 4 of these blue cables are now routing that 10 gigahertz clock to each of the components, to the different ADCs as well as to the chigger chip.
So now you can see how this architecture can be used to digitize 65 gigahertz, but now really the exciting and interesting part is to how do we extend that even above that. This is already difficult to synchronize and coordinate, but now to get signals up to 100 gigahertz, you're running into even further problems which don't exist in a coax system like you see here. Now you have to have waveguide components. Now your frequency sampling, the frequency LO signal going into your mixers, as we saw Peter explain, now has to be above 100 gigahertz, and those are a whole different ball game there. So I'm excited to go on and take a look at now the same acquisition board you saw before. We remove all of this and replace it with a single 100 gigahertz channel that does a times 3 frequency combining technique. And let's go and take a look at that. And here we go. This is where all the magic happens with the 100 gigahertz DVR architecture. And what we've done is that we've also placed a little block diagram here just to remind you of what it looks like. There's nothing under the paper, so you're not missing out on anything. This is a really early model, so it has some of the microwave switches here that are not installed. But Alan's going to walk us through from the 100 gigahertz input, which is a 1 millimeter connector, and then we're going to go from there and then think about how the different bands are architectured, just like we have the block diagram here. You can see that the reason this may look a little bit simpler at the beginning is because there's only one channel at 100 gigahertz. The previous system we were looking at had 2 channels at 65 gigahertz, so therefore they had 2 of the half. So if you want to have 2 channels at 100 gigahertz, you'd have to replicate this again, of course, and you'd have to have a whole different acquisition board. So go ahead and tell us a little bit about how this works.
Sure. So this is what we refer to as a DVI triplet, where the 65 gigahertz use 2 36 gigahertz channels. This one's going to use 3 36 gigahertz channels in its digitization, and using DVI to get to 100 gigahertz. So the signal comes in over here on the right side of the board where between the high frequency band and the middle and low. So the high frequency band then goes into some stages for amplification and makes its way over to a mixer where it's going to be mixed with a 102 gigahertz local oscillator. And the output of that now is going to get routed down into one of the 36 gigahertz channels for digitization. From the other side of this first diplexer, we're going into now a second diplexer, which is going to split off the low frequency content from 0 to 35 gigahertz and as well as the mid frequency content from 35 to 66.5. So the low frequency is taken out from where that right cap is and routed over to a switch and then down into the board, into the monolithic sample and hold chip for digitization.
And right now that's not there.
Right.
Just to remind everyone that this pad that's going to an ADC, because it's an early model, that pad is not there, but eventually that will go back down to one of the digitizing channels we saw before.
Right. So you can see a cutout here where one of those switches would be, and there's another cutout under the paper for another one of those switches to route the signal down into the board, into the acquisition board. So from the second diplexer, we're taking that output, going through this RF module, and then into a mixer stage where we're going to mix that signal, which now comes in with 35 to 66.5 gigahertz frequency content. We're going to mix that now with the 67.5 gigahertz local oscillator, and now we're going to get 1 to 32.5 gigahertz frequency content coming out of that mixer stage, and then now that's going to get routed down through a switch down to the acquisition board into another one of the 36 gigahertz channels. So we have now 3 36 gigahertz channels being digitized, one doing low frequency, one doing mid frequency, one doing high frequency. And now those 3 36 gigahertz digitizations are going to be taken and processed. The mid frequency is going to go through DSP that's going to upconvert to bring back that to the 35 to 66.5 gigahertz band. And for the 36 gigahertz digitization for the high frequency band, we're going to upconvert that in software to the 66.5 to 100. And then we have these 3 data streams that we're going to now put back together with DSP to come out with our final waveform, which will have that 100 gigahertz content.
Yeah, so just to recap everything that you said here, so if you think about it in terms of signal path, 100 gigahertz signal comes in here, goes through here. This is the 66.5 to 100 gigahertz path, so the signal comes through here, down converted. Here's our first output, goes to be digitized. The signal then is split again, goes through here, mixes down. Here's our second output, that's from 33 to 66.5, and then our first 0 to 33.5 gigahertz, so go in that direction. Another couple of interesting things to note here is that, again, remember, based on also what Peter said, that the sampling frequency of the mixer in the high band, the highest band, is at 101 gigahertz. So you can see they've chosen to connect those two pieces together with the waveguide as opposed to with the coax, because it doesn't make any sense anymore to use coax at those frequencies. And there's also a whole bunch of synchronization clocks and so on that Peter mentioned that are present in this, without going into too much detail. But yeah, there's quite a bit of stuff happening here. But the really nice thing about it is that if you think about it in terms of architecturally, they have built all these systems on the initial digitizing board. So they just reuse the ADCs they've designed, and they build continuously these frequency interleaving techniques in order to get higher and higher digitization bandwidth. All right, and here's the part I'm sure you've all been waiting for. So here we have a full system put together, as well as some optical tests in order for us to generate very high frequency signals. But before we go through there, just a quick overview. Here at the bottom, we have the 100 gigahertz scope, as we saw the internal construction. So the board that you were looking at last is essentially in this direction. Here's the 1mm front-end connector, so that's what we're looking at. So this would be the 10-100ZI module, and with all the high-end sampling modules from LaCroix, they have a lab master component here, which then is a master control module, which collects all the data coming from the sampling modules at the bottom, and of course has a display on it, which will take care of processing and displaying and all the math functions, all the advanced systems that they have there. And we'll show you the back of this and how these things are synchronized together as well. So I'm going to pass it back again to Alan. Describe to us what we're looking at.
Sure. So what we have here is our instrument here, which is a coherent optical receiver from our partner Coherent Solutions. We partnered with them to use the LabMaster as an optical modulation analyzer. We're not going to run it to optical modulation analysis today, but we're going to use their instruments to do experiment where we're going to beat some lasers against each other to look at a tone. So the LabMaster is an important piece of equipment, and we have a lot of customers in the optical community. So we thought we'd do an experiment today using optics. So we have here this yellow fiber. So we have an optical fiber that's bringing a signal into the coherent optical receiver. The receiver is going to demodulate that signal. It has a local oscillator that is being put back to be used, and we're going to take the output of that into the oscilloscope. Right now, we can see that our laser is off. We're starting off here with just sort of a noise trace, and what we're going to do is we're going to get the instrument up and running in a minute. On the right side.
So sorry, Alan. So the idea is to take a laser here that is sitting at 194 terahertz, and you're going to generate another laser for us from another IQ transmitter that has a frequency of up to 100 gigahertz apart from this laser, and the product of those two, mixing product of those two, is going to give you an analog electronic signal, which we can then stress the scope up to 100 gigahertz. And that's basically what we're trying to build here.
Yes, correct. Yes. So on the right over here we have Coherent Solutions. We have their complex modulation transmitter model IQ transmitter. So this instrument is designed to be able to output a dual polarization signal. Right now we're going to use it in the mode where we're simply taking the internal local oscillator out. Later we're going to use it in a different way. But right now we're going to take a 194.05 terahertz optical signal. We're going to bring that through into our coherent optical receiver, where, as Shariar described, we're going to beat that laser 194.05 terahertz against the 194 roughly.
Benzinga market update. S&P futures up 46. The Dow futures up 328. Nasdaq up 182.25. Crude is up $1.25 at $69.86.
The back of the acquisition.
Bitcoin futures up 21.65 at 49,225.
How it is possible for them to have so many channels at such a high bandwidth all synchronized together. The way they connect to each other via a bus at the back and all the synchronization. So tell us that.
Okay, so we have here the back of the master control module, the LabMaster MCMCI, and at the bottom is the acquisition module, the LabMaster 100 CI. So this is a modular system. You can see how they're connected. So at the top here we have the 10 gigahertz clock outputs. So there are five of them. We're using one at the moment connected to the ACK module. So this is using our channel sync architecture to be able to then keep multiple acquisition modules locked together using a common time base, 10 gigahertz. If you conventional instruments use 10 megahertz or 100 megahertz to sync, you can't accomplish the close channel matching you get with such a reference clock. So we use the 10 gigahertz clock distribution. Here we also have a PCIe cable using one for each of the module that you can attach for syncing different trigger signals and such. And then we have the data cable, which is also PCIe, with more lanes than the sync cable. So they come into the ACK module. So we have our three cables connected. This system supports connecting up to 5 acquisition modules. So you can connect 500 gigahertz scopes. You can connect other scopes in the series. So you can have a system with, let's say, 20 36 gigahertz channels, 10 65 gigahertz channels, 5 1 gigahertz 100 gigahertz channels. The architecture supports even more acquisition modules. So we could use a separate hub, a channel sync hub we call it, to be able to route these signals to 100 gigahertz channels.
So
That would
that
be
would-
a powerful system.
Yeah, so
indeed.
that would be in that configuration you would have 20 240 gigasample per second 8-bit system.
SKYW,
Just
ERJ, ZNTE, SkyWest. Even SkyWest announced partnership to develop regional operator network with an order for 100 EVTOL aircraft. That's Sandy Kilo Yankee Whiskey, Echo Romeo Juliet, Zulu November Tango Echo.
The jitters between those two channels, it's going to be nothing more than perhaps 150 femtoseconds.
So your clocking scheme noise floor is about 100 to 150 femtoseconds in total.
That's the matching, the channel.
Oh, the
channel
matching. I see.
match.
Do you have a specification on the 10 gigahertz?
KTTA, Pasithea Therapeutics, tells Benzinga Pasithea has opened its second London clinics offering intravenous ketamine therapy to patients. That's Kilo Tango Tango Alpha KTTA. KPTI, Karyopharm, and Minari Group enter into exclusive license agreement to commercialize Nexpovio in Europe and other key global territories. That's Kilo Papa Tango, India. KPTI.
So these lasers take a little bit of time to start up.
MNSO, Beniso announcing $200 million share buyback. Michael November Sandy Oscar.
15 dBm, 194.5 terahertz. This one is cranking up also to about 15 dBm, 194 gigahertz. So the difference should be
MNSO,
signals. Take a look.
MNMD, MindMed provides status update on IND for phase 2B trial of LSD to treat generalized anxiety disorder. That's Michael November, Michael Delta. MNMD,
The signal that you're seeing. Over here we can see
UNVR, Univar Solutions, announcing new distribution agreement for Kaisek's natural taste and sensory solutions, colors, and antioxidants. That's Uniform November Victor Romeo. UNVR.
200 picoseconds per division.
ONDS, Ondas Networks, receives order for North American Rail Lab. That's Oscar November Delta Sandy. ONDS.
The oscilloscope can be used in a few different modes. We could use that 100
MOSY and PRSO, Moses and Paraso Technologies closed business combination. That's Papa Romeo Sandy Oscar, PRSO.
Or we could go and just, if I click this button, we would just use it as a 4 channels at 36 gig.
So it's very nice that buying the 100 gigahertz option still gives you all the frequency bands that you would want to work at.
PXS, Pixis Tankers, announcing delivery of 2017 built MR product tanker and completion of debt financings. That's Papa X-Ray Sandy, PXS.
Okay. So just one other thing that I wanted to also point out is that what you're looking at here, and again correct me, Alan, these two coherent lasers are unlocked from each other.
Correct.
So as a result, you have a phase that is
CTO Realty Growth announcing acquisition in Orlando, Florida, with a new corporate office location.
because that's just the nature of the unlocked lasers. The variation that you see
That's
here
Charlie
with the
Tango
oscilloscope
Oscar,
is
CTO.
from the lasers. In fact, because you have such a high sampling rate, you can actually characterize that drift if you wanted to, and find out how fast the lasers drift with respect to each other. And if you're working on things like optical phase lock loops and things like that, a system like this at very, very high sampling can allow you to lock lasers that can be 100
XL Fleet installs charging infrastructure to power Apex Clean Energy's electrified vehicle deployment. That's X-Ray Lima, XL.
Or we could see over longer time periods, we could see what the trend is, if it's how
PAR, PAR Technologies subsidiary, announcing $15.2 million U.S. Navy award at Lago Patria, Italy. That's Papa Alfa Romeo, PAR. COMM, CommScope, Ectra selects CommScope's home networks to supply its customers in Lithuania with VIP 7100 UHD set-top solution. That's Charlie Oscar Michael Michael. COMM. HTBX, Heat Biologics, announcing planned acquisition of Elucis Therapeutics. That's Hotel Tango Bravo X-Ray. HTBX.
we could add some Sinex over interpolation. And go to the channel
AEHR receives order for 4 Fox NP test and burn-in systems for characterization and product qualification of new photonics-based devices. That's Alpha Echo Hotel Romeo. AEHR.
That variation. So I'm just going to go back this off a little bit so that we're not overflowing.
NTAR, Nextech AR signs multi-year virtual event and marketplace contract with Restaurants Canada.
Seeing that we've got sine waves.
That's
Let's
November
see.
Tango Alpha Romeo, NTAR.
So I'm going to go up here and I'm going to turn on my measurements. And I'm going to go to standard horizontal. And this is going to put up a bank of measurements. Rise time, fall time, period, frequency. So here we have a frequency column that's showing us the value of the very last cycle and then the mean. And this is what we can look at. This is the average frequency that's been measured over all of the cycles that have been accumulating. So it's accumulating data. We got a 50.05, et cetera, gigahertz sine wave.
Perfect.
All right, so the next thing you might be interested in investigating is the frequency content. So we could take this waveform, we could do a Fourier transform of it. So I'm going to go do that now. So I'm going to go to our math button here. One way to put up a math function on the screen. So here, since I actually set this up before, the category frequency analysis is there, and I'm going to choose FFT. And looks like we already have it selected for F1 FFT. So we look to put a few more grids on the screen if we want. So now we have our waveform, a zoom, and we have an FFT. So here, given the time base that we've selected, we have some frequency spacing in our FFT. We have some span based on the sample rate.
Yeah, so actually, it's interesting because this is 110 gigahertz, correct? Right now.
Yes.
Yeah, so that little area that you're looking at, and this brick wall filter is the DSP filter at 100 gigahertz that you have selected because the sampling rate is 240, so FFT will lead to a very large span. So I guess you can go ahead and zoom in by changing the time base.
Yeah, so the reason why we have that span as well is because we're doing sin x over x interpolation.
Yes, so you get lots more bandwidth. Yeah.
That's giving us more frequency. So I can go in and I can change, for F1, I can go and I can change the scale, for instance, instead of being 120 gigahertz per zoom, let's choose 12, and then we can put the center here at 60 gig. And so here we have now sort of a better scaling. So let's go and now actually require a longer waveform so we can get some better resolution in the spectrum. So I'm going to go here. And of course, we could do everything from the user interface, but there's certain functions that I go straight to the front panel. Some things I like to go to the user interface.
Yes.
So, but let's go to a longer time base. So here I'm cranking it up slowly, and here we can see that we have a faster, an FFT with better frequency resolution.
So you can see that tone. This tone will then correspond to our 50 gigahertz beating of the two lasers, and you can see that it ever so slightly wiggles back and forth because the two lasers are not quite locked to each other. So you can see the variation there.
So we could also get a measurement of that frequency. I could select my to change one of my measurements. Right now we're set for what's called standard horizontal. Instead, we could look to use what's called my measure. First, we could do a quick setup. We could get all of these from the standard horizontal. So that's what we had before, but now I can set up P9. And let's take the source, that function, F1, measure. So here we have our selector for all the different measurements that you can do. So here we see there's a lot of measurements built in.
There's a really extensive set of advanced mathematical functions built into all of the Lacroix LabMaster units, and we can use math as a function of math as inputs to other functions and create really for 194.075. That would then generate a 75 gigahertz analog tone in the electrical domain, which we should be able to capture again with the oscilloscope.
Okay, so I'm going to change it to 175. The laser turns off, turns back on. Now it's ramping up in power. And we can see on the scope that effect. We have now a peak that is it's showing up here. And we have here now a big change now in our trend plot. So our trend now shows that we have changed our frequency from one level to another. And for instance, we could bring up, for instance, a cursor and look to apply the cursor to that waveform and see what those values are.
So you can actually see an interesting effect here where here in the trend you can see that the impact of the laser being turned off and turned back on and so on, where you can trace that exactly, and then by putting a cursor on it you can then read each individual point. I assume.
So here we have at this point that was where we were at 50 gig, and over on this side now we're up at 75.
Yes.
So now our measurement here is where those measurements weren't clear. So this is not showing 75 for the average; it's showing it for the value, as you can see right here. But here it's still building statistics, so we could clear our sweeps and we could see that this now would be a more solid 75.
Yes, that's the average basically. So if you press clear screen right now, you will.
Well, let's clear. We don't want to clear the math sweeps.
Yes.
We'll just clear the measurements.
Okay, perfect.
There we go. So
That's the other nice thing is you can independently clear statistics for various components that are being displayed on the screen without clearing other things.
Right, so this clear sweeps button on the front panel would clear out all of the measurements. But here now, this is how you can clear out just the measurement system. That clear sweeps clears out not just measurements, but the math
Yes,
functions, clears out all the
yes.
processing.
All right, well, let's push it further. Well, let's try go all the way to 100. Let's see world's fastest 100 gigahertz true digitization of a signal, and that at this point no one else in the industry is able to do. Here we go. So Alan is changing it. So if you take a look here, now we're sitting at 194.1 terahertz, and that would be 100 gigahertz. And then we can go ahead and see the signal. I guess you can change the vertical scaling now in order to have even more resolution. But take a look at this.
So here we have our
laser tone.
Since we have now we're at 100 gigahertz, we have some attenuation. And part of that is just due to the cabling. This is coming out with out of a K connector. So this isn't rated to go out to 100 gigahertz. The receiver goes out to about 70.
Yes, yeah, exactly. I want to make sure that you don't mistake this attenuation with the attenuation of the instrument itself. This is an attenuation of the cable plus the optical detector. When you're beating two lasers together, that detector is not designed to put out a 100 gigahertz signal. As a result, its frequency response is rather limited. But the scopes, of course, has a flat frequency response after extensive calibration that is done. So that should be not a problem. But one thing I want to again point out here, this is 10 millivolt per division, correct, Alan?
Correct, yes.
So this is a 10 millivolt per division signal, 100 gigahertz being sampled and digitized. So it's not like we're dealing with 1 volt peak-to-peak signal here, which you may assume digitizing would be a little bit easier, but it's the 10 millivolt peak-to-peak. So very, very small signal, true digitization, 100 gigahertz, very impressive.
We can also adjust our zoom here for our zoom trace here.
There you go.
So there's a zoom in of our of the source. You can see that thin blue trace, which is now being zoomed in.
Yeah.
So while we're looking at now 5 nanoseconds per division for the full sweep in channel 3, our zoom trace is showing 20 picoseconds per division.
Yes, and again, the amplitude variation and phase deviation you see here is again due to the lasers being incoherent to each other, but you can see we have a true digitization of 100 gigahertz of signal. I would imagine for the first time. I'm sure you've shown this before, but definitely a first time on the signal path. 100 gigahertz digitized signal, pretty incredible. So something that is also interesting to try to really show not just the capability of the scope to capture signals that are very high in frequency,
frequency up to 100 gigahertz, but also show some correlation between various frequencies. So here we're looking at what we had before. We have a single tone. We're capturing right here that this tone has 90 gigahertz as before. But now what we're going to do is we're going to also apply an RF signal to the modulation port of the IQ modulator, but only on the I side or on the Q side, and this will allow us to create a double sideband, which is equivalent to an AM modulation in the frequency domain. So if I were to apply, for example, a 2 gigahertz signal to the IQ modulator, I will see two tones at the sides. There you go, Alan just turned it on. Now we have two extra tones and we're capturing this. Remember, this is 90 gigahertz, this is 88 gigahertz, that's 92 gigahertz. But another thing that I wanted to say to convince you that this shift in frequency is not because of the instrument, but because the lasers are on lock, is that you can see these three tones moving together, and that's because the stability of the modulation signal, the 2 gigahertz RF you're applying, is much more than the coherence between the two lasers. So you can see that they are together. So Alan's going to explain to us a little bit now how we can measure the difference between these frequencies and show that it is a stable frequency measurement.
Okay, so let's turn on those measurements, the exit max measurements. So I'm going to just turn my measure table back on. You see here I have some measurements already set up. So here I have in parameter 1, exit max, and here my
YTRA, Yatera Online announcing their earnings. Revenue of $6.1 million.
finds the peak. So I have P2 set up to be.
That's below the 10.6 million estimate expected.
Do this for the third one as well, but to keep it simple, we'll start with
Adjusted
those
revenue of 10.6 million is in line with estimate.
three. I have that set as math 1 parameters, and that's now taking the difference of the measurements of P2.
That's Yankee Tango Romeo Alpha YTRA.
We come up with a mean value of something very close to 2, 1.9997.
Yeah, so just remember exactly what we're measuring here. This 2 gigahertz signal is the difference between a signal at 92 gigahertz and a signal at 90 gigahertz, or 88 gigahertz and 90 gigahertz, and this is live digitization. I know that we may have gotten used to seeing these signals, and you may think that, you know, this is not a spectrum analyzer, this is an oscilloscope. It's capturing from DC all the way to 100 at the same time, and we're looking at two tones very close together at 90 gigahertz, and you can see that. So this 2 gigahertz signal here matches our synthesizer RF input right there, which yeah, there you go. If you push that little piece of fiber connection to the side, you can see there it is, just blocking the number. There it is.
There we go.
There you go. So now you can see that's a 2 gigahertz signal that we're feeding into the IQ modulator, and the small amplitude is only 100 millivolts. And then you can see that we have no problem digitizing the entire spectrum and measuring the difference in frequency, and you can do, of course, all kind of fancy analysis on it.
So one thing we can also now do is we could also increase the amount of time that we're zoomed in on. So here you can see that modulation pattern.
Yes, remember that if you feed a signal to only one side of an IQ modulator, you get a double sideband signal on each side. It's equivalent to an AM modulation, which is what we're looking at, and you also have the carrier here in the middle, which is the result of the two LO signals feeding together. So this is a very clear example of capturing small deviations in frequency by digitizing the entire signal. Now you can think about this as being a broadband optical signal, which you can, of course, then demodulate and post-process, and there have been record-breaking optical transmissions, for example, from Bell Labs using this oscilloscope for the first time, showing really high data rate dual polarization optical systems using the signal measurements. Now the next thing I want to do is to set up another experiment quickly, just so we can see some really fine pulses that we can capture because of the high sample rate of the oscilloscope. Alright, so as our last experiment, what we're doing here is we're going to try and capture a very narrow pulse coming from a femtosecond pulse laser, which is a unit you see all the way over there. So the idea is that we will generate an extremely narrow optical pulse here. And that optical pulse is fed to a photodetector with a really high bandwidth in the order of 80 or 90 gigahertz or so, and that will get converted into an electrical pulse. That electrical pulse is fed into the 100 gigahertz sampler of the scope, and we should be able to capture that and look at that pulse. This is a particularly difficult measurement to do because the pulses are really narrow, and in order to capture and trigger on them, there's a trick you can play where you can actually trigger off of one of the other channels of the oscilloscope with the synchronization signal that's coming from the pulse generator itself, and then you correlate that and you can do some computation in order to generate the pulse. So Alan's going to explain to us exactly what it is that we're looking at.
All Alright, so we have a laser from Kalmar Opticon. It's something like 100 femtosecond. It's coming through an optical attenuator, and then what's hiding behind here is just a joint, a union, and then into the photodetector, and then into the 100 gigahertz channel. Then we're using a Pro Power bus here with a sort of just a specially designed 2-volt supply to bias the photodetector. So we have the oscilloscope set up. Here we're acquiring our waveform.
AAPL, Apple Insider. New research claims Apple has about 25% of the global 5G smartphone market, beating its rivals in both numbers of phones sold and revenue.
External trigger signal as well as some software-assisted triggering and
That's Alpha Papa Lima, AAPL.
So here we have our pulse, and now we're doing some analysis on it. So in math function F1, we have that set up for what's called our p-trace mean. So what this is doing in F1, it's building an average of our persistence map using channel 3 as its input, and then it's outputting a waveform that is the mean value through that persistence map. So it's finding where that signal is in the persistence map. Then we take that and we're zooming here on the lower right. We're zooming in on that bright yellow section of math function F1, p-trace mean. So now here we have the best representation that we can show you of the measurement of this laser pulse. So the next step is to do some analysis of it to see, to quantify it. So over here in our measurement table, we have it set up for a few measurements. Here we have it set P3 set up for the width at level measurement. So the level is currently set to 50% level, and here we have a marker that shows that. And so we're recording a value of 7.786.
Yes, that's the width of the pulse at a 50% level.
Right. Then we're taking this and now looking to understand what the rise time is of the integral or the integrated pulse. So that would give us our step. So here we have a step that's the integral of our pulse. And when we look to make a rise time measurement on that pulse, rise time 2080, rise time 1090, we measure 4.2 picoseconds for 2080 rise and 5.9 picoseconds for 1090. Extremely fast rise times that you can only measure if you're using 100 gigahertz.
Yes.
100 gigahertz oscilloscope as we're doing here.
Yes, and it's interesting to note at the same time as these pulses, while being extremely narrow in width, are also really infrequent. They are 100 nanoseconds apart. So this pulse here, as narrow as it is, the next pulse that's coming from the laser is 100 nanoseconds after. It's almost a lifetime later compared to the width of the pulse itself.
Right.
And the amount of energy that the scope is capturing in this pulse is absolutely tiny. And so on top of that, you have to, of course, trigger it, as Anne explained, with the tricks that they're playing to do that. And when you're integrated, you can then measure the total amount of energy in that pulse and so on. And the limitation in this pulse here is, in fact, essentially primarily because of the detector itself, because the detector doesn't have enough bandwidth to support. So what you can do with this mechanism is to actually measure the bandwidth of a really, really fast photodetector by measuring the pulse width, because you know the scope's 100 gigahertz bandwidth is not your limitation in this case. And there is no cabling, so the calibration plane of the scope is at the edge of this connector. So whatever you see is now the bandwidth of the detector itself. Yeah, so I think this is a pretty good and conclusive test to do to show some of the more advanced capabilities of the scope.
Right. So with the 100 gigahertz oscilloscope, we've got an oscilloscope now with a bandwidth that really is wide enough that oscilloscope bandwidth isn't a limiting factor now for making these measurements, and either for fast pulse measurements of this type or for doing work in other optical areas like coherent optical, looking to understand companies looking to measure very fast baud rates and forming constellations at 80 and 160 gigabaud. That's key players, key customers for this product.
Alright, so we had a good in-depth look at electrodes
imagine this instrument is intended for a very, very specific application, because even fiber optics barely have bandwidths that can reach the bandwidth of this oscilloscope. It's really intended for next generation optical or even wireless communication, but it has some really unique and interesting features, which I'm discussing with Teledyne Lecroy separately for some research applications and so on, which would be very interesting. So I really highly recommend that you go and take a look at some of their material that's available on their website. They have a publication that shows how this technique works. The person who's invented this technique is an IEEE fellow, so he's got a lot of experience doing these type of things. So go ahead and take a look at it. And next we're going to go walk through the factory. You're going to see the different stations, and this is not just a factory that assembles, of course, the 100G scope. This assembles the entire lineup of all their Teledyne Lecroy's oscilloscopes. So it should be pretty interesting for you guys to see how a system like that is put together. They're very neat, very organized, as they have to be in order to create these instruments with the grade that they do. So let's go take a look at the factory tour.
Hi, my name is Tyler Cox. I'm the Vice President of Manufacturing Operations here at Teledyne Lecroy in Chestnut Ridge, New York. We're going to take a quick tour through our facility.
Thank you.
As you can see as we walk through the facility, this whole manufacturing floor is actually set up in a cell-based process, meaning depending on the kind of product that we're building, the whole operation is done within one particular cell. So as we walk around, we're really divided up by bandwidths because the equipment and the processes and the know-how that are required to build a 4 gigahertz scope are different than the processes and equipment and calibration that you have to do a 40 gigahertz scope. So as we walk through, we'll see we're really divided up into what we call a mid-bandwidth products, meaning things that range really from 300 megahertz up to 4 gigahertz, a high bandwidth cell that would really do from about 4 gigahertz up to 20 to 30 gigahertz. And then we have one tucked away in the corner called an ultra high bandwidth cell. And this is really where those very high end 65 gigahertz, 100 gigahertz kind of products are going to get put together.
Good morning. My name is Mark DeVries. I manage quality assurance and manufacturing at Teledyne Lecroy in Chestnut Ridge, New York. I'm going to walk you through the assembly and test of the product which we call HDO 4000 6000 oscilloscope. The process starts with acquisition assembly, which is what we have here. This was an acquisition card, and it's as delivered from our subcontractor. All the components are soldered onto the board. We have our front end, which is under this shield here, feeds into analog to digital converters, and then memory modules. This chip here, which is green, is a custom Lecroy HTT, which is our timing and trigger chip. At this station, which is an assembly station, we will glue on the heat sinks in the appropriate step, put on the appropriate cables, and now this particular card is at its higher level assembly that can now get moved to test. On these trays, we have fully assembled acquisition.
HOTH, Hot Therapeutics, announced submission of orphan drug designation request for HT kit to treat mastocytosis. That's Hotel Oscar Tango Hotel, HOTH.
So Robert, a senior test technician, runs the program, and it's a multitasking time. So while he's doing tests, he can also do programming. The card is now actually being programmed based off of the computer, and when it's done with programming, we can move to test. Let me start over the test, Robert. Yep. Test happens here. This is a fully custom
CYTR, Citrix, highlights immunity biology use of aldoxorubicin in ongoing clinical studies for various forms of cancer. That's Charlie Yankee Tango Romeo, CYTR. HEPA, Hepian Pharmaceuticals, announcing FDA clearance of IND application for CRV 431 to treat liver cancer. That's Hotel Echo Papa Alpha. HEPA. CERT, Certara, announcing FDA renewal and expansion of Certara's biosimulation software for reviewing regulatory submissions. That's Charlie Echo Romeo Tango, CERT. PPSI, Pioneer Power, announcing $12 million order from one of the world's largest mass merchandisers, expected to significantly increase revenue for 2022. That's Papa Sandy, India, PPSI. VCTR, Victory Capital Holdings, announcing new share buyback program up to $15 million of common stock through December 31st, 2022. 3. That's VCTR. Victor Charlie Tango Romeo VCTR.
In the motherboard, we have our AC to DC power supply underneath this fan duct with its fan here, and our AC inlet board, which distributes the power. This back box, at the next step, will get married with the acquisition card in what we call the front box, and we will then have a full-up oscilloscope that we can power. This station here we call front frame and naked
CGRN, Capstone Green Energy, to provide its 600 megawatt energy efficiency system to a Alabama hospital. That's Charlie Golf Romeo November. CGRN.
This is actually a simulation that I'm asking Anki to do for the purpose of the video. This would get screwed in, torqued in, and so forth. At this point, let's just lay the back box over the top Anki after one screw.
TTNP, Titan Pharma, to explore strategic alternatives. Tango Tango November Papa, TTNP.
5 minutes, but for the purpose of video, we're just simulating the construction so we can kind of see how it goes together. Front frame is completed, acquisition card gets put in, back box would then get integrated onto the front frame, similar to what Anki is doing here. Goes together quite nicely. The front box and back box get cabled together. We put cables to the acquisition card. It all gets screwed together. It all gets torqued together.
BBIO, Bridge Bio, Adam Feuerstein of Stat News tweeting, it's the cardiovascular version of Alzheimer's, and for a biotech with a promising drug, it could be a windfall. That's BBIO, Phase 3 study being mentioned, Bridge Bio Pharma, Bravo Bravo India Oscar, the tweet from Adam Feuerstein of Stat News.
And again, this is an example of what we call naked assembly because it doesn't have its final plastics. We can power this up like an oscilloscope, which is what we're doing here. We do Windows updates. We check for some for some testing via our traveler to make sure we are working like a full-up oscilloscope. The turn-on rate here is almost close to 100%, and after power up and Windows updates, the next step
TBLA, Taboola announcing launch of native bidding service, facilitating expansion to display social networks and other platforms to fuel even faster growth, signs new Microsoft agreement through July 2024. Tango Bravo Lima Alpha, TBLA. YUM, Yum Brands, Southpaw acquires 35 Taco Bell stores across Mid-Atlantic region. That's Yankee Uniform Michael, YUM. ADVM, Adverum Biotech provides ADVM 022 development update and anticipated corporate milestones for 2022. That's Alpha Delta Victor Michael, ADVM.
test and calibration sequence. We have 8 CalSol stations, and each CalSol station can test any of our mid-bandwidth scopes.
KRET, Carrot Packaging, announced expansion of its logistic services.
A Wave Runner 620ZI, and here we have an HTO 6104.
And placed an order for 10 Tesla semi-trucks. That's Kilo Romeo Alpha Tango, KRAT.
Let's finish its CalSol. At this point, the technician, Joe, would print out its calibration.
ZGNX, Zogenix submits new drug application for Fintepla in Japan to treat epileptic seizures associated with Dravet syndrome. That's Zulu Golf November X-ray, ZGNX. XELA, Excella Technologies announced partnership with UK's Post Office. That's XELA, X-ray Echo Lima Alpha.
Just so we have a unit that passes, it's about 2 hours on the station. They are automated. We have bigger switch boxes. Our turn-on rate is north of 98% here. So on the mid-bandwidth product, we have 98 out of 100 that pass CalSol, and we're quite proud of that. If a unit doesn't pass, we would typically take the acquisition card out and figure that one out. But very high turn-on rate here. After CalSol, the scope is at its highest common denominator. It can then go into finished goods to be married up with its ultimate sales order, where we do configure to order. Oscilloscopes nowadays have so many software packages that are available. The configure to order process is loading the customer required software packages that they purchased, picking probes from inventory, testing them on the scope that they're going to ship with, final quality control, turn it on, storing test system is exactly that. It's an automated test system. And while we sell into test environments, automated test environments, the primary user of our oscilloscope is a electrical engineer doing debug or research and development. So they will be using the touchscreen, turning the knobs. So we make sure we do that with a human before we ship it to the end user. This workstation is what we call skinning. Skinning is applying the final customer plastics as we see here. We have our front bezel with our encoders and encoder board. We have our back bucket with serial number and trim ring and fee. This process takes about 30 minutes to get everything bundled up. And at this point, when we're done, the scope is at its highest common denominator. It's a full-up scope that if there are no additional options, will be shippable to the customer. This step is what we call lockup. Lockup is final quality control and configure to order. John, who's doing lockup, he's actually been working at LaCroix 19 years, is actually doing lockup on one of our WaveMaster scopes. At this particular step, he puts on the final plastics. We only put the final plastics on here because we do have the option to install increased processor memory if the customer wants, so the plastics are only put on at the very end. Lockup is for WaveMaster is buying the plastics. John will also take the sales order and configure to order. We have about 150 different software options where John can load the software into the oscilloscope. He will power up the scope, use it like the customer, turn the knobs, adjust, work the touchscreen. Even at a lockup, we have a lockup check sheet. This particular one is Rev D, and it lists the 75 steps we're going to go through to lock up this unit. Again, final quality control and configure to order. When John is done, this unit will be put in its box and shipped to the customer with all the probes, accessories, manuals, power cords, everything it needs. So a very key step, and we have our most senior people doing this job because it is, again, the final person to touch the oscilloscope before we ship it to the customer. So what we see here is an acquisition system comparable to a 36 to 100 gigahertz scope mounted in its chassis. The green printed circuit board is mounted to a matrix similar to this. That's a quite large board. As soon as they come in the door, we mount it to this frame. It's a quality assurance step. We don't want the board to bend or be flexed in any way because there's greater than 15,000 components on there, greater than 30,000 solder parts. Under each of the large heat sinks, we have a LaCroix custom analog to digital converter. And these cards are custom memory that LaCroix is designed to work within our acquisition system. Very complex board, but this comparable acquisition card can get used between 36 and 100 gigahertz in this type of chassis. Clearly, to get to 100 gigahertz, we do some additional things though. Is our the top end of our 65 gigahertz oscilloscope, our 65 gigahertz acquisition system. The acquisition card is on the bottom, and on top here we actually have our microwave device, which is essentially a bandwidth doubler. It takes our 36 gig architecture and doubles it up to 65 gigahertz. It's all piped with rigid and semi-rigid cables, very complex, but very accurate and very high tech. So where we are now is what we call high bandwidth and ultra high bandwidth CalSoft. We saw mid bandwidth CalSoft earlier. Here, the station is a little bit larger. We have 1, 2, 3, 4, 5. So we have 8 CalSoft stations for high bandwidth and ultra high bandwidth. Here, we calibrate and do performance verification of our WavePro, WaveMaster, and LabMaster products. At these stations, we can calibrate between 4 and 65 gigahertz. They are all computer controlled, and we have one operator who manages multiple stations.
So you were mentioning that you calibrate up to 65 gigahertz here, and then for the 100G scopes, you have to send them somewhere else?
So on this particular station here, we can calibrate our slaves that up to 65 gigahertz. When we need to go to 100 gigahertz, we work with our engineering group upstairs, and the unit will go upstairs for its final calibration from 65 to 100 gigahertz. So here we have a thermal chamber, and for certain oscilloscopes, we need to do calibrations at different ambient temperatures, starting at 20 degrees C, 25 degrees C, 30 degrees C, 35 degrees C, and 40 degrees C. So what we'll do
it, a lot of effort on everyone's behalf. I want to thank Teledyne for putting this together. This is definitely a very nice gesture on their behalf to show and share the knowledge they have and the experience they have in building world-class instruments. So if you like it, please make sure you leave a comment, give it a thumbs up, and if you happen to buy $1 million oscilloscope from LaCroix because you saw this video, let them know. I'm sure they'll appreciate it. So until next time. Hi, welcome to the Signal Path. In this episode I have another repair video for you guys. I'm going to be repairing this Agilent E4407B, which is a 9 kHz to 26.5 GHz spectrum analyzer. I'm actually recording the introduction of this video at the end of the video. And the reason is because this is a really long video. When I started, I wasn't expecting it to take so long, but I think it's almost 2 hours or even more than 2 hours long. The reason it's so long is because I've spent a lot of time describing in detail how the spectrum analyzer works, from the block diagrams, the schematics, and also by tearing it down, really comparing the hardware and the block diagram that I have available to me to really understand how it works. Another reason why it took so long is because I really did this on the fly. I never opened it before. I didn't know what I was going to look at. So I kind of showed you my thought process step by step on how I went about discovering what was going on, doing some reverse engineering, figuring out the block diagram and the functionality of the unit. So it's going to be a long video, and I hope that you watch it to the end, and I want you to give me some feedback and let me know if this was too much detail or you prefer the video to be shorter. But I think there's a lot of interesting and educational content in this video that I hope that you will enjoy. One other thing I want to let you know is that some of you may know that the Signal Path has a Twitter account that I usually use to announce a new episode is being posted. But I thought that if there's enough followers on the Twitter account, I'll start announcing little interesting bits of information about electronics and technology. No, I won't let you know what I've eaten for lunch or anything. It will be strictly scientific and strictly about technology and electronics. So if you know some interesting idea comes to mind, I'll just write along, let you know some little tiny bit of information which you might find useful. So if there's enough followers, I'll start doing that. And if you like, go ahead and subscribe to it. There's no other benefit other than me having more interaction with you guys. So it might be interesting. No, I hope you stick around and watch the whole video. It's a really interesting thing. Let's see what we can do. So let's take a closer look at the front of the instrument. As I said before, this is the E4407B, 9 kHz to 26.5 GHz ECA E-Series spectrum analyzer. And this one actually has a Type N connector in the front, as typically the instruments that go up to 26.5 support Type N connectors. And even though it starts at 9 kHz, you still cannot put more than 0 volt DC at the input. So unlike other spectrum analyzers where the input starting at 9 kHz means that it has an internal DC block, this one does not allow you to put more than 0 volt DC. It also has an amplitude reference out, which is used for internal alignment, which we can try out if we are able to fix it. This particular series also supports an internal tracking generator as an option. Unfortunately, this one is not equipped with that, so you can see that it's blocked out. If it were possible to have one, then you could have a tracking generator that goes from 9 kHz to 3 GHz. It doesn't cover the full 26.5 GHz range, but then you could do some characterization up to 3 GHz that I've shown you before in, for example, the WeBull spectrum analyzer. There's also Pro Power and external keyboard which are there, and there's a volume knob that you can adjust the volume as a speaker inside for the modulation of FM and AM signals. The screen, of course, right here. I really like these buttons. They're curved and they really feel nice. You can really get some good feedback on them knowing that you press them. Other than that, it's really straightforward front panel. All the typical buttons that go into getting a spectrum analyzer settings are on. We'll take a look at that. And of course, it also has a floppy drive. We'll come back to the 90s, which we have to use to actually operate the firmware. There's also a headphone jack. And there is a tremendous amount of effort that's been put into this instrument to protect it from EMI as well as prevent it from creating EMI. And this series of spectrum analyzers have very low emissions, and everything in here is being taken care of to ensure that happens. For example, even the floppy door is designed to protect it from any EMI. This material that's here does not allow EM fields to go through, so it's really carefully designed. So let's take a look at the back of it and then we'll take it apart. So here's a quick look at the back of the unit. This particular series supports an external battery pack, supposed to be portable. Not that it's very portable, but you can see it even has an external fuse that you can replace 30 amps here. You can put AC power, of course. And he has a bunch
interfaces, for example, the trigger in and out and so on. Here's a 10 megahertz reference in and out. Here's a GPIB parallel port and some tune output, which I have to actually look exactly what this does. There's also a lot of empty slots. This instrument has a lot of options that you can upgrade it with. Unfortunately, it has almost none of those options. It's basically the base unit. Still, a 26.5 gigahertz spectrum analyzer is a really valuable tool to have in the lab. So this one has that bad low, and we're going to find out what that is. Now, before I turn it on and actually show you what's going on, I'm going to go straight ahead and try and upgrade the firmware, because I want to get the latest message that the instrument will generate based on the problem that it is experiencing. Also, I want to make sure that I have the latest firmware, of course, which will be always an advantage. And here's a date code here, April of 01. So this is actually a really old unit. So let's see, let's go ahead and take it apart. And I'll show you a little bit of interesting things in there, and I'll show you why it is such a complication to upgrade the firmware of this unit. So here I have the unit on its face on the table, and I've put two wooden spoons again underneath the edges so that the instrument doesn't sit on its front RF connector. It's very important not to forget that. I did this before with the wavelength meter as well. You gotta be very careful not to put pressure on those connectors. So in order to take the instrument apart, there's just a couple of screws at the top. I've already taken most of them out, and then the back cover should completely slide off, and you should be able to then take the whole thing apart. So taking the screws at the top should hopefully slide off. Oh boy, here we go. There it is, and it's off. Take a look at that. This back piece is made in Canada. There's our contribution to the spectrum analyzer, us Canadians. Wonderful. And then this should come off as well. There we go. Perfect. This all, you can see they've taken care to make sure that this area is blocked so that airflow is well controlled and it doesn't distribute in parts of the unit that will not be helpful. And everything here is, they've got EMI protective strips and so on all around this to make sure that it is well protected. Of course, inside, they don't expose any of the circuitry right away. They have a panel in the front which covers all the sensitive components inside, and on top of it, here there is clear markings of what exactly all the slots are used for. I really like the fact that Agilent typically does this. They make sure that everything is really well labeled. Now, there's a transition in Agilent from, now that our Keysight also, is that there was a transition where they went from component level debugging to module level debugging, and this is an example of that if there's something broken, they don't go ahead and debug the module, they just throw it out and put another one in, which is a little bit annoying because it means that the data sheets and the service manual aren't as detailed. But let me take all the screws off so we can take this panel off also. Alright, here we go. I should be able to take this off completely. There we go, perfect. Again, nice attention to making sure everything fits well and everything is well protected. So now we don't need this anymore. Just put this aside. Here we go. So as you can see, most of the instrument is empty. There is the main processor card here, which is what we will look at. This card over here, I'll show you close up, is the GPIB, and this is a frequency extension board, which has some specific functions related to this particular model. So let's take a closer look at this. So here's a closer look. Let me take the camera off so you can see better. Here we go. So on this side, this is a processor board. Here's a heatsink right here, which is where the main processor is. These are the memories, and this is a complication with regards to upgrading the firmware of this. So it turns out that after a particular revision of the firmware, you need the higher capacity memory. This is, I believe, only 4 meg, but you need 12 meg of flash memory to be able to upgrade. You see the other two ICs on this module are missing, they're not populated. Agilent can sell you this, of course, they can sell you this module, and you also have to upgrade the RAM. But again, it's extremely expensive. We're talking hundreds of dollars for what is essentially 8 meg of flash memory. So I did some research on the internet, and I found these ICs, and I bought 2 more. So we can populate these 2 empty sockets ourselves, and then change the jumpers to tell the instrument that this is the later model with the upgraded memory, and then maybe we can successfully upgrade the firmware. I hope that I can do that. And these are pretty fine pins, so you have to solder this quite carefully. And there's a typical sort of kind of memory at the back, and that's a normal one. This is 16 meg or 8 meg, and it needs the next generation. So I bought one off of eBay. That was cheap. It was about $10. But the ICs I bought
components down here. This long piece looks to be a filter. There is a mechanical attenuator module down here. I am not certain what this is. That looks like it's either a mixer or a Yig oscillator with a board on top of it. And the entire back of the unit is this entire piece. Inside is a main RF processor where the front connector cable actually directly goes in here. So, and it's all labeled. 10 megahertz reference, for example, is labeled here. There's a whole bunch of first IF, second IF, third IF, and a whole bunch of LOs coming in and out. So this is where all the magic essentially happens. You may have to take this apart. But let's go ahead and take the processor board out. I don't really need to take it completely out, but just so I can show you what it looks like, we'll take this out because this is accessible. And then we'll take these, solder it, take a look at it. After that, upgrade the firmware, and then only then we can actually start the repair process. So I'm taking this little piece of plastic that locks all the cards in place. I've unscrewed the little screw, taken the cable off the bottom, and then the main processor board just slides out. Here it is, so we can now take a closer look at it. So here's a closer look at the main processor. Of course, here underneath this heatsink is the main core processor. I'm not sure what it is. This heatsink is
RELI, Reliance Global shares moving higher again now. Romeo Echo Lima India, $7.28.
underneath it. I don't know if it could be made by Intel, but I have to check the data sheet for it. But if you look around, there's a bunch of other things in here.
Shares now up 135% on RELI.
Component that can be used to dynamically change the size of the bus that the processor is talking to. Let's say if it's talking to something that has an 8-bit wide or 16-bit or 32-bit wide memories or other type of components that he wants to talk to, he will automatically select the appropriate size and do the programming. So this is a nice chip to have in between a couple of different types of interfaces with various bus sizes that you can handle and recognize what that size is and handle all the little details behind the scene for you. This one is there's a CPLD, lattice CPLD here. There's a Motorola component here also that is used specifically for, it's a type of a bus controller in a sense, and a good way to put it is that it's a communication controller. It allows the main processor to talk to a whole bunch of different components such as memories, and it has SPI interfaces, it has yours, and serial interfaces, it has an internal RAM, it has a JTAG interface, and a whole bunch of other things that is probably like a glue that connects all the different components here on this together. There's a couple of other interesting ICs. There's up here, there's the main firmware, I believe. There's actually some flash memory directly on this board too, and this flash memory probably stores the very basic instructions in the case that this main DIMM is missing, and some basic instructions which you cannot modify by removing this. And I believe this DIMM therefore only contains the main operating system and nothing more. So we can go ahead and take this off. Actually, before I do that, there's another interesting component here, which is this one. This is a dual crystal and rechargeable battery built into it simultaneously. Now, why they do this? I have actually another one here because this one was dead, and I think I said rechargeable, but it may not actually be. It's just a lithium battery. No, it's not rechargeable. So the reason they do this is because they have the little crystal in here, and next to it they have a battery, and they do that so that you can plug this in afterwards onto the board, so that the battery and the crystal aren't exposed to the reflow heat when this board is being manufactured, so that you don't have to have these components on the board, and then you can simultaneously snap them in there afterwards without them ever being exposed to the heat. I thought this is pretty interesting, and you can see it's filled with epoxy, so you can't take it apart. This one is dead. I knew this is dead because the instrument couldn't hold time and date anymore, so that's how I knew that the battery was dead. So I just took it out, bought another one, and these are still available, and I just replaced it. So that should probably fix that problem. So if we go ahead and take these guys off, you can see here's some basic memory. If you remember these from a long time ago, that all PCs used to have these. This I believe is either 8 or 16 meg, and I bought the next version of this, which is twice the capacity, which is required for the next firmware. And of course, the main problem we are having right now with the firmware is the fact that this guy is not fully populated. So I have 2 more of these. Let's go ahead and solder these. I won't show you the whole process. I'll just show you a little bit of what I'm going to try and do. Put the surface mount components on there, solder it, reset it, and then install the firmware, which is over many floppy disks. I get
again, I won't bore you with those details. We'll just quickly show you the first steps, and then we'll see what happens. Alright, here we are. So we're ready for some soldering. So I've put the module here, and I'm looking at it using the Dyno Light H series microscope that I reviewed recently. You can see some of the fine pins here that are magnified. So I ordered the components, as I said, the 2 flash chips from Quest Components, and they packaged it really nicely, and actually in a moisture sensitive container. Even though there's only two ICs in there, they've done a pretty good job of packaging them. They have a large stock, so I'll probably go back to them again in the future. So here we go. So you see that, again, they've taken quite a bit of care. There's a silica gel to absorb the moisture, and everything is nicely packaged. So let me open this and see what it looks like. Here we are. So you can see the 2 ICs in there, nicely packaged. Again, just to remind you, the moisture sensitive packaging is intended to make sure that there is no moisture in the plastic of the package, so that at the time when you do reflow, they don't pop like popcorn. It's very important for components that are going to be wave soldered or reflowed, that they have been in a moisture sensitive container for quite some time, making sure all the moisture is out of the package themselves. Otherwise they'll pop and of course they'll become useless. So I'm going to go ahead and just do a rough placement of this IC on one of these guys, just so we can see what it looks like. Let's say this one, just to get a quick idea. Here we go. So, you know, it should be possible to solder this by hand. I'm not going to try and put all the little detail here on camera, but we can get started. That's a reasonably good alignment. You have to align the other side as well. And then once I'm satisfied with it, I put some thermal tape on it, and I'll go ahead and solder. And you can see this side is not aligned perfectly yet, so I have to kind of do it a couple of times back and forth to make sure everything is solid. So yeah, let me do that again. I won't bore you with the details of all of this. You've seen soldering.
GOED 1847 Goedeker announcing share buyback program, Golf Oscar Echo Delta. GOED. RIGL, fostamatinib, meets primary endpoint in phase 3 trial in Japan for treatment of chronic immune thrombocytopenia. Romeo on India Golf Lima, RIGL.
I just have to remember this has already been wave soldered, so those pads.
BA Boeing announcing UPS purchase of 19767 freighters. That's Bravo Alpha and Uniform Papa Sandy. BA and UPS.
Just going away from the pins. Quickly over each pin.
NLSN, DIS, Nielsen 1 Alpha launches with Disney and Magna, marking significant milestone towards a single cross-platform measurement solution. That's November Lima Sandy November and Delta India Sandy, NLSN and DIS. WULF TeraWolf purchases 15,000 S19X Pro miners from Bitmain. That's Whiskey Uniform Lima Foxtrot, WULF. BK Technology announcing share buyback program. Bravo Kilo Tango India. BKTI.
It's nice and smooth. Yeah, look at that. That's not so bad. You can see all the pins are hopefully soldered.
SURG, Surge Pay. Blockchain update enables Bitcoin purchases at corner stores. That's Sandy Uniform Romeo Golf. SURG. BKKT, Manasquan Bank selects Bakkt to offer retail clients access to cryptocurrency. That's Bravo Kilo Kilo Tango. BKKT. NTRB, Nutriband, initiates plans to offer topical lotion, contract manufacturing services. That's November Tango Romeo Bravo, NTRB.
Fine point tweezers, and I just run them over very gently run them over the individual pins and make sure there's no movement, meaning that the pins have been soldered down, and I can do that very easily. I verified that they're all fine, so there's no problem. I am also going to show you my new tweezer set. Check it out. Just don't ask how much I paid for all of these, but these are all WeBull German EST safe tweezers. I made a little base for it, and so that's why
HLBZ, Hellbiz Live, will broadcast Globe Soccer Awards live in USA, Italy, and around the world. That's Hotel Lima Bravo Zulu, HLBZ.
Let's go ahead and put this back. I've always forgotten what we were doing. We're trying to repair the unit, so let's put this back, see if we can upgrade the firmware, and then we'll see the error message that the instrument's generated. And here we are. This is the module that I installed, and I put the chips on, and here's the old RAM. You can see on the other side, nothing is
EPAC and EnterPack tool, reporting 5 cents.
I'm going to put these guys back in here, and then
The estimate 21 cents. Echo Papa Alpha Charlie, EPAC.
you will erase the entire flash, and then there will be nothing there, and you cannot use it until you update the flash. So let's hope that step works.
Reiterates full year guidance.
Walk it even further. Well, here we are. This was a success. I put all the chips back together, and I did the jumpers to tell the spectrum analyzer that the higher order memory has been installed, and I upgrade the
That's Echo Papa Alpha Charlie, EPAC.
9 CDs. I wish there were 9 CDs. There were 9 floppy disks, and I installed them all. It took a very long time, and I'll have you know I only tried 5 times. And here we are. It's installed, and this is the error that it's giving. It says that the system alignment is required, and it says LO unlock. Now I've done the system alignment before, and I don't believe the system alignment itself actually failed. The LO unlock obviously refers to some unlock synthesizer inside the unit. But believe it or not, this LO unlock message actually doesn't show up in the service manual very clearly. Whenever they talk about LO unlock, they only talk about the tracking generator, which of course this unit doesn't even have. So we have to find a way to debug this differently. First, let me show you the service manual because it's really a well-put document, really put together really well. So let's take a look at that, and then we'll do some debugging and see where we can get. So here's the service manual. I just want to quickly show you how nice this document is. So it comes with a whole bunch of CDs and some computer-aided training material for the technicians who would normally use this. And there's also the soft copy of it. The soft copy of just the service manual is actually available on Keysight's website. I don't think it was there before, but somehow it's there now. But anyhow, this is a printed copy, which is always nice to have. But this comes with something that I couldn't find online, which is the ESA schematics. So the entire schematic down to every component level of the entire spectrum analyzer is on this CD. So really you can essentially, without you don't have the firmware, but you can replicate it as far as hardware is concerned. So this might be very useful if you have to debug some complex circuitry, which this thing has plenty of. But aside from that, the document itself is really, really nice. It has multiple sections about exactly what to debug. This thing is many pages, so I'm not going to read all of it obviously, but it has a troubleshooting section for the RF section. But like I said, it doesn't have the LO unlock message the way I was hoping. But one thing it has, which I really like, are block diagrams, and it has block diagrams for all different models. And this is the one we have is E4407, which is, I believe, this one. Take a look at this. It unfolds out. Look at that. Isn't that some technology pornography right there? So it has the complete block diagram from the beginning to the end.
ZIXI, Zix Corporation, resumed trading. Zulu India, X-Ray India.
We can do a couple of quick tests, and I want to go through a bit of this block diagram to tell you how the instrument actually works. So let's go over the general principle of operation of the instrument. As you can imagine, this is fairly complex, and the block diagram is very big. But I can go over and tell you kind
mixer here for the second converter, and there's an entire assembly here where the third converter and the reference generator is inside. So what does all of this mean? So this instrument actually does this very complex super heterodyne architecture, meaning that it does multiple conversions before it gets to the final desired IF frequency. Now, there is no direct conversion architecture in the spectrum analyzer, and that makes sense because direct conversion has, it has some drawbacks which they want to avoid, DC offsets and spurs and unwanted tones and so on. Anyhow, in order for them to be able to filter something very well and have the resolution bandwidths as they do, they reach a final IF frequency of 21.4 megahertz. So any signal that you put into the spectrum analyzer as it sweeps ultimately ends up in a very narrow window around 21.4 megahertz. So that's the third IF component. So how does it do that? Well, it actually depends on the frequency range. So in this instrument, if the frequency is below 3 gigahertz, it first up converts it to 3.9 gigahertz, then down converts it back to 312.4 megahertz, before finally down converting it again to a final IF of 21.4 megahertz. If the signal is above 3 gigahertz, then it forgoes the first conversion and it directly down converts the signal to 312.4 megahertz, which then goes into a second final converter down to 21.4. So again, you can take a look at that, but let's follow the signal. It might be easier than me describing it. So here's the front end portion, and the front end portion has electronic attenuator option or a DC block option, which you can bypass with switches. I don't have any of those installed on this unit, but this shows all the possible options. So you can see the signal it says 2 ohm, 50 ohm inputs, but of course this is just one of them. It's just showing option UKB and some other option for a different unit. This is actually showing it for E4407, and these are for the different options for the same unit. So anyhow, I don't have any of these, and you can see the signal comes here. Now in this first YIG tuned filter mixer, which is this block, which of course YIG is YIG oscillator. We saw that you saw me using some YIG oscillator in a different video, and you can see that there's a pin diode switch here. I believe it could be a mechanical switch. I can't tell from here. That it can select two paths. One of those paths is a pass through directly, whereas the other path has a down converter in there. So this is where the selection, whether the signal is above or below 3 gigahertz is done. So as the spectrum analyzer sweeps up until 3 gigahertz, this path is selected, and as soon as you hit above 3 gigahertz, then this path is selected. And let's follow that up. So let's say the signal is below 3 gigahertz. What happens? It comes over here, and look at that. There is a 3.1 gigahertz low pass filter. Why? Because they want to make sure that no signal above 3.1 gigahertz enters the first converter, because it's not supposed to be converted of that frequency. Remember that the signal at the input of the spectrum analyzer can be broadband. It can be covering from 9 kilohertz to 26.5 gigahertz. So you better filter it really well, and these are microwave filters, so they have a really sharp roll-off to make sure that no signal above 3.1 gigahertz is present in the first converter, because it's supposed to be up converted down to 3.9. So they take that signal and they pass it through, and there's some AC block and so on, some options to bypass it. Not important. There's some protection circuitry here, and there's some selection circuitry. We'll talk about that. That's not important right now. We'll actually have to come back to this. And he goes forward, and here's the first mixer. This first mixer is the mixer that up converts to 3.9 to 1.4 gigahertz for the first converter if the signal is below 3 gig. And you can see here's a band pass filter at 3.9124 gigahertz, which blocks that, and it has a 700 megahertz bandwidth. So the mixer has a 700 megahertz conversion bandwidth that it blocks everything else outside of that region, really cleaning it up. Again, this is one of the reasons why a super heterodyne architecture is chosen, to make sure that anything that you don't want is cleared up. Then he goes into some first IF amplifier, blah blah blah, not so important. And then from there he goes into the second converter. Now you can let's go back here. Now you can convert the signal down to 321.4 megahertz as a second IF, as I mentioned. And you can see here's a 3.9, again another bandpass filter. I'm actually curious about why they're doing this here. This is an interesting block here. This is a band reject 5.5 gigahertz rejecting signal, maybe because there's some frequency around that that's here. It's interesting. Anyhow, let's move on. So here there's a 3.9 to 1.4 gigahertz bandpass filter, again allowing the signal to go through. Here's your second mixer, and the second mixer then has, and its output can be selected to come from a second path, and we'll talk about that second path. So here's the second converter, and the signal comes out as 321.4 megahertz IF, and we can follow that line through here, and it goes all the way around here and finally enters what is called the third converter, as I mentioned. mentioned, and then it goes back through some filters and some gain stages, some more filters, and here's an active mixer right here, and they point out that this is an active mixer, maybe the other ones are passive, and here's just some attenuation adjust, and here's our final 21.4 megahertz bandpass filter, which will be your third IF, and the signal then can go outside, and this goes to the sampler. At this point, the signal of 21.4 megahertz bandpass filter can be digitized with a high resolution, perhaps delta sigma analog to digital converter, in order to get your digital signal finally. That's your detector ultimately. Now this is a digital detector, this instrument, because it can do demodulation around a particular bandwidth. But anyhow, that would be your IF signal. So that's the first path. So the first path is any signal less than 3 gigahertz goes through, gets filtered, up converted to 3.9 gigahertz, filtered, down converted to 312 megahertz, filtered once again, going through to the third converter, filtered, mixed down to 21.4, once again filtered, and down to sampler. That's signal below 3 gigahertz. What about signal above 3 gigahertz? As soon as the sweep goes above that, then this path is selected. And yet another mixer is here, and this mixer actually down converts the signal directly to the 312.4 megahertz. So it now becomes a two-stage conversion, not a three-stage conversion. And then from here you can see, again, there's another mixer, and the LO of this mixer is provided by this LO amplifier. So the signal, if I were to follow that, it goes through, and here's an interesting thing, is that the 312.4 megahertz IF signal passes through the same module that generates the LO for that, and that's common because they're related. There's the IF and LO of the same signal. So then it comes back down here, some selector switch, and some unoccupied connector here, selects some gain, nothing fancy. Signal goes out here, enters the second converter, but doesn't go through the mixer anymore because it's already down converted. But now here's an IF switch, so it's filtered again at the bandwidth that it's interested in, is a high pass filter, and it passes it through here, 312 megahertz, which then comes back down and goes similarly to the third converter. So the third converter is common between both bands, the upper and the lower band. And this might be interesting for us as a debugging tool, because it seems to me that because the instrument treats signals below 3 gigahertz differently than the signals above 3 gigahertz, we can find out where the LO is failing. So the instrument is showing me an LO unlock. Well, where the heck do we start with that? Well, the LO unlock obviously has to do with one of the mixer LOs during one of the down conversion process. So where would I look? Well, if you look at this piece here, so there is a really large assembly, this A8, A1 assembly here. By the way, I'm just figuring these out as I'm speaking, so I hope that if I'm making any mistakes, let me know. So there is the A8, A1 assembly right here, and it constitutes of two parts. There is the A8, A1, A2 front end and a low board, and there is the A8, A1, A1. Jesus, name conventions. So these two boards are under the same shield, it seems, and all the other pieces are separate. So in here, there is a reference generator. I believe this would be a good part to take a look at, because first of all, this is the part that has the voltage controlled crystal oscillator in there, which there's also an option for. Here it is. Actually, it's interesting. Here's your time base. So the time base comes in. There's a 10 megahertz VCXO and a 10 megahertz OCXO, an oven controlled crystal oscillator, which is option AY5, which I don't have. So you can actually have this one populated. And then there's a three-way select switch. So if you put a 10 megahertz input, you can actually bypass these crystals. So if these crystals are bad, we could try bypassing it. But anyhow, easier than that would be to go ahead and follow the signal. So here's a 100 megahertz VCXO as part of some kind of a PLL loop, it seems. And then it comes down here. There's the 50 megahertz AGC, which is for amplitude adjustment. Here's another interesting thing again, is that the 50 megahertz reference amplitude that's in the front of the instrument is actually generated from the same signals that generate all the other LO signals. So we have multiple points of checking to see if there is failure. And here we go, look at it, there's a 10 megahertz output. Look at that. The 10 megahertz output is a synthesized version of the 10 megahertz crystal. So that's interesting, because this means that the 10 megahertz crystal is actually not directly connected to the 10 megahertz output, which makes sense, of course, because that's just a reference. This 10 megahertz output is the synthesized version of the internal PLL. So if the 10 megahertz output is present, it means that at least this part of the circuit is working, and perhaps the LO unlock comes from elsewhere. So let's look at some of the other. Okay, so here's a tripler. Here we go. Here's a tripler right here. So that the 100 megahertz signal gets tripled, becomes 300 megahertz. Look at that, there's a bandpass filter. This bandpass filter is to take out all the tones, all the spurs that are generated, harmonics that are generated as a result of tripling your signal. Again, you can afford to do this on something like here because these are all microwave components. You can't really do these things very easily on ASICs. But then you triple this, so then you have 300 megahertz, and it's broken up into two, and that 300 megahertz signal is the LO signal of the third converter. So here's one point where failure could have happened without the LO. I just don't know where the LO is detected. Maybe this doesn't have enough detail to tell me where the LO unlock signal is detected. It could be one of these digital lines. Again, this is just a rough block diagram, but anyhow, we have a really good parts to try out now. So the triple 100 megahertz signal gets doubled again, becomes 600, and that 600 megahertz signal goes into two different LO drivers. There we go. Now we're onto something. And these LO drivers then drive different mixers, the second converter mixer and the first converter mixer. So we have a lot of things to look at. So first thing to look at is to look and see if the 10 megahertz output is there. If the 10 megahertz output is there, at least this portion of the synthesizer is working. Then the next thing to look at is to see if this 50 megahertz signal is present, because this 50 megahertz signal is taken a little bit after, although if this is present, I'm assuming this one will be present as well. But let's follow that. So the 50 megahertz calibration signal comes out of here, connected J1 on the A8, A1 assembly, then goes up, goes through here, and goes through here. Here we go. Look at this. So let's see what is going on. So the 50 megahertz signal that is used for reference actually has an internal pin diode switch that allows the instrument to internally connect it to the RF input for alignment. So it switches it over to the RF input. You can see if this signal is switched to this side, then it goes back here and it goes to the front of the instrument, so you can pick it up from the front, or it is switched this way down and forward through a 30 dB attenuator directly into the RF path. So that's one other place you can take a look at it. So we can monitor it here and see if it is there. If it is, so the first two things to try is the amplitude reference available, and then we check to see if the 10 megahertz signal is available. And this should give us at least a starting point to go on. So let's try what I said. By the way, you may be asking, why don't I just connect an RF signal and see what happens? Of course I've done that. I did it a long time ago. I didn't mention if you connect an RF signal here, nothing shows up there. So that is not, and it's not because there's connection problems or this is not connected and that's why the signal is not getting in. No, that's not true. It fails the RF, so if I take the amplitude reference and connect it back to the input, it fails that alignment. So it's more than just that. And I also looked at the connector, it made sure it was perfectly fine. So anyhow, I've already done that. That's why I'm not doing it again. But then, just to let you know. So here we go. I've turned this guy on, let it warm up. I've turned on my HP 53131A, which is the universal counter, where we upgraded to the 3 gigahertz option in a different video. So here we go. I've connected VNC. If everything's warmed up, let me hook it up to the 10 megahertz output if I can find it. There we go. Let's see now. Is this the right connector? Why can't I get this? 1 second. And voila. There we go. It's not so bad. Actually, I'm kind of upset that it works because I thought that would be an easy thing to figure out. But anyhow, here it is. 10.00000, so it's 4.5 hertz off. But again, that could be because my counter is off, and a lot of you had offered to give me a rubidium oscillator to calibrate it. I'm sorry I haven't gotten back to you. I've been very busy, but yeah, I'll definitely take you up on that offer, and we can calibrate that. But anyhow, that works. So that is not the problem. It does have the 10 megahertz reference out, which means that portion of the synthesizer at least is functioning. So I was going to measure the 50 megahertz, but I realized that you guys must be by now bored out of your mind. Again, please leave me a comment if my technical explanations are too long. I thought it would be useful to go through the block diagram to really understand. I still have to go through more sections of that. So again, this would be a good time to let me know if you think that I talk about it too much, just so that you can see the inside of it and do something different. I took all these screws out. There's just so many of them. I took them all out so we can see what's underneath this. Remember, this is the A8 assembly where the LO generation is should be inside this. I don't know which one it is going to be, which module, but anyhow, I've taken all the screws out, and let's take this apart. And again, I'm figuring these things out on the spot, so hopefully if you catch me making a mistake, let me know. You see this one more screw left up here. I gotta be careful with this thing so that I don't drop it. I don't know how heavy it is. There we go, is the last screw. And oh, there we go. Oh, look at that. That is some neatly laid out section board. Here's the back of this. We've seen something like this before. This is an RF shield. The bottom cover is labeled here. You can see different pieces here. These are RF absorbers, most likely on the parts of the circuit that have high enough frequency where the radiation can happen and can bounce back and come back. That's at least what I think they are. We can see. Let me take a quick look. Yeah, I think I'm right. So anyhow, you've seen this before. I showed you this in another module before. So again, section, everything covered with this foam material, which is conductive and really shields it. You can see the traces here, which are all ground, of course, which line up with these. There we go. So let's see now. So let's figure some of this out together. And let's see, where do we start? Let me see if I recognize anything here. So, okay, let's start here. This looks like some kind of, this is the connector right here, is the connector, which is, there's a ribbon cable up here. I don't know if you can see it. There's a ribbon cable up here which goes deeper inside the instrument. So this is where I believe all the power is coming from. And there's of course some easy hints to see that. You can see all the big caps are here, inductors are here. These are filters, RF filters, which basically prevent maybe DC-DC converter noises to come into this analog RF section. So this is some digital stuff. There's an Altera FPGA or CPLD here. Bunch of 74H series logic, maybe AND gates. And actually it's really nicely labeled. I'm looking at this. You can see all the power supply numbers are written here. There is LO-ALC on level. So if the LO were to be on level, there's an LED here, but I assume either turns off or on. And so this is not the error we're getting, by the way. LO on level is a different error. We're getting LO on lock. There's a bunch of circuitry here from a connector, which we can check and see what that is, where that's coming from. This could be, for example, the 50 megahertz coming in or something. And there's a bunch of test points labeled here. What else is interesting that I can show you? Okay, here we go. I recognize some more stuff. This is I believe is the EEG oscillator. I recognize that from just the circular connector. I've used a EEG oscillator in the past. You can see there are 3 screws that's holding it in place, and here's the RF output of the EEG oscillator. We can see with a sender RF connector and the ground around it. So that signal, again, I know this, I can tell this because of the not just the shape, but then it goes into something called an LO pin modulator. This, I believe, would be some kind of an attenuator to modulate the power from the LO, perhaps, or turn it on and off or so. And then you can see the signal path, no pun intended, going through here. Here's an LO amplifier. This is really cool, actually. You cannot see. Here you go. This is a cool structure. We can talk about this. So here's the LO coming in. It actually says LO amp 1, LO amp 2, 3, 4, 5, and 6. So LO comes in amplified by an RF transistor here, amplified again, and it goes into a power splitter, a microwave power splitter. This is a common broadbanding technique. It's probably a Wilkinson, 2-stage Wilkinson, or this is a technique used to typically broaden the bandwidth of a Wilkinson. I've done this before. Then the signal splits into 2, so it's just a power splitter essentially. Goes into another 2-stage amplifier, another 2-stage amplifier, and then combined together. This is a common technique. This is not a balanced amplifier, by the way. This is just 2 parallel amplifiers with the power connected together. By doing so, you can sum the power of these 2 amplifiers and get higher output power together by combining them. And so you would get ideally you would get 3 dB more power by combining the power back together. Of course, these passives have loss, these splitters and combiners have loss, so you won't get 3 dB, you get a little bit less. But this is a common technique. We do this on ASICs all the time too. It's not limited to PCBs. And there is a LO. Oh, there's an LO detector. So LO level detector. So this is a detector circuit which will tell us the instrument how much LO power is coming out of here, and you can see it's close to the LO on level LED up here. Actually, I'm explaining something that's not even screen. I apologize. Let me see. There we go. Sorry about that. So here, this
this is a low level detector right here, and then above it the yellow on level. So if the level of the yellow is detected to be too low, the signal is sent up here and the LED will come on. Well, let's see what else. Here we go. Here's our mixer. There it is. Right here. This is our mixer. So this would be the mixer we saw for signals below 3 gigahertz. This is what up converts it to 3.9 gigahertz. And then you can see, remember I told you there was a 5.5 gigahertz band reject filter. That's right here. You can see it. These stubs on this line are tuned to reject 5.5 gigahertz. Again, I can talk about microwave circuits and PCBs and so on some other time. If somebody wants to send me a network analyzer, I can do a tutorial on that. But anyhow, so you can see there's some bandpass filter somewhere else that I guess there's an arrow here that says maybe it's on the other side of the board, and then it goes through here, some amplifier here, the 5.5 gigahertz reject filter, and goes out and goes into the other assembly at the bottom through this connector. So what else? So then we can see, so we found the yellow path. Zoom out in here. So we found our Yiga oscillator, we found the LO amplitude modulator, we found the LO path, LO detector, the mixer, the low pass filter. This must be some kind of an input switching mechanism, because I believe that this signal must be coming from somewhere that is going. Okay, so this signal must be coming from that front end Yiga oscillator, a mixer, because it's coming back onto this converter. So this must be coming from there, which means this is where the input signal is processed. Makes sense because here's the RF input of our mixer. So that completely makes sense. So here's the LO path, here's the IF path going back out. Remember, this is an up convert mixer, not a down convert mixer. This converts everything to 3.9 gigahertz. So this is actually a really good board for us to have access to. I'm glad that it's not the other way around. The other board is the board where we measured the 10 megahertz reference. That's not on this board, that's on the other assembly. That's actually behind this. So this is great that we got this one as opposed to the other one, because the other one probably works because we have the 10 megahertz coming out. This 10 megahertz is not connected to this board. It looks like it's connected, but it's actually on the other side. There's another shield, and then there's a whole other
SSNC announcing strategic investment in combination of shareholder services of Quantity and AST. That's Sandy November Charlie.
3.912 gigahertz going out up converted. This signal here, I am not sure what that is.
CBAT, Seaback Energy, enters into agreement with Zappa R&D China for developing customized battery pack. That's Charlie Bravo Alpha Tango, CBAT.
Okay, so I know what this is. So this section must be the section that drives the Yiga oscillator. So here's some of the components of the PLL must be here. The PLL for the Yiga oscillator, which I suspect is what the problem is, because the other PLL seems to be working. And so that would be this guy, obviously, this power transistor here looks to be, I think, a power transistor on the other side. This probably drives the Yiga oscillator. So this drives the tuning coil.
DM Desktop Metal and Korea Institute of Industrial Technology partnered to accelerate the adoption of metal binder jetting for SMEs in South Korea. That's Delta Michael DM.
I believe this signal must be coming from the LO output. So remember, this is a PLL. The PLL has to divide down the signal and then compare it with the signal that's coming from the other synthesizer, which is behind this one. I believe this portion of the circuit does the conversion. Yeah, you can see there it is. Okay, it makes sense. 684 megahertz signal converted to 21.4 megahertz. That's the alignment signal. So that's generated here. A bunch of other circuitry here. OP, these are op amps. We have to look at the schematic for what the heck this is. No idea what that does. Here we go. Here's a 6 meg. Okay, that 9 makes more sense.
NOW ServiceNow awarded 5-year contract with the Internal Revenue Service. That's November Oscar Whiskey. NOW. SIDU, Sidus Space, and KSAT joined forces to enable end-to-end mission operation solutions to support LizzieSat constellation of 100 satellites. That's Sandy India Delta Uniform, SIDU.
And we saw on the block diagram here. I have no idea what these two LEDs are, but there's two more diagnostic LEDs here. Interesting, they're just called DS1 and DS2. We have to look at the schematic. So now we have an idea. So Yig driver,
DASH, DoorDash, and Southern and Southeastern grocers partner for on-demand grocery delivery.
What that is yet exactly. Some other op-amp circuitry here. The divider for the reference.
That's Delta Alpha Sandy Hotel, DASH.
Here. No idea what that is. Well, looks good. Well, what else can we do except to let's take. I know you don't look at the block diagram, but let me take another quick look at the block diagram with you and see what is worth actually probing on this. So here's the block diagram one more time. Please don't forget to leave me a comment and let me know if this is I'm going into too much technical detail. It's very important for me to keep you guys interested throughout the video, and I think it's nice to learn these. So again,
KPTI, Carrier Farm, and Manarini Group enter into exclusive license agreement to commercialize Nexpovio in Europe and other key global territories. That's news that was out earlier. KPTI.
It goes back. Remember that 128 to 129 divider I just mentioned? So the 600 megahertz goes back in here and is used as a reference for the gig-based PLL. So there's a couple of places to measure. We want to measure, is this output present? Do we have 600 megahertz divided by 128, 129, blah, blah, blah? Is that there? If that is there, this entire board at the bottom works. Luckily, we are looking at this board and not this board. That's why I was happy that I found that this is the board that's exposed at the back, because this one most likely works. If there is no 600 megahertz reference, the divider must be bad, or some doubler or quadrupler would be bad. We should have to get to this. But if the divider signal is there, that means this PLL is bad. And let's look at how this PLL works. This PLL uses the 600 megahertz from here by dividing it out as a reference. There is something called the pre-tune, tune offset, delay compensation, blah, 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 which is part of the feedback loop of the YIG oscillator. Here's the YIG oscillator, YIG tune oscillator. There's the main call, there you go, there's the main call driver that I was talking about. And then here's the amplifier, the LO amplifier, and there's a bunch of coupler in here. These are microwave couplers, so they use the LO for multiple purposes. Makes sense. Here's the LO out that goes all the way back to the other side. This YIG oscillator, by the way, and there's something else I have to mention. So they take the power out of the YIG oscillator, come back here, they divide it by 4, divided by 2 and 4 again, they send it to the fractional end divider, the fractional end divider then goes back, and there must be a charge pump, which is this thing, and an integrator, here we go, that then drives your YIG oscillator. So here's your YIG oscillator PLL, and this is a divider in the feedback path, and here's the reference path. So it makes actually it's very clear exactly how this thing works now. So we can now go ahead and measure this guy and measure stuff in the loop and see it works. Now, you may be asking yourself something I didn't explain. What do you think the frequency of this YIG oscillator is? Well, it doesn't say here. I suspect that the YIG oscillator probably is maybe between 3 and 8 gigahertz, maybe, or maybe 2 to 6 gigahertz or so. Because then how can a YIG oscillator that only has 2 to 4 gigahertz down convert something that's 27.5 gigahertz? How can this guy do 27.5 gigahertz down conversion? But the trick is here, which I didn't describe. Look at this mixer. This is not an ordinary mixer. This is a subharmonic mixer, meaning that it is able to give you harmonic down conversion as opposed to just a fundamental down conversion. So by putting an LO in, there's actually a switch here which picks odd and even output harmonics. So if you are measuring at 4 gigahertz, a 4 gigahertz LO will be sufficient to bring you down to DC, although this doesn't do direct conversion homodyne. But anyhow, let's put it aside. A 4 gigahertz LO would be enough to bring you down. But what if you have a 27 gigahertz signal? You can still use a very low frequency like 4 gigahertz or so, but then you would be using the harmonic down conversion. And there are switches here to choose the odd and even order harmonics.
RAD, Rite Aid shares popping here, $13, $13.20 now, following their earnings report. That's Romeo Alpha Delta, RAD.
To get all the subharmonic mixing all the way up to 26.5. Well, then you might ask yourself, well, that sounds easy. Why doesn't everybody do this? Well, the reason is because subharmonic down conversion and up conversion is extremely lossy. So the conversion gain of this mixer degrades significantly as you try down convert it with other harmonics.
and as a result, the noise figure of the mixer goes up. And as a result of that, the dynamic range of the instrument degrades. This is why at 26.5 gigahertz, this spectrum analyzer does not have the same dynamic range, does not have the same noise floor as it does at 4 gigahertz. Aside from the other sources of noise that go up with frequency, the subharmonic mixing is highly responsible for that. So anyhow, there's that, and some other mixing knowledge there for you. But so now we have some ideas. Let's measure some basic power supply voltages, make sure they're there, and then measure these voltages. Take a look at the schematic, and we may be able to fix it, although, well, you know, it's pretty complicated. So let's see what happens.
MNSO, Miniso, marking its 5,000th store globally. Mike and November Sandy Oscar.
I don't even remember where the on button was. I think it's this way. Let me see if I can reach it. Oh, wait a second. There it is. I just turned it on. Ooh, look at that. Some LEDs are lit. Huh, interesting. The LO on level LED is lit and PS2 is lit, but it's still booting. So let's wait and see what happens. Oh, I just heard some clicking. Oh, this one went off. That's good. That one's still on. I think it's still booting. I remember it took maybe 10 or 15 seconds before it started sweeping, so... Oh, okay, here we go. I think it started. Look at that. What the heck is that?
RAD, Rite Aid, on their call now says expects continued demand for
Which makes sense because the instrument is not reporting LO on level. Thank goodness, because otherwise...
COVID-19 vaccine booster shots in Q4, but at levels below those seen in Q3. That's Romeo Alpha Delta RAD.
So there it is. I'm going to use the Fluke 289. I've connected the negative terminal of the Fluke to the body and just hang it up on the side here, right here, and maybe you can see. So let's measure some voltages, and you may not be able to read the cell screen, but I'll tell you what it's supposed to be, and then you can let's do this and see what happens. So there we go. I think you can see everything.
MA and MCD, MasterCard, and McDonald's announced agreement for MasterCard to acquire McDonald's state-of-the-art personalization platform and decision engine company, Dynamic Yield. That's Michael Alpha and Michael Charlie Delta.
Is 14.9. That's okay. Plus 5 digital. It's 4.9, a little bit higher. Minus 5 is minus 4.8. So the plus and minus 5 is a little bit lower.
Terms not disclosed on that deal. That's MA and MCD.
Perfect. Let's go and measure everything that says has a voltage return on it, just for the sake of argument. Here's something that, here in the mixer, it says IF bias. Doesn't say how much it should be, but let's see if there is IF bias. IF bias is minus 3.8. Is that good? I don't know. We don't seem to have an IF problem anyway, but let's measure this. Hello bias, minus 4.7. At least there's something there. What else is there voltage written on it? Here's plus 5 volts. That's good. Here's plus 6.5 HPT, which I remember I said that I believe this part is the LO divider, so this should be important. 6? Ah, she says 6.5, but it's 6. Could be. Now I'm a little bit suspicious. Maybe the divider is not working because it's only getting 6.5. 6 volts is supposed to 6.5. Well, we should have enough margin. Let's see. This guy says plus 5. Plus 5. Parent output. No idea what that is. Here's the VDD of the fractional end divider. Could this be the problem? Damn it. No, 4.8 volts. That's still okay. Other voltages, there's a 6.5 here before the filter. Interesting, they put additional filtering here before the divider to prevent noise being injected into the divider. Any noise you inject into the divider path of the PLL would actually show up directly at the output of the PLL. You can't filter that out. So important to make sure it's filtered out. That's what they're doing here. Let me measure that guy. 6 volts. So actually the 6 volts, 6.5 volts for the HPD here, so it says it must be coming from elsewhere. But it's okay so far. Any other voltage I can measure?
ZNGA, Zynga, and Forte announced strategic partnership to drive rapid development, create more economic opportunities for players in blockchain gaming. That's Zulu November Golf Alpha. ZNGA.
Does it follow
Shares of
the
Zynga
section?
getting a pop here. $6.62, up 15 cents.
Just covering this as we go along. So if this is a fractional divider, as we saw on the block diagram, and it says a reference here, FLO here, then this must be the phase detector, because it is comparing the reference to the FL. What are these? These are HT. Oh yeah, these are logic. So this must be this is actually, what is that? I have to look this up. HT74. So 74 series logic. So this actually makes sense because a bang bang phase detector, although this would not be a bang bang phase detector most likely. But anyhow, let's just say a typical phase detector has flip flops and an AND gate. So this actually could be that, which then means this must be some kind of an error signal. I have no idea what that represents. Something wrong with the LO, which of course is the problem. So maybe that's actually a good place to measure. We can directly measure that. Then we don't have to try and measure the 600 megahertz signal. Remember I said the 600 megahertz signal gets divided as 128 and 129 to become the reference of the PLL. So here's the reference of the PLL. So this is the feedback reference. If this signal works, then the other board is most likely completely good, and the problem is definitely on this board. Well, how am I going to measure that? There is something else. This board
SPNT, Serious Point, announcing strategic investment in Canadian digital life insurer Policy Me. That's Sandy Papa November Tango, SPNT.
see what the LO frequency, the LO signal actually is. Then we can use the LO signal and then look at all the other signals. So the first step would be to
Terms not disclosed on that deal.
look at the signal up here and see what we get. For that, the best instrument to use, I think, would be the MDO,
SPNT.
which I've connected up already and put the probes down here ready.
HLTH, first of its kind Q Health partnership with Air Canada, provides US-based customers with special access to most accurate COVID-19 self-test. That's Hotel Lima Tango Hotel.
Cannot get better than that.
HLTH.
An analog correlated to RF signal.
GE Digital to acquire Opus One Solutions to advance energy transition. That's Golf Echo.
So I'm gonna figure out which of these
GE.
I think I'm gonna have to turn this around so we can actually see the screen, and then we'll take some more measurements. So there, I turned it on a corner, and so the screen is now here.
GNUS, Genius Brands Cartoon Channel, launching on JetBlue, Golf November Uniform Sandy, Juliet Bravo Lima Uniform, GNUS and JBLU.
Tight, but okay, these tight. Yeah, these seem tight. Okay, that should be enough though. And anyhow, I actually just
MTTR Matterport
not a very good practice. Don't do this.
announcing new experiences for retailers and customers using capture services on demand.
Output, and the swing can actually become really large. It doesn't have
That's Michael Tango Tango Romeo.
damage it. Anyhow, bad practice. Don't do that. Shouldn't have done it myself, but anyhow.
MTTR.
We want to see what's going on. So here we go. There's our LO signal. Connected it to some SMA cable. Let me clean this up a bit. Probes out. Alright, here are my probes. This guy's missing the tip. I don't know what happened to it. So here, so I've connected it. So I wonder what's going on. So I have nothing configured here. So let me turn channel 1 off completely. Let me turn the RF channel on. Here's the RF channel. And well,
TYL, Tyler Technologies, renews 5-year contract for digital government and payment solutions in Oklahoma. That's Tango Yankee Lima.
gigahertz because it does up conversion 3.9.
TYL.
Let's get rid of, let's change the frequency band. So I'm going to go frequency span. I'm going to start from 0. I'm going to start from, start from 0 is fine. Stop at 6 gig. 6 gigahertz. Ah, look at that. That is cool. That is the sweeping. So it's sweeping back and forth really rapidly because the instrument is sweeping back and forth. So we can't even tell what's going on here. So I suggest, what can we do? Oh, what I can do is I can change the sweep speed. Remember, the instrument is sweeping back and forth. Let me show you the screen. I don't know if you can see it. I cannot see it. Oh, wait a second. What the heck is that? There is a tone here that wasn't there before.
Now, okay, now it says LO and level. The reason it says LO and level is because I disconnected the LO myself to connect it to the spectrum analyzer. But this tone, ooh, that's suspicious. I don't like. I hope you can see it because I cannot see the screen of the camera. That is not a good thing. I hope I didn't damage anything. That should not be there. I don't know why, because there's nothing connected to the input, of course. So, anyhow, it's sweeping really, really rapidly. I'm really sorry for the camera angle because I cannot see anything. So what I'm going to do is I'm going to change the sweep speed by going to system and sorry, it must be very annoying. System, and I can do sweep time. Let's change that to 30 seconds. There. So you can see now it's sweeping really, really slowly, and that stupid tone is still there. I don't like that a bit. So anyway, it's sweeping very, very slowly. So let me put the camera back. There we go. Actually, the screen now makes more sense. You'll see in a second. Look at that. You see the screen now? Now the frequency is moving slowly. So it's moving. It's not. Oh, it just jumped. And it went out of the range, I think. So it must be going above 6. Oh, and it came back. Now it's going faster. Oh, disappeared again. Oh, okay, did you see that? Wait, we'll wait for it to come. Do you see this? That's bad because it wasn't locked. You can see how it moved back and forth. It was actually unlocked. So this, indeed, there it is. You can see it again. That's a problem because it's not moving with the sweep. That's okay. So definitely, and it's moving at a different rate. I wonder if I should make that a puzzle. I want you to think about why it's moving at a different rate. Why is it sometimes moving really fast and sometimes moving really slowly? Like you see, it's moving faster, and next time it's going to move even faster once it starts moving. There you go. And then you can see how it's changing. There you go. So what I meant to say is that it moves slower, not faster. So it moves slower, and then eventually it's going to move really fast again, and then slower, and then really fast again. I want you to think about, I'll tell you why. Think about why it is doing
IMPP, Imperial Petroleum, reporting Q3 and 9-month results.
Wait. And then, see?
Revenues of $4.1 million.
So it's unlocked. That's definitely the problem, which means that it makes sense that the instruments
A decrease of $1.7 million versus Q3 of 2020.
Wait, I forgot I promised you to measure the
That's
some of the,
India Michael Papa.
So let me go ahead and turn the time back on. And now the instrument stops here. It does that because it cannot do the whole sweep in that region. Because remember, this is a segmented sweep. So we have to limit it to 3 GHz and above. So go frequency. We're going to change the start frequency to 3 GHz. Now we're looking at something of just above 3 to 6. So now you can see that it is. You can see it just jumped big time. So let's take a look at one of those frequencies that I mentioned, the feedback path. So let's look at the feedback path. So maybe we can fully eliminate the other board. If the 600 megahertz signal is there, then we can fully eliminate the other board. Now I cannot measure 600 megahertz with this directly because this only goes up to 500 megahertz. Oh no, this is a 1 gigahertz probe. Fantastic. We should be able to measure even that. But let's look at the divided signal first. Where is that? Here it is. Here's the signal. Here's the 600 megahertz reference signal for the EEG oscillator coming from this connector, going here, getting divided. If I see a divided signal here, that means that the other board is fully functional and the divider in the yellow feedback path is working. Where can I plug this in? I guess I can just connect to the body of this connector. And then I'm going to touch this guy, which is labeled as that. I hope that's what that means. Look at that. We have something on the screen. What is this? What is this? That's something I cannot measure. It's sitting in a really bad angle. Look at that. There is something up there. Let's measure that frequency. First thing, let's put this into AC mode because there is some DC signal. I just disconnected it because I'm not looking at it anymore. There we go. There it is. Okay, let's change the nope. Alright. Ooh, look at that. Not bad. Sample it is fairly low. But what is this frequency? We go under measure. Wait, I'm holding the other probe with my hand, so Excuse me, my speed is not going to be very efficient. Measure. Give me frequency. Where are you? Come on. 4.651 megahertz. Is that right? Just let me think. 600 megahertz divided by 128. What is that? Let me do a quick calculation. 600 megahertz divided by 128. 4.687. Perfect. It's correct. That is a good piece of information right there. Right there. Look at that. That is actually working. That's great because so this means that you can see how stable this is. There's almost no jitter on it. It's very, very, very stable because it's the reference for the PLL. It's coming from the other board. It's locked to a 10 megahertz reference. That's the other PLL. Perfect. So let me now measure. Oh, that's actually a really, really useful piece of information. Really narrowing down what the problem is. So here's the reference, which means I should be able to measure the same frequency here. Oh, that's much larger amplitude, which makes sense. So let's go. Oh, look at that. That is beautiful. Perfect. Perfect. And 4.6, that's it, dead on. And this is a 1 volt division ratio, so this is a it's a CMOS signal. It's not AC, so this is a CMOS swing signal. Perfect, it works. This doesn't move, of course, because that's the reference for the PLL. This is moving, which means if I move to the LO signal, remember I was measuring the reference, so this is definitely the phase detector. If I measure the reference, I go to the LO. Whoa, look at that.
GRPN Groupon prescience point out on Groupon this morning. Says we think it's worth 2.7 times to 4.3 times current share price. That's Golf Romeo Papa November report from prescience point.
Look. See that? It's divided by what would that be? It's divided by some large factor. I forgot the block diagram, but it's divided by some maybe 64 or oh no, but there's a fraction on n divider, so I don't know what the division ratio is. So there you go, and you can see. Look, this frequency is close to the reference frequency, but it's not locked to the reference frequency. It again makes sense because the PLL is unlocked. And again, here, look at how useful this correlated measurement is. Once again, time correlated measurement, divided down signal of the PLL directly with the signal of the PLL itself as it
SAVA, Cassava,
frequency is slowly changing.
Sciences shares are now halted for news, Sandy Alpha, Victor Alpha.
Makes sense. But there is also a weird jump. It just
SAVA shares at 48.81 off the highs, up about $12 now on SAVA.
From here to here. That's interesting. So something really fishy is going on. But this is extremely beneficial. This tells us that everything is working. The divider is working. The LO path is working. The amplifiers and the LO are working. Everything looks good. So now, what is not working is, well, what is most likely not working is the comparison of the reference to the divider down low, or the charge pump, or the drivers of the yeek. Although the drivers of the yeek are kind of working because this is moving. So I think it's time for us to go and find the schematic. This is the most I think I can figure out without looking at it too much. I have glanced at the schematic before in order to find out the frequency of the yeek oscillator. So let me go back and take a look at it again. So here's one of the schematic documents. There are many documents. It took me a while to even find this one. So this is the 3 gigahertz front end LO part. That's the portion we're looking at. Oh, this says for E4403. That's not the right one. Oops. Let me see if I can find the right one. So I actually don't have a schematic for the E4407 specifically for this because I believe this is the same for the E4403. The 3 gigahertz front end LO is shared between all the models for signals below 3 gigahertz, which is what this section will do. So anyhow, so that's the same thing. And let me tell you, these schematics, all the schematics that are the many files are so wonderfully put together. I can understand why these things cost so much money because it just must have taken forever, and you'll see. So let's take a look at all the material list, of course. Everything, all the components, exactly what they are, what value they are, what manufacturer part number they have, they're all there. Okay, so here is the placement, the layout placement of all the components. This must be the back of the unit. Look at that. Here's the YIG oscillator. Here's a description of how it's attached to the board and so on. This is how the, sorry, not the YIG oscillator, this is how the connectors are connected to the board. So the YIG will be here. And there's a component here that has, it's called R542. Don't know what that is right now. There's something looks like a transistor. There's, okay, here's a divider. Remember the main LO divider that's down there? This actually positioned, it's positioned in a weird way. It's not exactly the same orientation as the instrument. But anyhow, so here's the connector with all the power coming in that I measured all the power supplies. Here's the connector LO that I'm connecting to the spectrum analyzer right now. That's it. This is on the other side of the board. All the components we've been looking at, so all these different sections that we've been looking at are here. And excuse me, here are all the schematics. So power distribution, look at that, so amazingly detailed and perfectly described and separated by function. It's amazing. So power distribution, digital control. What else? Why this thing doesn't change pages so easily. Here's the YTO prescaler. There it is, up here. Perfect. Again, I hope I'm not going into all this detail. Here's the prescaler. So here the LO coming in, amplified, divided by 2, divided once again by 4, and it comes out. So this will be around 600 megahertz or so, which is what the signal that gets divided again becomes goes through the fractional divider. Here it is. Here's a fractional prescaler. Here's the main fractional divider. Here's the calibration, IF calibration at 21.4 megahertz. So that's coming from here. Okay, now it makes sense. Okay, so let me see what I just figured out. So this 21.4 megahertz calibration signal comes from the YIG oscillator.
SAVA Cassava Sciences says journal finds no evidence to support claims of data manipulation in 2005 publication.
Not do the alignment because the alignment signal is derived from the YIG oscillator. That's why it's failing. Here's the divide by
Editor-in-Chief
129, which
says after careful examination of these original material, Neuroscience Journal found no evidence of manipulation of the Western blot data or other figures of this publication.
here's the it's a very classic phase detector. These must be flip-flops.
At Sandy Alpha Victor Alpha, shares were halted ahead of that news.
Yeah, they are.
SVFD, Save Foods, expands presence in Mexican agricultural market. Sandy Victor Foxtrot Delta, SVFD.
Anyhow, take my word for it. That's how it works. This is again, it says up here phase detector, so that we figured that out. Here's a divider. So here's the reference for the phase detector. And
VUZI, Vuzix receives another follow-on smart glasses order from AMA to support its expanding worldwide customer base. Victor Uniform Zulu India.
So we tested it all the way up to here. Both of these were fine. Here's phase up and phase down signal of the phase detector. So those two go somewhere else. They're not drawn directly. That's where we have to now start to look at. That's where the next portion should be. What else is here? Okay, we're really on a good track here. Whether we can fix it or not is a different story. Here's our charge pump.
Dow Jones Industrial Average up 0.9% after the open. S&P up 0.9%. Nasdaq Composite up 1% after the open.
Which is a little bit strange. I have to think about this. But okay, here's the loop integrator. Here we go. This is the YTO loop integrator. This is what integrates the phase error. Unlike a VCO with varactors, where the voltage of the varactor is actually does the integration function for you, the phase integration for you. Again, I have to do a different video on that. You have to have an integrator here for a YIG oscillator. YIG oscillators are tuned by magnetic field, by current through the coils inside. That the yttrium material itself reacts to magnetic field and its direction constant changes. Anyhow, so this is the main part. So the charge pump drives the integrator. Makes sense. Here's there. Look at that. Look at that. Look at this. I found the diodes. Let me make sure I'm too fast here. Are these diodes? They are. Okay, yeah, there you go. DS1, DS2. These are the diodes. And this thing is called YTO unlock. So the diodes are light up when it's unlocked, I guess, I think. And there's a signal here that's called frac N unlock, which means the fractional N divider is unlocked. That's a little bit. Does that mean that I hope the fractional N itself is not broken, because I don't know where I can get a replacement for that. Here's the power supply for the YIG
oscillator, we measured this. Remember the 15 volt? We measured that. That one was fine. Here's the FM coil driver. Yig oscillators have two ports. They have a tune and a coil, FM coil and a tune. Let's talk about that later. What else is here? What is that? What the heck is this? Oh, there you go. This is the Yig oscillator itself. What is the frequency? 3 to 8. See? I said 4 to 7 or something. Okay, 3 to 8 makes sense. That's why our spectrum analyzer can measure it, because it goes above 6 for some of its range. There it is. So here's the main tune and the FM tune. So the main tune is where the coil should be. This is really complicated. Many things happening here. Okay, here. So let's focus here. This is one possible failure point. Oh, I hope you guys are still listening. So here's the main coil driver. The main coil driver consists of a power transistor, which makes sense. Remember, you're driving a coil, so a lot of current. So there's something. So here's an op amp. This could have failed, for example. No, I take that back. This could not have failed because the Yig oscillator frequency is moving, which means
NAKD, Naked Brand Group Limited shareholders overwhelmingly approve acquisition of Centro at extraordinary general meeting, November Alpha Kilo Delta.
Maybe not the problem. But so the signal from the loop
NAKD,
the main loop integrator signal that tunes the Yig oscillator and does the locking, the phase lock loop, seems to come from here. That's connected to this, so that makes sense. So the loop integrator directly drives the Yig. But there's also a couple of other signals, something called pre-tune and delay compensation. Pre-tune and delay compensation. I don't really know what those are, to be honest. I can take a guess. Maybe the delay compensation is some kind of a phase.
MS, Morgan Stanley, NewsStreet.com, Action Alerts Plus, strong buy.
Because you have to
Michael Sandy.
Close to the frequency of locking in the PLL. Maybe that's what pre-tune does, or maybe pre-tune is some kind of a calibration that initially is applied. I have no idea. We have to look at it. But the fact that the pre-tune comes from somewhere else, it doesn't say what's coming from here. So a couple of places to check. We can check this op amp, although I'm pretty sure it's working. But we can actually look at the signal. I don't know where this transistor and this op amp are, but we can maybe look at the signal and see the curve, the actual curve, whatever curve, whichever direction it's going, that moves the Yig oscillator's frequency. So we should actually be able to see the tune voltage. And again, because we're using an MDO, we can see it directly correlated with the frequency. That would be useless. That should be the next thing we look at. And again, I can go into so much detail here. This is a sense feedback pathway. It senses the current. Remember, the Yig is tuned by current, by magnetic field, which is proportional to current. So it measures the current. That's how it knows. Anyhow, again, you have to give me some feedback because there's so much detail that can go for hours like this. Yeah. So and then we should definitely look at the loop integrator to make sure that's working. We can look at the pre-tune, although I don't know what it is. Okay, here's oh my god. This is really complicated now. This monstrosity that you see before you is the pre-tune generator. Lot of no idea. Some craziness. I hope this is not broken because this will take forever. There is a 100 Hz low pass filter, so there are low pass filter in the pre-tune, so it must be an active signal. Switched gain amplifier, some amplifier with a switched in the feedback path, so you can adjust the gain. You know what? I can take a guess why this is. This is actually related. This is actually related to what is causing the frequency. That was. Remember, I asked you why do you think it's moving faster at some time and slower at other times? That's why. This is the responsible. But think about it again. I let you still think about why it should do that. I think I understand what's going on here. What else? There's a delay compensation generator. Whatever. Then calibration switch and all the VM. Okay, the calibration. Here's the first one. Here's the mixer. The mixer that I showed you. The only mixer that's on that board. Looks normal. Looks like a regular mixer. It's interesting that they're showing components inside the mixer. It must be a custom part from Agile. Okay, we measure. Remember, we measured mixer IF bias and mixer LO bias. They're there. Here's the first IF. This is the 5.4 gigahertz band stop filter, and the 3.9 gigahertz. This is the band stop filter. First IF. Oh no, I'm sorry. This is the attenuator. Here's an attenuator. These are attenuators, so we saw that already on the board as well. I guess these are working because we have a low signal we can detect, so I wouldn't worry about that. driver. This must be what's driving the. Let me see. Again, I'm sorry, I'm figuring these out as I go along here. I don't know what it does. First IF variable attenuate driver. It must be. Oh, okay. I think I know. This is what attenuates the IF signal that's coming out of the mixer. Makes sense. It must be it for some conversion calibration or something. Okay, that's the last page. Oh no, it's not. There's more. Here's the LO pin modulator. We saw that. Okay, here's that little thing I explained to you with the two dividers and the amplifier. So here's the amplifier, power splitter, amplify, combine, out. Here's some detectors. There we go. This we saw. Remember I told you there are microwave couplers? So they couple power out of the LO for different functions. So they couple it out to go to the LO detector. Okay, here's the LO detector. This is how they detect if LO is present, which we know is present. They couple here again, LO lock coupler. This time it goes to the prescaler. So this coupler is what's feeding the feedback path of the LO. This coupler is supposed to go to tracking generator, which we don't have. Okay, makes sense. So there's another LO to lock the tracking generator to this one. We don't have that. All these must be working because we're detecting LO out. Oh, there's so many things. LO amplifier LC, this is what does the amplitude leveling of the LO signal. Blah blah whatever. LO amplifier bias, thank you very much. Oh, thank God. There's no more. It's finished. Most of this stuff is working because we have all this necessary. We're not getting an LO on level, we're getting an LO out, so these are working. I don't know if the mixer is working. Although that tone showed up, remember on the screen, I don't know where that is coming from. Forget that. This stuff this is the mixer. I told you this stuff is working. So let's go back. I have no idea what this pre-tuned generator or how it works right now, but I know that this is probably to adjust the LO to a frequency where the PLL can lock. And this switch gain amplifier is related to the speed in which the LO changes. That I already told you. I let you think about that. That's a really good puzzle. I will know if you've listened this far because you'll try to answer it. Tell me if you know why the frequency of the LO, the rate in which the frequency of the LO changes depending on how it's sweeping. Think about it. What else do we have? So let's go back here. Good place to start. Sorry, 1 second. Here we go. Good place to start is look at signal that's tuning the ego oscillator.
WMT Walmart, the March 145 calls active now. Whiskey Michael Tango, WMT.
This is where's the charge pump again? The charge pump here. And look at the, oops, where is the charge pump? I just had it. And the charge pump needs to be checked. Sorry, I'm going all over the place. Oh, here it is. Here's the charge pump. Sorry. So look at the charge pump. Look at the loop integrator. Look at the signal on the ego oscillator. Oh, let's go. So after looking at this for a while to try and find out all the components, I figured out where those signals are coming from. It's a couple of the ones that we are interested in looking at. First of all, I found out the pre-tuned signal is actually labeled right here. This is our pre-tuned signal, so we can look at that, which is going to have that switch gain amplifier on it. There's something called I don't know what that is. There's some offset. Don't know what
DAL, Delta, the February 40 call sweep now in Delta. Delta Alpha Lima.
Gate voltage of the transistor that controls the current in the tuning coil of the ego oscillator. Well, that was a handful sentence. So if I look at this is directly the gate voltage of the transistor. So this should be correlated to the frequency. As you change the gate voltage, the current in the ego oscillator will change, its frequency will shift. So let's look at that. I'm gonna ground this bad boy.
BFRI halted on a circuit breaker. Biofrontera halted now. Share is spiking $11.59.
There. So, look here. Look. As the LO
That's
goes,
Bravo Foxtrot Romeo India BFRI.
until you see some LO. Come on, where are you? There. You see, as this LO is moving. Oh, this is an AC. There you go. I goofed that one up. Should be on DC. It's a low frequency signal. Let me change the amplitude to 4.5. Sorry, let me try again. That should not have been on AC, of course. This is a low frequency signal. We wouldn't have been able to detect it. Let me see. Aha, there we go. That's much better. Look. So, as when we see it, follow this. Look. This frequency is this. You see how this signal is going up? Once again, watch this. When the LO appears, look. As the LO is moving forward, this signal is going up. That makes sense
That's, oh, and you just did a jump. So did you see how this jumped when that jumped? You're gonna see it again. You see it goes up, up, and you begin, so you see how the correlation is? You can directly detect it. So this signal, as the signal goes up, more, this is a gate voltage, so the higher the voltage, more current will go through the oscillator, the frequency of the oscillator will go up. So that makes sense. Now I need to look at this on a very, very low time scale because I'm at a 30-second sweep. So I'm going to turn the RF off, because with the RF on you can't look at a very, very long time signal. It's going to have to do a tremendous computation in order to see that. So I'm going to turn this RF off briefly. Only look at the time signal, and I'm going to change the time base. Am I going the right way here? 100 millisecond, 20, 40, oh, this should be very slow. We're looking at like 1 second there. Let's see. Up, 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 up. You see it's increasing? Oh, wow, that's a big jump. It shouldn't do that. I don't know why it's doing that. Let me lower it, let me bring the reference down. The reference here. That's just because I moved the reference. So we should see it. Change it one more time. There. So there. Now you're going to be able to see a full sweep. So it goes up, it jumps down, so it's jumping to another band.
TTNP, Titan Pharma getting some volume here. Tango Tango November Papa, TTNP.
Does it jump? I don't know why it does that. You know, do you remember when we look at the oscillator frequency, how it all of a sudden did that big jump? That must be here. That's not normal. But look at this slope. This is a slope. You see the slope slowly changing? So this, compare this slope to that slope, is a little bit less. Even lower slope. I don't know what's doing that. It's definitely something's wrong in the feedback path. And then again it goes up, up, up. So there's definitely something wrong on the signal that's on the oscillator transistor. Let me look at the pretune. Let's look at the pretune. The pretune should be following the oscillator also. Let's see. Oh, that's much better. That makes sense. The YIG tune, remember, is the signal that will bring the oscillator close to the lock frequency. Look at the, wait until this part goes away, and look at how the slope is changing. Slope is high, gets lower, gets even lower and longer and longer and longer, and then it should drop down and become very sharp again. Look, you see that? That's the puzzle. Tell me why that happens. So this is actually a very, very promising result, because I actually see no jump, no noise, nothing on the pretune. So the pretune signal is working, which means the problem most likely is not with the pretune. Thank goodness, because I have no idea how that works, how that whole circuit generates this even. But it's generating it fine. I think it's generating it fine. Again, if you think something is wrong with what I'm saying, please point it out, but I believe this is correct. Therefore, what we're left with is most likely the loop integrator. The loop integrator is our most biggest culprit. So let's go and look at that. Actually, I should point out that even though I said that this is the most culprit, it could be that the charge pump itself is broken. I don't know, because the charge pump itself is sitting here, and that could be the problem. I honestly don't know. I shouldn't have jumped to the conclusion so quickly. It could be that the charge pump is bad, but the pretune signal looked good. So the pretune signal looked good, and the pretune signal is added to
BFRI, BioFrontier, resuming after a circuit breaker halt. Bravo Foxtrot Romeo India. The high of $12.75 now, up more than 60% on BFRI.
coming from the integrator, therefore must be the problem. So I suggest that you measure the signal out of the loop integrator and see what that looks like. And I wanted to take a closer look at this. There's a couple of interesting things to point out here. Man, this video must be already like 2 hours long. Some interesting thing. This is a loop integrator, obviously, so it's configured as an integrator. Look at the way this is configured as an integrator. They have, first of all, they have resistors in series with the power supplies and a capacitor. They're filtering the power supply even further with 19.6 ohm and 1 microfarad to get rid of some of the high frequency noise.
BFRI halted on a circuit breaker again, $13.35. Bravo Foxtrot Romeo India.
They've done that here. They have the positive terminal of the op-amp connected to what appears to be a voltage divider,
between 10 kilo ohm and 3 kilo ohm. Hope you can see this. So there's a voltage divider here. There's a plus 10 volt reference. I've never actually measured this reference. I should measure it just to make sure it's there. And there's 10 to 3. So what is that? The voltage here, expected voltage at the positive terminal of the op amp is 3 divided by 13 times 10. So something like 2.5 volts, maybe 2.2 volts or something. So it should be around that. And it's also filtered again. So that's the reference voltage. And look at the feedback of the op amp itself. The feedback of the op amp has 2 paths. So it has 2 resistors and 2 capacitors in series. So it actually has 2 zeros in this response. Let's think about it. At very, very low frequency, this op amp is this capacitor is open, that capacitor is open. This op amp is actually an open loop. So at low frequency,
Rivian, December 31, $99 calls. Now, Romeo, India, Victor, November.
higher, this 1 microfarad capacitor becomes a short first. So then you have a resistor essentially becomes a short. I mean, the its impedance drops until it's much less than 2.1K. It drops significantly. Then you have something that's in feedback, and the feedback gain will then be set by the resistor here, which is 316 ohms and 2.1K. So first is open loop, frequency goes up, the gain becomes 2.2 divided by 316 roughly. Then the frequency goes even higher. Then this becomes a short, and the gain will then be 10K parallel with 2.5K over 316. So it has 2 different zeros actually. Interesting. So I don't know which one will kick in first. You have to calculate the time constant between these 2 things. The time constant 1 over 2 pi RC of this and 1 over 2 pi RC of that, whatever those are. Looks like they're in like hundreds of hertz or something. So then this is how this integrator works. So therefore, what we should measure is this signal here, and let's see if this signal has any problems. If this is broken, this signal will be all over the place perhaps, and then we can go from there. So after a long
BKKT, December 23rd, 11.5 call. Active now, Bravo Kilo Kilo Tango, BKKT.
But interestingly enough, I was looking at what this is. This is a DG11DY, which I looked it up, and it's an analog switch. But the U11100, which is the component there, that component is not in the schematic. That's a little bit worrying me because I don't know what it's doing. I don't have the schematic anymore. I can't trace it out, but it's not in the schematic, which means either I have a different version of the schematic, or this is an older board, or I have no idea. But anyhow, that's not there. But U93 is there, and you can identify the components I was talking about. Here's the positive supply decoupling. Here's the resistor they use for filtering the positive supply. Here's the resistor they use for filtering the negative supply. Here's the filtering supply capacitor. Here's that reference signal I was talking about. So if I were to measure, I haven't measured it yet, but if I were to measure this, I should see the 3 over 13 times 10 volts. And then this is pin 1, 2, and 3. Those are the different signals, and blah, blah, blah. We should be able to measure it. So let's measure the power supply voltages just to make sure those are okay. Here again. Get some of this glare. Sorry, it's all over the place. Okay, let me get the cable. And what? You guys are still listening. Okay, here we go. So let's measure the positive supply going into the op amp. That's this guy.
RELI resuming trade now. Reliance Global.
14, that's correct. That's what the schematic says. It's 14 and a half or 15. What does it say?
Shares at
That much. Okay, so
$8.11.
the negative supply must be this one. Minus 14 and a half. Okay, the supply
Up 165% now. RELI.
And this should be the reference voltage. Let me see. So okay, we can measure the. Is this then minus 10 volts? No, that's 0. That must be ground. Where's minus 10? There it is. Minus. Okay, so our minus 10 volts is actually there. The reference, the voltage going in, 2.3 volts. That's it. Oh, once again. Oh, whoa.
BFRI, BioFrontier resuming again. Bravo Foxtrot, Romeo India. 1463 the high now. And pulling back following that pop about $2 from the highs. of about 68%. Bravo Foxtrot Romeo India BFRI.
Maybe there's a because when I push it down and it's making contact, and maybe something at the cold solder joint. Let me touch a different point. Let me touch here. No, 0.9. No, it's very repeatable. Look, I'm trying to be very still. It goes up, and then jump. Whoa, that is strange. I don't understand why it's doing that. Well, anyhow, that's weird. Let's take a look at it on the scope. Connect this guy up here. I'm going to connect it to the reference voltage, which should be a constant voltage. What the heck is going on with that? Let me adjust it here. I'm measuring the reference voltage. Looks good so far. I thought it was changing. Doesn't seem to be changing anymore. No, it's sitting at 0. What is going on with it? No, it's not changing anymore. Strange. No, DC coupled. That doesn't make any sense. Okay, I have no idea what was going on. It wasn't making good contact, I guess. So here it is. Now it's sitting at the. Oh, look, you see, it just jumped. Oh, it jumped back down. That is the reference voltage that is on the input, positive input of the op amp. That voltage should not move around. That's strange. I don't know why it's doing that. Let's look at the output of the op amp. Which pin is that? That would be pin number 6. So 1, 2, 3, 4, 5.
SAVA Cassava Sciences to resume trading in 5 minutes at 10 a.m. Sandy Alpha Victor Alpha SAVA.
Okay, so it's not constant. Oh, it jumps. Okay, so now it makes sense why the and this is really noisy now. So it makes sense now why the voltage on the control voltage of the transistor that controls the EX current was jumping. It's because this is jumping. So I think we are onto something here. It shouldn't do that. Yeah, let's go back to the reference. This is the reference voltage. The reference voltage should be constant. Again, let me show you what I mean. The voltage that was jumping around between 2.3 and 9, or 2.3 and 0.9, that's this voltage. This one, port 3. Why should that voltage change? That's connected to the positive terminal of the op amp. The positive terminal of the op amp should take no current. This voltage should be absolutely constant. There's no reason for it to move. That's actually now, I think we got lucky because this might be now an issue. Let me dig out the datasheet for this op amp. Here's the datasheet for that op amp. It's a low noise, makes sense. It's on the PLL, has to be low noise, high speed operational amplifier. Its noise is reasonably good. It's 3 nanovolts per square root hertz. That's pretty good. It has a very low drift, 0.2 microvolt per Celsius. I'm not sure if that's good or not, to be honest. It has a 17 volts per microsecond slew rate, 63 megahertz a gain bandwidth. So it has a reasonably high bandwidth, and they need this. Let me explain. So I think they don't really need 63 megahertz of bandwidth because the loop bandwidth of the PLL is not going to be 63 megahertz. But there is a correlation between the small signal 3 dB bandwidth and the slew rate, even though slew rate is a large signal behavior. So they want the slew rate. They want high slew rate so that it will jump to the locking quickly. And then because there's a again, I should do a video on PLL. So there's a tracking and there's the locking. So there's the locking procedure and there's the steady state. So they want the highest slew rate for that reason. Now, unfortunately, I don't have this. I don't have this op amp. I don't actually have any surface mount op amps like that one that's AOSYC that's there. So now I have to go and buy this. Okay, here they actually even have the schematic. Okay, so let's take a look. Oh, this is bipolar. So the positive input of this goes to the base of transistor Q1A and Q1B. And transistor Q1A and Q1B during normal operation should have very, very little base current. Certainly not enough to change the voltage, just have enough current going into the positive terminal to switch the current we can look at this and find out what the input current is. Input bias current. There, input bias current is, it says it's 10 nanoamp. There's no way, unless because this is bipolar. The reason I was a little bit surprised, or that I thought about it when it was bipolar, is that if you bias the bipolar switch poorly, obviously you can forward bias the base collector junction and actually have current going into the transistor, so you can mess it up a lot of current because you can forward bias the junction between the base and the collector. Unless that's happening, I don't see why this should take a lot of current. So this is an interesting size component to change, and it's easy to change because it's on this side of the board. So now I have to go and order this and wait for it to come back. That's annoying. So I cannot upload the video right away. I have to wait and see if this is even the problem. So I'm gonna go ahead and order this as one thing. And you know what? While I'm at it, I'm gonna order a whole bunch of components that I think could be wrong. I'm gonna order, you know, a bunch of these op amps. I'm gonna order this transistor, and these things are cheap. You know, we're talking about dollars here. So I'm just gonna order a whole bunch of stuff so that if this is fine, when we change it and we see it's still broken, then we have other things that we can change. So now I'm gonna go ahead and try and order this, and then you know, we'll continue when I get the components. And through the magic of television, we have a DigiKey box. So the components have arrived. I ordered the op amps and a couple of other extra things in case the op amp is not the failure. And now I'm gonna take the board out, show you removing the op amp, putting one in, and let's see what happens. So here we are. I took the board out. This is the side we've been looking at. This is the suspect op amp that we want to replace. Now we can see the other side of the board as well. If I were to flip it over, you can see here's the
EU consumer confidence for December -8.3 versus -8 expected. SAVA, Cassava Sciences, shares resume, popping here now 53. That's Sandy Alpha Victor Alpha. CLVR, Clever Leaves license expansion, doubles Portuguese production capacity and diversifies export potential. CLVR, Charlie Lima Victor Romeo, CLVR.
Alright, here we go. This is the bad one. I took it off and unsoldered and cleaned it. Throw that one away. And here's the replacement. So I'm just going to have to put this guy up here. I'm sitting in a very awkward angle. So I'm going to go ahead and align this and solder it up. Pretty straight.
SAVA, Cassava Sciences halted, shares reversing and dropping here 4807.
It's still broken.
Dropping from near the mid-50s down to 4807 after resuming. Sandy Alpha Victor Alpha halted now on a circuit breaker, SAVA.
I guess the fact that the voltage on the non-inverting terminal was changing is probably because it's operating in saturated mode and it's just banging against the two rails. And so the input for bipolar devices may be biasing different. That's kind of my guess right now. But you can see the LEDs are still blinking. So something's still not right. Well, we have to investigate further. So I've discovered something else. Let me show you. This is the back of the board. So this is the chassis that separates the other assembly from this one. So you can see this is the cavity where the EOS liver goes a bunch of places for some heat sinks, and these are the signals that come from the other board. So here I'm looking at the back of the board again. I've actually connected it to power and it's running.
STWD, Starwood and sell 23,000 square meters of office space in Hamburg, Germany. That's Sandy Tango Whiskey Delta. STWD. PTPI halted on a circuit breaker. Papa Tango Papa India. PTPI. Shares of Petros Pharmaceuticals spiking to $4.84.
So you have divide by 4, divide by 4. And here's a prescaler.
That's Papa Tango,
It's a
Papa
custom
India,
part I
PTPI.
couldn't find replacement for. And this is another custom part from Agilent. So the prescaler and the fractional and PLL stuff, there are no replacement. And this one here, the divide by 2, is also actually an Agilent part. It's a DC to 12 gigahertz gas-based divide by 4 differential in, differential out, which actually could be a part from a barcode that Agilent has rebranded. And this is a regular 2.5 gigahertz divide by 4, which is not in stock on Agilent right now anyway, on DigiKey anyway. But except for the transistor here and this divider, everything else is an Agilent part. But look what I found. So right now I have set the instrument to 0 span, and I found one frequency where the output is somewhat stable. This is not locked, but at least it's stable. So right now the output, I'm collecting the LO, and it's sitting at 3.996 gigahertz, so about 4 gigahertz. So let's remember that number. And I actually don't have a 4 gigahertz probe, so I cannot do an active probing of the signal on this path to make sure it's working. But there's something else I can do. I'm gonna go ahead and disconnect the LO signal from here, like so, and I'm going to add a decoupling cap and a termination to that point so that it's terminated, so we don't leave it unloaded for the rest of our measurement, like this. Here we go. We're gonna go ahead and terminate that. So now I have this board sitting here, and I want to look at these signals. Well, I don't have an active probe, so I'm just going to use this basically this SMA with a very, very sharp pin at the end. Now this is not a very good thing to do in a way, so I'm going to try and probe the circuit with this. Now first of all, remember this is not active, this is passive obviously, and it's going to represent a 50 ohm load, which is actually somewhat mismatched because there's no ground around it. It's just a pin there, so it's not going to be very well matched. But I'm going to go ahead and connect that to the input of the MDO, the Tektronix MDO, like so. And this allows me to at least check for the presence of the signal and get a frequency from that, even though it won't give me accurate power. So if I go ahead and probe this point here, I will see, I've checked, and I will see the 4 gigahertz signal. So let's go ahead and probe here, and we will see if there's a signal before, and we'll check after the amplifier, and we'll check after the divider. So since I have to look here, I'm going to turn the camera the other way, but I will tell you where I'm landing. So first I'll land before the amplifier, then after the amplifier, and then after the first divider. So let's go ahead over here, and you guys can take a look at the signal. So here, first I'm going to go to the input, like so. There it is. Here's the first 4 gigahertz signal, and the amplitude is smaller obviously because it's now double loaded, 50 ohm and 50 ohm. So you saw we're only interested in relative power. So here we have the power at minus 18 dBm. I go after the amplifier, and then the power is hold on a second. This is a very, very bad angle for me.
SAVA, Cassava Sciences resumed trading.
Here we go. So you saw the signal before the amplifier. Here's the signal after the amplifier, like so. You can see it's much larger. So this is a good sign. It means that amplifier, the very first amplifier, is working. So we can eliminate that as a suspect. So that transistor is good. Now I'm going to go right at the input of the divider. Here's the right at the input of the divider. I still have signal. Now I'm going to look at the output of the divider. Here's the output of the divider. Now look at that signal. First of all, it's not stable. Second of all, the fundamental tone is sitting at 666 megahertz. But 666 megahertz is not 4 gigahertz divided by 4. The signal there should be 1 gigahertz, but it's actually 666, which is a weird number. Some kind of perhaps a self-resonance frequency of the oscillator. Whatever it is, here's the input of the oscillator. Now input of the divider, 4 gigahertz. Here's the output again, unstable, and 666 megahertz. So I think
PTPI resuming trade now. Petros Pharma. PTPI shares $4.88 the high up 42% now, 43%, continuing to spike here, just under $5 now for PTPI, Papa Tango, Papa India.
Which of course is completely wrong. So a couple of days has passed by and I managed to find something after a bit of research. Hittite makes this particular part number, which is a frequency divider that works up to 13 gigahertz, has a very, very similar pinout to the existing one that was on the board itself. So I went ahead and bought one of these. I only bought one because they're a bit pricey. And so here, I've taken the other one off. It wasn't easy to take it off because it's the bottom plate of the package is actually soldered to the board itself, and they do this typically for microwave components, not just for heat transfer but also for good EM shielding. Unfortunately, I don't think I'm going to be able to very easily solder the new component down and from the bottom part as well, because you have to reflow the board, and there's a lot of massive amount of thermal inertia here because of all the ground. So I'm just going to solder the pins and hoping for a reasonably good contact to the bottom. That's the best we can do. So let's go ahead and I'm going to try and solder it back on and see what happens. Alright, I put it back. You can see it's right there. There's a little white spot that you see underneath it as thermal putty because I couldn't really get the bottom soldered. It would have been very difficult. So it's going to run a little bit harder than normal. So, but check it out. I remember we measured it before. So now I'm going to do exactly what I did before. I'm going to monitor the input frequency. So here I'm going to now look at the input frequency, which is this guy. 4 gigahertz like before, and we're going to look at the output frequency and check it out. 1 gigahertz main tone. The other ones are harmonic because the output is square. So it is doing something different than it did before. Before it was producing 666 megahertz. Now it's producing 1 gigahertz. So there's a chance, there's a potential that this might be doing something now. So I'm gonna close it back up. Let's see. I hope it's working now. Well guys, check it out. I put it back together and look at that. All the errors are gone. It's sweeping perfectly fine. No alignment requirements and no LO unlock or anything. So it looks good. It might have actually, that might have repaired it, and cost about $25. That component that was bad was about $25. Not bad. These things are quite expensive. So, well, how can we test it? Well, there's a lot of ways of disconnecting signal source to it, but I thought I'd do a really quick experiment to test it out. Here I have a PLL module. This is some kind of I actually haven't opened this. I'm interested to see exactly what's in it, but it's just a basic PLL. Its output frequency is really high. It's 14.5 gigahertz. I've tested this before. It's fairly accurate. It's very, very close to 14.5 gigahertz, and it requires one power and just has an RF out, which is connected to this. And this is a Type K cable, not an SMA cable. Although 14.5 gigahertz is still okay for SMA. So we can go ahead and try this. You may ask me why I'm not using this source. This is a 26.5 gigahertz tracking source, but this is actually a tracking source. It's not a synthesized source. So if its frequency is not very accurate unless it's connected to something that's doing the tracking with it. So anyhow, let's go ahead and
AEHR test system shares now spiking here, $18.37, up 18% for Alpha Echo Hotel Romeo. AEHR company earlier this morning announced new order for 4 Fox NP test and burn-in systems. That's Alpha Echo Hotel Romeo. Also now Banyan out on AEHR with a newsletter recommendation. Alpha Echo Hotel Romeo.
Span here of the peak, and we can reduce the span quite significantly, and then we can center it again. Do a peak search, center once again, reduce the span even further. Now it's a 10 megahertz span resolution, reduce the resolution bandwidth further. Now it's 1 kilohertz resolution bandwidth. Further center it. I can further reduce the span, and you'll see the point of what I'm doing very soon. There we go.
I can even, I believe I can even do that even further. Reduce the span even more. 200 kilohertz, 100 kilohertz, 50 kilohertz, 20 kilohertz. Actually, in this option, I cannot go resolution manual lower than 1 kilohertz, so there's no point reducing the span that much. So you make the span a little bit bigger. Here's a, there we go, this is what I wanted to see. I apologize for that. Take a look. This is a classic PLL output, of course. You can see the
TSLA Tesla Model Y earns highest IIHS accolade. That's Tango Sandy Lima Alpha.
or by the PLL itself, but you can see some, typical characteristic. These spurs that you see here are the reference spurs of the PLL coming from inside the module, and you can see the frequency 14.493605. Really close, the amplitude 5 dBm. That's how much you should be. So it works. It's been repaired in all its glory. Now it sits in a new location in the lab. Now we can do spectral measurements up to 26.5 gigahertz, allowing for more interesting videos in the future. And if you're still here and watching this, bravo, really, leave me a comment, let me know that you watched it to the end. I'd be amazed, it's more than 2 hours, I'm sure. And let me know what you thought of the content, and also don't forget the Twitter account I mentioned at the beginning. Go ahead and sign up for that, and see you next time. I have a really cool episode for you guys today. We'll be taking a look at the Keysight EXA signal analyzer / spectrum analyzer, and I'm going to do a very extensive review of this unit, including a teardown, operation, as well as a whole bunch of different applications that's built into it. Now this is a very, very long video. It's over 1.5 hours long, so there are pointers in the description that allow you to jump into a specific section of the video, but I hope that you get to watch all of it because they're all related in a way, and then you can pick up a lot of useful information. Now of course I can't cover everything with an instrument like this. It's going to take quite some time to go through all that detail, but nonetheless, let's go ahead, take a look at what's going on. I hope you enjoy the video. So how does the Keysight model overview look like for the X-Series spectrum analyzer? Well, here I have it right over here. The X-Series spectrum and signal analyzers vary from the CXA, EXA, MXA, PXA, and finally the UXA model. And of course, as you go up in model, you're going to have quite a bit of difference in performance. Now the EXA, which we're going to take a look at today, has a unique position. It's because even though it's the second model here, it still has millimeter wave capability.
RIVN, Rivian, more call activity now. The January 120 call sweep on Romeo, India, Victor, November, RIVN.
And the PXA remains the instrument with the highest frequency of operation of 50 gigahertz. Now if you look at the UXA, which I've used before, I mean, this is a fantastic instrument. It has a brand new GUI.
Rivian shares now at 93.79 off the high.
Multiple applications in parallel. It's just a totally different paradigm and a way of using the spectrum analyzers. And this is undoubtedly a reaction to the fact that Roden Schwarz has had spectrum analyzers with advanced GUIs for quite some time now, and Roden Schwarz is definitely Keysight's biggest competitor in this area. The highest frequency of operation of the PXA at 50 gigahertz is still short of what Roden Schwarz offers, which now they have all the way up to 85 gigahertz, but of course that's a very niche market, so whether or not Keysight thinks that that's a market that is important to them remains to be seen. But nonetheless, now if you look at the performance of the EXA as we go up, we are looking at a phase noise of minus 106 dBc per hertz at a 10 kilohertz offset at 1 gigahertz.
OLPX, Olapex Holdings, February 25 call sweep, Oscar Lima Papa X-ray.
All the way up to the UXA, there is an enormous improvement. We're talking about 30 dB of improvement in phase noise, which is huge. Nonetheless, the EXA being able to do millimeter wave capability and at a price point that it has, it puts it in a very attractive position for a general purpose spectrum analyzer. Now, obviously you can go up to 1.1 terahertz if you have external mixers, but unfortunately the external mixer capability is only available for instruments that are operating at 32 or 44 gigahertz. They don't have mixer capability for 26.5 gigahertz models or below. Even though the PXA certainly does offer that at 26.5 gigahertz, you can still have external mixer capability. And in terms of the noise floor, you can see definitely some improvement from up as well. And the list of applications that the EXA supports is just huge. I mean, I have all these applications installed currently on the model that I have here, and there is everything under the sun, every single ISM band, every type of different wireless application standards with all the required tests and masks and everything is already included in different applications that it supports. Now in terms of real-time spectrum analysis, the real-time spectrum analyzer options only start from MXA and going above, so the EXA does not support that, but it does support 40 MHz of instantaneous analysis bandwidth, which means that you can do baseband demodulation and all those things, and we will take a look at that as well. And the other point to mention is that the linearity of the EXA at 18 dBm for a TOI is also fairly respectable. Of course, it improves significantly going up to the UXA. Nonetheless, now that we have a fairly good idea of where this sits in the lineup and what the purpose of this instrument is, so you can have a better idea of whether this would meet your needs. So let's go ahead and take a look and see how this instrument actually operates.
We're going to take a look at the EXA signal analyzer from Keysight, and we're going to take a look at the architecture, the building block, and we're going to do a teardown of the instrument. Once I told Keysight that I wanted to do a teardown of the EXA, they went ahead and they sent me all of this, which are all the different LO building blocks, the RF circuits, the baseband processors, all the different boards that go into making the EXA signal analyzer. This is fantastic, and I really appreciate this, not just because it's a lot of effort to put the package together and send it to me, but also because it represents a level of commitment from Keysight's perspective toward their potential buyers and existing users. After all, you really won't need to understand how the instrument is manufactured, how it works, what the principle of operation is, before you can make an informed decision, and also because that's the only way to get the best out of your measurements. And Keysight and HP and Azure, they've always been really, really good with that. So I really appreciate it. Big thumbs up from me for sending this to me and being able to show it to everybody, and being so open about it and actually sharing all this valuable information. A lot of learning experience and very, very useful, definitely for the people who are going to be using it. So we're going to go look at the block diagram first, and then depending on the different sections, we're going to come back to these boards and look at the boards and then compare with the block diagram, and that should be a very interesting section to understand the instrument's operation.
So here we have the block diagram of the millimeter wave EXA from Keysight. Now this is the millimeter wave instrument, meaning that this is the model that operates above 30 GHz. In fact, you can buy these all the way up to 44 GHz, as I showed while we were doing some model comparison. Now, as is with any spectrum analyzer operating on such a broad range of frequencies, not all the conversion is done by a single mixer. As a result, the signal path takes different routes throughout the instrument depending on the ranges of frequency that's being looked at. And this is broken up into different pages in the service manual, and here right now we're looking at the section that operates below 3.6 GHz. Now the service manual is 657 pages, so we're not going to look at everything obviously, but I want to give you a good idea about how the instrument operates so you learn how to get the best out of your measurements. So let me get rid of this up here so we can get a slightly larger view here. So let's start.
BA Boeing shares at the highs now 197.89. Boeing up about 5% today. Bravo Alpha. Boeing earlier announced orders for 767 freighters from UPS. That's Boeing BA shares 197.89, the high now.
And the signal after that enters this low band switch. And this low band switch is responsible for routing the signals that are below 3.6 GHz to a different path. And you can see some into protection over here. And once it's broken down here, all this upper section is not connected to anything anymore. And the signal goes through a low pass 4 GHz filter, and that makes sense because you don't want this portion of the circuit to process anything above 3.6 GHz. So they cut everything else to make sure they don't have any extra harmonics. And then you have an option of going either to an electronic attenuator, which we'll take a look at once we're looking at the instrument, or if you have the option of a preamp, it will go through the preamp. And the preamp here will give you another 20 dB of gain, lowering the noise figure of the front end significantly, bringing your noise floor down. This will be very useful when making noise figure measurements, as we will do. Then
Then the signal is processed by a mixer. Now, normally spectrum analyzers, which go all the way to these higher frequencies, don't like to process signals at very low frequencies. They want to bring it up to a kind of a mid-range of frequencies before they get processed, and this is in fact what this mixer does. This mixer actually up-converts the signal all the way up to 5.1 gigahertz, and the output of it is amplified and sent out through an external filter because they want to use a nice high-quality factor, high-Q microwave cavity filter to really band pass that signal to make sure that it doesn't have any other components that they don't want. And obviously the LO distribution network here is responsible for tracking the desired RF frequency so that the output of the mixer is kept exactly at the center of 5.1 gigahertz with 150 megahertz of bandwidth and so on. Then that is IF out, called the IF out here, is fed back.
New York City Mayor de Blasio announced a $100 incentive for people to get the COVID-19 vaccine booster.
Here can process signals from 3.6 all the way to 17.1 gigahertz. So there's a solid state switch here that then gets switched into this direction, and the signal would then enter this mixer. And this mixer receives its LO again coming from the outside, and this LO takes this path over here going to a balance, becoming differential and amplified. So this is actually a balanced mixer at the LO port, and it's most likely also a subharmonic mixer all the way up to
BFRI Biofrontera shares off the highs now, 1390 up about 83%, hit a high of 1463 earlier. That's Bravo Foxtrot Romeo India BFRI.
control it, and I will talk about that separately. So you can clearly see that the signal path, no pun intended, of the RF signal coming all the way through here, below 3.6 here, getting filtered, getting up converted to 5.1, going through an external cavity filter, going back over here, getting mixed down all the way to 322.5 megahertz. Now if you go ahead to check another signal path, let's jump up to 3.6 to 17.1 gigahertz. Now this portion of the circuit is no longer needed, and you can see that we go through the same front-end mechanical attenuators as to be expected. So these are 44 gigahertz rated attenuators, and then we switch up into this path which processes everything from 3.6 all the way to 44 gigahertz. And if you have the preamp option, you get a 30 dB boost of signal power over here for these frequency ranges. Once again, very helpful for doing low noise, low signal power measurement, so that your signal is not buried in the noise floor of the instrument itself. This will significantly lower the noise figure of these mixers. The signal is then sent out over here. Let's ignore this for a second. It's going to go through the YTF. The YTF is a Yig-tuned filter. Of course, this is a high-quality narrowband Yig-tuned filter which tracks the RF frequency, and this is absolutely necessary for these subharmonic mixers. If you don't have this, then your broadband signal covering from 3.6 to 44 gigahertz is going to just overwhelm these mixers with tones and harmonics and images and everything, and it's going to be unusable. So this is absolutely necessary, and that is going to be tracked and following the LO and the RF signal. Now these things are aligned, of course, because as the temperature changes and the age and so on, the alignment gets shifted around. So that's why these internal alignment circuits really exist. One of the reasons is to tune and align the Yig-tuned filter here. So the output of that is now a narrowband signal, and that signal then goes through this other mixer, gets amplified. There's a three-way switch here, which is these are all solid-state switches, and that goes into this same mixer here.
Futures are pulling back here.
And the LO path is slightly different. You can see that the signal here, they double the signal first, and they go through a 14 gigahertz low pass filter to get rid of the harmonics of the LO, and then again becoming a balanced differential and so on, the same as before. The IF lands once again to the same frequency at 322.5 megahertz, which is exactly what you want. All of these mixers will always down convert the signal, no matter where it is, into the same IF frequency. Now if you jump up again to 17.1 to 34.5, everything remains the same, except that we're going to be using this top mixer over here, and again it's driven with differential LO, and the same path is chosen in order to do that. We're doing exactly the same thing, except this mixer is running on a different harmonic of the LO, and therefore it's going to land back the same ranges of frequencies, just a multiple higher, back onto the same IF. Now we go again forward from 34.5 to 44 gigahertz. Now this is purely in the millimeter wave region. Everything is the same again, except the path is now single-ended. So in fact, they're doing a single-ended LO drive for this final subharmonic mixer, probably because they can't process the signal at the LO differentially and then have the subharmonic mixer working differentially. It's probably a single-ended device, not fully balanced, because this frequency is very high here. So it's to be expected. And then they have the same IF. Although I'm a little bit surprised that this path is never used, I suspect that this is an error in some way, that this should be going down through here, but you can see that between these two versions it's actually not. So I suspect that's probably a mistake, or maybe not, but otherwise then they're never using this, which doesn't quite make sense. Anyway, so then the IF coming out over here goes through this front-end controller. This front-end controller has
UK's Sun reporting UK Prime Minister Boris Johnson to make announcement in the next 48 hours on whether to impose a circuit breaker restrictions in the UK.
But there's also another path which you can take, and there's actually two other paths. The other path down here, which has its own mixer and its own VCO here, can be taken out of an auxiliary IF at the back of the instrument. And this is really helpful because the analysis window of these instruments can only go up to 40 megahertz for the EXA series, as I mentioned before. So if you want to look at a wider IF simultaneously and digitize it, if you have the auxiliary IF out option, that's exactly what you can do with that. You have a much larger signal, over 100 megahertz, which you can take a look, and hopefully we can do some of that experiment here with the EXA we have. Then you also have this other option here that the signal can be switched to this path, and once it's switched to this path, this is the 40 megahertz analysis window, which is going to go through a different A to D converter than this one. They don't need to be digitized the same way. This is the regular view, and this is the baseband view, the 40 megahertz analysis window view, so which is fantastic. We'll take a look at that. So let's go ahead and follow the IF signal here.
Circuit breaker restrictions in the UK refer to a short-term lockdown.
System block diagram. Now we don't want that because we want to take a look at the 40 megahertz version. That 40 megahertz is the upgrade, and of course the unit that I have here in the lab is fully loaded. It's going to have the 40 megahertz analysis one. So let's jump to that one. This is basically the same thing, except it has much more broad processing power and the 40 megahertz band. But let's take a look at that then. And we have the IF coming in at 322.5 megahertz. So this is the IF coming from the previous section, and then it enters an analog IF section. And this is purely an analog portion of the IF, has no data converters in it yet. And this includes things like the cone calibration, which is used to switch into the pad to get the calibrations for the IF and so on. But it also has the very important down convert mixer, which mixes the 322.5 megahertz signal all the way to 22.5 megahertz. Now this is within the window of the frequencies that our high resolution ADC can actually now process. And after that there are different filters and so on depending on the IF configuration that you've chosen. And there's also the burst carrier trigger used for some of the options in the instrument to detect some carriers that come and go at certain rates and so on. We'll probably get into that later when we're using the instrument. But then the output of that now sits at 22.5 megahertz. Once it comes out of
BLNK blink charging, March $30 calls active now. Bravo Lima November Kilo. BLNK.
Portion of the instrument as well. So we're going to take a look at this. So what happens for the 22.5 megahertz signal? Well, that has to be digitized now. This is low frequency, and all the everything that was processed from 9 kilohertz to 44 gigahertz ends up in here as the LO and the RF suite of the instrument, and that goes into a signal to differential converter there for the ADC input. Is a low pass filter, anti-aliasing most likely, and then it goes into a 16-bit A to D, and there is also some dithering added into here, and of course dithering is added to the ADC input to decorrelate any signal with the frequency, clock frequency of the ADC, and reduce spurious-free dynamic range, and improve the spurious-free dynamic range of the ADC. And that's
AERC Aeroclean Technologies shares spiking here. Alpha Echo Romeo Charlie. $13.55 now halted on a circuit breaker. AERC up 20%.
Analysis, and we will get to that in detail, and I'll tell you some of the things it can do while we're looking at the board itself. Now the other path that we have is the main path that actually does the 40 megahertz digitization, and that path is a different path because they don't do 40 megahertz analysis on a 16-bit ADC, they do it on a 12-bit ADC, and that's this signal over here, and that signal then comes over here, and that is going to go all the way through here, and that's already down converted once again with another mixer that was in the RF section. Now it's sitting at 250 megahertz, and that goes through a whole bunch of different things, filters and so on, again some dithering added over there, and then it goes into this ADC. So depending on how you're using the instrument, if you're just using it for basic signal viewing, you will be using this path, and if you're using the DSP digital signal processing of the 40 megahertz bandwidth, you're going to be using this path. And I'm sure that there are some combination of both of them that are used perhaps. And then we also have the 100 megahertz reference clock that's generated from somewhere else going into here and getting doubled and split, and so on, and goes into the ADC clock when the ADC requires twice the frequency of 100 megahertz. All the different sampling frequencies of the ADC whole bunch of other digital portion here which controls everything under the sun for all of these digital fancy digital functions to be taken care of. All of them are handled through the digital IF. So what are all these LOs coming from? Well, the LOs are going to come from the reference and the synthesizer block diagram here, which is going to describe exactly how all the different LOs are generated. Now I have this board here we can take a look at. Unfortunately, I don't have this board. It would have been perhaps more interesting to take a look at this one because this is the main reference portion and it has all the different PLLs already in here. There's only one PLL in here. But let's start from here. We have our 10 megahertz reference coming in here, or the 10 megahertz voltage control oscillator that's built into this board there. And that 10 megahertz reference is the foundation for locking all the PLLs. And you can see a whole bunch of different PLLs. Here's the 100 megahertz PLL. This PLL is locked again to this 10 megahertz reference. It's got triplers on it, it's got divider by 2 on it, it's got a whole bunch of different things generating just an enormous number of different LO signals distributed all over the place. All the instrument LO signals required for the mixers, the ADCs, the alignment signal, everything has to come from somewhere, and they're all generated over here. And the high frequency portion of the PLL is then taken off out of the 100 megahertz, going through a doubler, a quadrupler, another doubler, reaching all the way to 4.8 gigahertz, which will be the reference used for this DRO, the dielectric resonator oscillator here, which is a very high quality factor oscillator. And this 4.8 gigahertz oscillator is going to determine the main phase noise of the system, because this is the main LO used for all the mixers. And that then goes out over here, goes into a fractional length synthesizer with a VCO over here, used as a reference for it, and then that is doubled and goes through a whole bunch of different filters and more doublers and filters in order to be able to get a very good isolated tone of the final LO that's going to be fed back over here into the instrument's front end for all the different mixers, subharmonic mixers, and so on. So this entire section over here handles all of the LO distribution, multiplication, and so on. And this is one of the key blocks that enables low phase noise from the EXA. Of course, the phase noise of the EXA is not as good as the UXA. That's going to be much fancier there, but nonetheless, we're going to have a fairly good phase noise from this instrument as a result of this. Anyway, so I've talked a lot about the block diagrams. I hope that you found it interesting, and it's very cool to see how this instrument is made. So let's go back, and I'm going to show you this board over here, the RF front end. We're going to take a quick look at that. I'm also going to show you this board over here, which is a digital IF, as well as the LO synthesizer board. And that's going to complete this section, which includes the teardown as well, and then we'll get to play with the instrument.
So let's go ahead and take a look at some of these boards that I have. The first board is going to be the RF front end, and here's a block diagram of it just to remind ourselves. And the RF front end is the portion of the circuit that processes all the millimeter wave components, so it should be pretty interesting to take a look at it. And here I have it right over here.
AERC resuming after a circuit breaker halt. Alpha Echo Romeo Charlie.
Now I've taken all the screws from the RF shield, and these RF shields also act as heat sinks. And if I were to go ahead and lift that, you can see that by the presence of these thermal pads that are going to be able to dissipate the heat. And the other side also has another board which has fins on it, which is another indication, and there's some isolated compartments there for EM shielding. And there is our board, and it's all covered up. We can't see anything, and there's a few reasons for that. One reason is because they obviously want to protect those circuits, probably for intellectual property, and also just to protect them and shield them really well. Now, by the height of these little sections, you can see how shallow they are. I suspect that they probably don't have a lot of packages under there, and a lot of die on PCB or a wire bonded or flip chip directly embedded. And all of the ASICs that are in here are going to be custom, either made by indium phosphide foundry from Keysight or some other gas foundry that they have access to. And now, looking at this, one of the other things you immediately notice is this cavity filter over here, and that filter is indeed the external filter that we were talking about before, required to have very high quality factor, and indeed they're using an external filter there, and that's to be expected as well, connected through these rigid SMA cables to the board. So the input is going to be right over here, and we know that because this is our highest frequency connector. Indeed, this is a 1.8 millimeter connector, which easily goes to 44 gigahertz. No problem there at all. And you can see that the front end chassis here is different. It's most likely to support the connector, so they enter with a much nicer connector, a very solid build over here as to be expected. They don't skim out on these high frequency millimeter wave stuff at all. And one of the other interesting things is that these little circles that you see there, there's tiny little holes underneath that, and those holes are necessary because when you reflow the board, the gas needs to be able to escape, because they probably put all these together and then they reflow it, and then they stuck these copper tapes on top, which seals them completely, and they have actually some special glue underneath them, and the sealing is necessary because most likely the ASICs aren't all in silicon. Like I said, they're in phosphate or gas, and that means that they need to be hermetically sealed, which is very important. But nonetheless, even though we can't see them, we can follow the signal path. Here comes the RF signal. In between these two blocks over here is going to be our solid state switches, which is a three-way switch, goes all the way up to 44 gigahertz, and our triple mixer is going to be all embedded in here, which means that our IF at 322.5 megahertz is generated within this section, and it needs to be amplified, and I suspect that's what this little guy is. There's a little amplifier over there, and it has two balance at the input and the output, single into differential conversion with the center tab common motor, and that's because the IC is probably differential. Interesting that they've gone through that route to go differential and back to single-ended again, and that's going to be the IF output. So where is the solid state switch that selects which output the mixer is taken? Well, if I flip it on the other side, we can indeed see that we have a Hittite or an analog devices gas three-way switch over here, solid state switch, and this is probably the circuit that's responsible for selecting which IF comes out of which mixer. Now, everything else, such as LO distribution networks, which goes to the triple mixer, as opposed, and also for the low band path, are all going to be embedded in here.
Bloomberg headline: FDA expected to authorize Pfizer Merck COVID pills this week. That's PFE, BNTX, MRK.
I think is actually exposed, so we should be able to take a closer look at it, and I believe that's right over here. And there are some indications that that's the case, and you can see that you have like a few different paths of signal. This is where I believe the LO comes in, and you can see the LO coming in here. It goes into this little lumped capacitor there. We have some coupled lines.
Shares of Pfizer off the lows now. PFE 5784, Papa Foxtrot Echo. BNTX also off the lows, 270.50.
And then they have some other capacitor components there, two little actual discrete capacitors.
Actually, BioNTech not affected on that, on the pill itself.
Following that, we can go over here. You can see that
and Merck getting a pop here.
And we have another impedance transformer line where we have a signal coming from above here, which is probably going to be an IF signal coming in. We have another stop to a nice discrete.
Merck popping here,
making a good stop at
584.
And then we have the output of it coming all the way out over there, and that goes onto our cavity filter, exactly what the schematic says, or the block diagram says. You can see the mixer that has to go through the cavity filter, so it matches really nicely, and I think that's probably what's going on. And if I were to flip that to the other side, the location of these places where the solder mask is missing is a good indication of where those ASICs are, because they have removed the solder mask so they can make a better connection, better thermal connection with lower resistance onto the thermal pads on the other side. So everything works out quite nicely. All the other different LO ports and so on are all, of course, embedded on there. And if you look closely, someone also has left a message. Oh, it's upside down. There you go. Actually, it's on the other side. I apologize. Here we go. And you can see it says P3 Love. Someone has used the ground stitching on this board to make a little symbol, which is kind of interesting because normally people just use traces, and this individual has used the stubs, which is kind of unique. And of course, people do this all the time. I have left a lot of drawings on different ASICs that I have made, because somebody made one. They look at it under the microscope. It's kind of a fun thing to do, and it's nice to see that someone's done that. And other than that, it's really otherwise pretty straightforward. All of our LO distribution paths are all embedded in there, and I don't think there's anything else that we can actually see. Unfortunately, I can't open these to show you because these are permanently connected, but I thought it's a pretty close look. It's pretty neat, and I wanted to point out the quality of the work that goes into this. Obviously going to be first class, as we shall see from the performance of the EXA when we use it. And Keysight, some of the best in the world, they really know what they're doing. So let's move on to a different board. So here we have the baseband digital processor board, and this is where all the magic at the 40 megahertz capture happens. This is again for the 40 megahertz version, not for the 10 or 25, so this is an upgrade that I have over here. And one of the very first thing to note is I've taken one of the heat sinks off, and you can see two big Vertex 4 Xilinx FPGAs here. And these FPGAs are critical because they provide hardware accelerated analysis within the 40 megahertz window. They interface directly to the A to D converters, which we will take a look at, and this allows you to do very fast power detection, spurious tone detection, and do things that you normally wouldn't be able to do if you were doing a sweep analysis. This is critical if you want to be able to detect intermittent events, which are not very common. It also has a deep memory of 2 GB, which is stored on the other side of the board, and we'll take a look at it when I flip it over. But without these hardware accelerated FPGAs, you wouldn't be able to do the fancy detection of problems that you normally would want to do on a 40 megahertz analysis. And to add on top of that, the VSA software, the Vector Signal Analyzer, runs natively on the Spectrum Analyzer because it runs Windows 7. But the nice thing is that the VSA has a direct hardware connection to this board, so it runs ridiculously fast. It can grab data directly from the hardware processed by the FPGAs and then just display it on the VSA. The processor doesn't have to do anything, the main processor of the PC, of course. You don't want that to be reliable, to be responsible for doing this type of analysis. You want it hardware accelerated. They've done that here with these two big FPGAs. And the other things you can notice is there's obviously other FPGAs which are used for other little purposes, and this is the back of the instrument with all the different I/O interfaces. Notably, this connector over here is for the smart noise source, the SNS noise sources, and I have one of those, and we'll take a look at it and use it in one of our experiments. And the drive voltage for that and the interface for that is built directly on this board as well, and there's some expansion slots. I've also gone ahead and taken screws off over here as well, and underneath it you would find exactly what you would expect. All the clock distribution that you would need for this board are all over here. This board also has built into it a whole bunch of other interfaces that it has to take care of because it talks to many other components which are outside of this board. All of that needs to be taken care of as well, and the processing of course done on the FPGAs. And there's clock distributions and so on which will be embedded in here. And the ADCs are right over here, as I mentioned before, a 12-bit and a 16-bit. Just to remind ourselves, this is the block diagram. So we're looking for this ADC, and this clock distribution which has multipliers and filters on it, and of course all the DSP processing which was over here, which I just talked about. So we should be able to find those, and in fact a very quick search reveals exactly where they are. And we have two ADCs over here. The first one is an analog devices one, and the second one is a Texas Instrument one. Let's start with this one. This is a the AD5527. And that's, as I said, the Texas Instrument part. This is a 12-bit, 210 megasamples per second ADC, and it has a DDR output, which is very helpful because you can interface with it really, really fast, and that's what you want, to be able to grab data from the A to D converter really quickly. This is the ADC that's used for the 40 megahertz analysis window. And its performance is quite good. It has about 70 dB of full-scale SNR with a 70 megahertz input. So that's exactly what you would want to use. The second one is an analog devices. It's an AD9446. This is a 16-bit A to D converter. Can be sampled up to about 100 megasamples per second. At around a 30 megahertz input, it has over 83 dB full scale of SNR, which is perfect because the IF coming in is at 22.5 megahertz. So everything else is pretty straightforward. We have our multiplier path, which has a quadrupler. I'm sorry, it has only a doubler on it, and a whole bunch of different filters. All the filters are implemented in discrete lumped LC elements here because you can afford it. The frequencies are low enough, you don't need to have them embedded into the PCB. And we have some other paths again for LO distribution for the ADCs as well. And if I were to flip it on the other side, you can see a whole bunch of other components there. This is where our IF circuits, IF signals and the LO signals for the ADCs all come in, and I mentioned that those are generated by the LO synthesizer itself, and we'll take a look at that board next. There's the back of the FPGAs, and here's our memory that you can see, just standard DDR memory it looks like, and everything else is just power distribution, DC-DC converters. These two transistors over here, which I'm pretty sure are responsible for the 28-volt drive voltage for the SNS noise source. And I'm going to flip it back over here again just to notice a couple of other nice designs there. You can see that the FPGAs and the digital section is completely isolated. There's a gap in here which completely separates the ground and the VDD and everything of this section for isolation from noise and switching. and all the signals from the A to D are two differential transformers coupled across magnetically, essentially. So there is no direct connection, which is great. Again, these people are, you know, some of the best in the world. They know exactly what they're doing, and this design looks pretty nice and neat to me. I'm not sure how much more I want to talk about it. It's just the architecture is fairly clear and it looks beautiful. Let's take a look at one other thing. That would be the
SAGAU, Sagliam acquisition shares opened at $10, priced at $10 per unit, Sandy Alpha Golf, Alpha Uniform,
microwave filters,
SAGAU.
as well as solid state selectors and VCOs and so on. So let's go ahead and lift this guy up. I've taken a whole bunch of screws out of here and take a look at it. It looks very nice, as like to be expected, just like any other of the board that we were looking at. Let's just remind ourselves of the components that go in here. So we're looking for things like VCOs, fractional controllers, doublers, amplifiers, solid state selectors, bank of filters, and again doublers and so on. This entire chain should be pretty obvious and detectable. So let's go over here and look for our VCO. Do you see it? Can you see it yet? It should look different than anything else on the board, and in fact, indeed, it's right over here. There it is. You can see it's very nice looking. It's got the RF transistor right in the center. Here's a VCO tank and above and below it, and you can see that inductors are embedded directly onto the PCB right there with what appears to be the reactors there and the control voltage coming in. The output of that VCO is taken out over here, amplified. If I zoom back out there, you can see we can follow the signal path very nicely from there. You can see the amplified output goes over here, goes through some filtering there, and then it goes through a ball and becomes differential into a doubler. But this is at least what appears that is going on over there, and the output of the double signal then comes out and goes through our selector there. This is a solid state switch again. Now another interesting thing to note is that I don't see any of the filters embedded on the PCB top layer there, and they're not at the bottom layer neither. But because of the ground stitching and because of the fact that there are these shapes in the ground stitching, it gives me the impression that those elements of the filters are embedded in the intermediate layers of the board. And that's really interesting. I wonder why they've done that, perhaps to protect how they were made. But you know, I guess you could extract
UBER Uber popping here. It's the highs 4164. Uber shares up almost 5%. The February 42.5 call sweep now on UBER.
Put some strain on the lithography of the board in order for your components now to fit your new stack up, which is okay. I imagine that they know exactly what they're doing, but at least that's what I think is going on, that they're all embedded in the intermediate layers. Now everything else, all the selectors between the filter banks are all solid state, and they're all these little Hittite components that you see all around here. And the signal coming in, and you can see these are all the three-way switches, and then going into over here, and then going through the filters, and here's a doubler here from mini circuits, here's another doubler there from mini circuits. So the signal is selected between which path you want it to go through, which filter path, which are these ground stitching reveals them, and then selected again, and then goes to doubler again, select which filter path, and doubled again. So the overall signal, we have a reference coming in, which is from the dielectric resonant oscillator. This is a clean reference, 4.8 gigahertz coming in over here, goes through here, then it goes through some amplification. Over here again becomes some more amplified or differentially to signal that converted, and then goes over here. In this appears to me to be the fractional element controller. The output of that then goes over here and controls the VCO. So, and the output of the VCO then goes over here, gets doubled and so on and on, doubled and filtered, and comes out of here. So the signal path is very nicely visible through the PLL. It's very nice and clean, and you can see the FPGA Spartan 6 over there in the middle, a whole bunch of DC-DC converter sections scattered all over the place, all of them individual compartments of signals so that they don't contribute to noise from each other, and they put the VCO in the corner as they should. And if I were to flip it upside down, you can see exactly the same thing at the back. You can see all the ground stitching openings for what I believe where the filters are, and everything all looks pretty good. I didn't see any of the filters under, that's why I'm guessing that that's where they are, and I mean, these shapes are pretty revealing, at least to my eyes. The interesting thing is that there is another chip that appears to be another fractional controller, which is kind of unusual, sitting over here. I'm not sure why that is there. It doesn't show up in the datasheet, but it may be that simplified, or that, you know, we're making some assumptions on this board anyway. But other than that, looks fantastic, and pretty happy with it. Again, great A quality as to be expected from Keysight, and especially from such an expensive instrument. So it looks wonderful. There you go. This was a pretty extensive teardown of the few boards that we had. Luckily, they only sent me 3, otherwise this portion would have been 4 hours long. But don't worry, we got lots of cool experiments. I hope you stick around to watch, and let's go get to our fancy experiments. Alright, this was a close look at the block diagram and the teardown of a couple of the important modules. Luckily, they only sent me 3 modules, otherwise this teardown would have taken 2 hours on its own. But now that we have a good idea of how the instrument operates internally and we've taken a look at some of the critical blocks, we can now go and do some experiments with it. So let's move on to the next section. And here we have the front panel of the EXA signal analyzer by Keysight, and it has a very recognizable spectrum analyzer look to it. If you've ever used any of the Agilent or even the HP spectrum analyzers, you're going to feel right at home because the button configuration and the grid configuration is very consistent and has been refined over time to be able to give you the quick access to everything you need. Now the biggest part of the front panel is obviously occupied by the LCD screen. This is a very sharp, very crisp, really bright LCD screen, and it doesn't have a touch screen.
SOPA Society Pass halted on a circuit breaker, Sandy Oscar Papa Alpha.
Very heavily, so the instrument is designed for interaction with the
$11.73 SOPA.
On the right side, the power probe connector, which is a mandatory connection there. You have the headphone for audio demodulation. You have 2 USB ports, and at the very bottom of that, you have, of course, the RF input. Now, on a 26.5 gigahertz spectrum analyzer like this one, this is going to be a Type N connector, and here I've put a Type N to K connector converter there so that we can be SMA compatible and be able to switch things in and out very quickly. You also have this bunch of buttons up here, which are your analyzer setup. This is going to be the frequency, the vertical amplitude, the detector type, the source control, resolution, bandwidth. All the main controls of the spectrum analyzer configuration are right over here. This is what you're going to be interacting with the most. At the bottom of that, you have the measurement section. Now, for depending on what application is loaded, the measurement, the mode, and the setup of that is going to give you all the necessary settings and configuration for that application. And this has been kept consistent no matter what you load. So phase noise, noise figure, or any of the other types of wireless standards that you load, you're always going to be able to configure and find what you're looking for with this. And they've done a really good job of keeping that consistency so that you never get lost in the hundreds of menus that are available. On the right side of that, you're going to have your marker, which we're going to talk about later, and then the utility buttons, which, system configuration, loading files, saving files, and so on, are going to be handled there. The trigger, restarting, and doing a single or continuous measurements are here. All the entry button keypads over here with the directional pads right above it. The rotation knob here, of course, also available, and a few other buttons which aren't used as often. Some of the applications still take advantage of them. All the soft buttons on the side of the screen are, of course, going to be there, which is going to be depending on what is displayed on the screen. Your window management, maximizing, minimizing, and swapping windows, the volume control for the built-in speaker, and the help button, which can be very handy. Other than that, it's really straightforward. And the top right is where we would have had the external mixing capability. Unfortunately, as I mentioned, the 26.5 gig version of this instrument does not support that. Only the millimeter wave does, and that's unfortunate because you should be able to, in theory, use it. Perhaps there's an LO configuration that doesn't allow it, but I don't see why they have omitted that. On this panel over here, which is empty, normally on the higher end spectrum analyzers like the PXA, you're going to be able to have your baseband inputs directly here, so you can actually feed IQ inputs into the baseband analyzer, which this instrument also does not support. None of the models of the EXA support that, but if you jump up to the higher models, you will be able to add that to that instrument. Let's go ahead and take a look at the back of the unit. In the very center, of course, we have the main motherboard, which houses the CPU as well as the Windows operating system, and you can see some typical interfaces from that Windows machine. We have GPIB and LAN, we have VGA. There is no DVI port yet because these type of motherboards take a while to be upgraded to the latest interfaces, so we're still stuck with VGA here. We have host USB ports, 4 of them at the back, and a device USB port, so you can connect this to an external computer so that it can be controlled via USB, and LAN, of course, serves a similar purpose. At the top left, we have the external reference coming in and a 10 MHz reference coming out. These 2 ports are available independently from each other, and then we have the SNS series noise source or the 28-volt drive host for the external noise sources as well. So if you have a smart noise source, this would obviously be the way to go, and I have one of those, so we're going to try it out. For the rest of the BNC connectors, we have 2 trigger inputs, 2 trigger outputs, and a sync port used to synchronize and trigger external instruments or trigger the spectrum analyzer from an external event. Then there's the analog output port, which may be configured as like a video output or directly the demodulated audio if you have those options installed. And then there's the digital bus, which is an expansion port for other things. I don't have anything that connects to that right now. There's the power line coming in and the auxiliary IF output, which is the wideband IF output exceeding 100 MHz of bandwidth, and we're going to take a look at that hopefully in one of our experiments once we get it working. So this is at the back, pretty straightforward and exactly what you would expect from this instrument class. Now, even
even though this instrument runs Windows 7, and normally that computer itself boots very, very quickly, because of all the application that's loaded on this particular model, this is a fully loaded one, it has everything on it, it actually takes quite a bit of time to boot up. So this is not a type of instrument you're going to turn on and off in between your measurements. It's something that people typically leave on, so I'm not going to wait on camera for it to boot up, but it's going to have to go through the all the applications preloaded, and it's going to go through all of its internal alignment for the first time it starts up, and that's normal for all the spectrum analyzers. Here we go, we're all up and running. Now in order to capture the screen, instead of filming it directly, I'm going to install the screen capture program to run on the spectrum analyzer directly. And that's going to be quite helpful because I think it's going to improve the viewing experience, since it's very difficult to get the focus and the lighting correctly this way by filming the screen. Also what I've done is I've
SOPA, Society Pass shares resume trading now. Sandy Oscar Papa Alpha, SOPA, $12.76.
Directly, and as well as the fact that I've connected the triggers to
Up about 14.5% now, SOPA.
which they can communicate and start and stop measurements quite significantly, and you will see that in action. Now, instead of just showing you all the different things on the spectrum analyzer, I have devised a very elaborate experiment which we're going to go through, and in the process of that experiment, we're going to SAIA partners with Daimler Trucks North America to test electric box vehicle. That's Sandy Alpha India Alpha, SAIA. And take it apart and look at it one step at a time and really understand what's going on. So let's take a look at our experiment setup. Now this is going to be a wireless transceiver with a sliding IF with a super heterodyne architecture. So let's take a look at it one step at a time in order to understand what it is that we're going to be testing. Our transmitter starts with an arbitrary waveform generator, which is connected to a single sideband mixer. Now that's going to bring our spectrum to a frequency around 500 megahertz. Now I want to bring that even higher in frequency, so I'm going to use a double sideband mixer connected to a PA, which then ultimately drives an antenna. Now this mixer is going to require its own LO, and that LO is going to come from a 6 GHz PLL. Now this configuration implies that if I use a 6 GHz PLL here, I'm going to have spectrum on around 6.5 GHz and 5.5 GHz coming out of the PA here. So I want to receive that now. And on the receive side, I'm going to have again an antenna, a low noise amplifier, and another double sideband mixer right over here. And of course, that's going to require its own LO signal. But since this is a sliding IF configuration, we're going to use an EXG vector signal generator from Keysight, whose output is connected to a doubler and then amplified before fed into the mixer. So now the output of that can go back onto a single sideband demodulator right over here, and then we're going to get our I and Q signals back at the end. This is itself going to require an LO signal, and that's going to come from another PLL that's going to run at around 1 GHz. Now, if you notice, what is missing in this setup is that we don't have any filtering, and of course that means that we're going to have a whole bunch of spectrum in the frequency band which we may not want, and that's going to be something we can take a look at, and we'll see the consequences of that as well. Now, where does the EXA fit into all of this? Well, every single one of the components in this setup needs to be characterized in some way, and the EXA is capable of doing that. So we're going to take a whole bunch of different components and we're going to characterize them using the EXA so that we can understand their performance, and each of the performance of these components obviously is going to impact the overall link budget and the system performance of this transceiver. So there's a lot of different things I would like to test. And we're going to start with something very simple, and then we'll take apart this setup one step at a time and characterize each component, and there's a lot of really cool and interesting things that we can learn from that. So the first component we're going to characterize is going to be this frequency doubler, and right now I have it connected to the EXG at the bottom and connecting the output directly to the EXA. And just to remind ourselves, that's the doubler that's going to be used on the receive side on the double sideband mixer. So let's go ahead and take a look at what happens when we put some signal into it and how we can use the combination of the EXG and the EXA to characterize it. So let's jump to the screen. And here we're looking at the spectrum of the spectrum analyzer, of course, and I don't have the EXG enabled yet. I have set the EXG to be at 3 GHz with an output power of 0 dBm. Let's go ahead and turn it on. And there we go, and you can clearly see the main tone coming out of here. This tone is going to be at 6 GHz, and this is the feed-through tone. Normally you don't want this in a doubler. You want that to be as small as possible so that you can have a clean double tone, and of course that's not quite possible, so you're going to have some feed-through. Now if I go ahead and press the peak search function over here, you're going to see that the instrument will report, of course, the maximum peak, and at my
minus 27.3 dBm. Now I can go ahead and increase the power into the doubler from my synthesizer down here, and you can see as I increase it, we're going to get stronger and stronger fundamental tone. Now I'm at 6 dBm, and you can see we are also going to see the third and the fourth harmonic to start coming up, and we have some rejection of the fundamental, and we'd like to characterize that. Now I can also go ahead and change the frequency. So right now, as I said, we're at 3 gigahertz. Let's go, for example, to 3.5 gigahertz. You can see all the tones will move and synchronize with each other, as to be expected. But if I want to characterize this doubler, I don't want to sit there and put every single frequency and then measure the tones. Well, since we have the EXG directly connected to the EXA, we can actually use the EXA's source control functionality to do a characterization of our doubler. And we can do both the fundamental and the double tone because we can do offset tracking from the source control. Let's take a look at that. So let's characterize the fundamental feedback.
Marijuana moment tweeting. GOP lawmakers file bills to streamline research into marijuana, psychedelics, and other Schedule 1 drugs.
I can start the frequency at 2 gigahertz, and I can stop the frequency at 4 gigahertz. And of course, now we're going to be able to see our fundamental tone right here in the middle. Now let's go ahead and turn off the synthesizer for a moment and configure it in the source control option. Now if I click on source or press the button right over here, you can see all my source control here. Now the source has already been selected right over here, and it's actually listing it as an MXG, which is unusual because this is
Letter F, Teslarati says Ford implements stop sale order on Mustang Mach-E over seatbelt issues.
See that the connection has been verified. So we have our source control nicely up and running. Now,
that's letter F.
The fundamental frequency. So the same frequency going in and the same frequency coming out. And if I click on frequency here, it gives me the option to do an offset tracking. Now here I can do a multiplication on the numerator and a multiplication on the denominator. So obviously 1 over 1 is 1, which means that it's going to track the EXG 1 to 1 with this start and stop on the RF frequency at the bottom, which is exactly what we want for the fundamental frequency. Let's go back to source. Now what about the amplitude? Well, we're going to operate this multiplier with quite a large input signal as it is required for passive multipliers like this. So we're going to go ahead and change the amplitude to 10 dBm. So now it's going to put a constant 10 dBm into the multiplier. Let's not worry about power sweep. We're going to use that later for something else. We're going to go back to source. Now everything looks good. Obviously it's turned off, so you can see that the source mode is off right now. And I'm going to go ahead and turn the RF output on. Now the first time you're going to turn it on, because it has to synchronize and it has to reset the source, it's going to take a couple of seconds for it to do that. Right now it's resetting the EXG and configuring it with everything, and there it is, it's up and running. And this trace that you see over here is the actual measured output power at the fundamental tone while the EXG is sweeping the input. So basically it's a tracking generator now. Now you may ask, well, how do you know this power is accurate? You didn't do any calibration, you didn't do any normalization of the input, because normally you would want to connect the output of the EXG directly to the input of the EXA and then do normalization. Well, I skipped that step because we don't care so much about the accuracy of this power. But don't worry about it, you can easily do it. In fact, there is a very nice way to do it. If you click on trace and detector and you continue over here, you can see that there is a normalization option. And if I click on normalize, in fact, you can do a proper open short calibration. And if you click that,
LSPRU, Lake Spur Health Acquisition shares opening at $9.99. IPO priced at $10 per unit. That's Lima, Sandy, Papa, Romeo Uniform, LSPRU.
And if I go back to the frequency, what this is telling us is that if I put a 10 dBm signal into the multiplier, I'm going to get about minus 30 dBm output power, just a little bit higher than that. So we have roughly about maybe 40 dB, maybe 35 dB of fundamental rejection. And that's nice and great, but this doesn't tell us how good the multiplier is performing, because the actual rejection is going to be the power coming out of the double compared to the fundamental. So we still need to do another test to figure out. We can do exactly the same thing, except now do an offset tracking, so we should be able to see what the efficiency of this multiplier is. And
FSR Fisker tweeting.
The trace on the screen if you want to, and compare it with the next measurement, but it's going to be easier this way.
Fisker says we're excited to announce our partner Bridgestone will provide after-sales services for Fisker customers in France and Germany.
The other parameter. Just one other thing I wanted to point out. Look at how fast this is. I mean, we're sweeping.
That's Foxtrot Sandy Romeo FSR.
And the synthesizer is doing a tracking generator with everything connected at just under 0.3 seconds. So it's really, really responsive, which is very important if you're going to do lots of points and you're going to keep doing different measurements that have a dynamic behavior. So let's go ahead over here. Let's turn our source off. Since we don't need it anymore, obviously the trace is going to drop because we don't have anything anymore coming out. And I'm going to turn the tracking also off. This is going to now reset the synthesizer, so now we can go and get back to our normal spectrum exactly like we were doing before. So let's go over here now under frequency and change our denominator by a factor of 2. So this means that now the input is going to be at half the frequency of what the RF frequency is shown at the bottom. This is exactly what we want because we want to measure the doubled frequency. So now I also have to go ahead and change my start and stop frequency. Now we can go from 4 gigahertz and we can stop at 8 gigahertz. Now we're going to be looking at the doubled output. Let's go back to the source control once again and let's go ahead and turn it back on. This is the same input power as we had before. It's going to put 10 dBm into it again, except it's going to look at the signal between 4 to 8 gig and the input between 2 to 4. Now it's resetting the source one more time, and there we go, and check it out. We have a much better response than we had before. So you can see that there is a little bit of a ripple, and that's most likely due to some impedance mismatch. The output of this multiplier, which is on just a very cheap, inexpensive PCB, but then we get a much better flat response. Now if you look at an average value here, let's put a marker on it. Right here in the middle, you can see that I'm getting minus 5 dBm. So I'm putting 10 dBm in, I'm getting minus 5 dBm at the doubled frequency, and I was getting about minus 30 at the fundamental. So we have roughly 25 dB of fundamental rejection in dBc compared to the doubled frequency. And this is very useful. I just managed to very quickly find out exactly the behavior of this doubler to give me an idea of what kind of rejection I can expect. This will tell me whether I need a filter or not, and other system parameters will depend on that. But then you may ask, well, how much power should I put into this doubler? Is it worth to keep putting more and more power into it to get more and more power out? At what point is it not worth it anymore? Well, for that, we need to do a power sweep and not a frequency sweep. And in fact, we can easily do that using the source control as well. As I mentioned, we have power sweep capability. So now we're going to choose a center frequency, and based on the center frequency, we're going to do a power sweep so we can see the efficiency of this doubler as a function of input power now. So let's go ahead and do our power sweep. First, I'm going to turn off the output of the RF source one more time and disable the tracking. And now I want to characterize the doubler at a fixed frequency, and I'm going to do that at 6 gigahertz because that's the frequency that I'm interested in running the double sideband mixers on. And we can do that by making sure that the center frequency is indeed set to 6 gigahertz, and it is. And we're going to change our span to be 0 span. So now the x-axis of the spectrum analyzer is in time and it's not in frequency anymore, continuously measuring the power at 6 gigahertz. Now let's go and configure the source. Under source, we're going to go under amplitude. Let's change the starting amplitude to minus 10 dBm. So it's going to start sweeping the power from minus 10 dBm. And how much is it going to do? Well, here I have entered the power sweep range, 35 dB. So it's going to go from minus 10 dB and plus 35 is going to be 25 dBm. And 25 dBm is no problem for the EXG because I have the high power option installed on the EXG that I have here. So let's go ahead and enable the power sweep. Let's go back and check one other thing. Let's change the frequency, and you can indeed see that we have 1/2. So the EXG is going to stay at 3 gigahertz and sweep the power from minus 10 dBm to 25 dBm, and the EXA is going to plot the input-output power relationship, which is exactly what we want. Let's go ahead and enable it once again, and based on that plot that is going to be generated, we can decide how much power we want to put into our multiplier in the final system. Now it's doing the reset on the EXG one more time. I'm not sure why it has to do the reset each time. Oh, and we're actually going outside the screen, no problem. Let's change the input level all the way to 10 dBm and check it out. This makes perfect sense because it means that at very low input powers, remember here at this left corner we're at minus 10 dBm, and here at the right corner we're at 25 dBm. So at the very, very left, we are getting basically a very linear relationship between input and output power.
MPC, Marathon Petroleum, the April $65 call sweep, about 1,300 contracts on that. Michael Papa Charlie, MPC.
On this, and I go over here, I can see that, well, for a reasonable input power, under 20 dBm, around 50 dBm or so, I can get almost 2 dBm out of this multiplier. But that's not enough for a double sideband mixer, and this tells me that I am indeed going to need to put an amplifier after this multiplier to really be able to take the most out of it. And all of that in one setup. I haven't touched the setup at all. All I've done is just pushing the buttons on the spectrum analyzer. And one other thing to note is look how fast it sweeps. Again, we're sweeping from minus 10 to 25 dBm at 201 points, and it happens in about 0.1 second. It's very, very quick, and I appreciate it because if you're doing a lot of measurements, the last thing you want to do is wait for a slow instrument. So I think that's pretty good. Now we can move on to our next module. And here, for the sake of completeness, you can take a look indeed at the EXG sweeping. You can see that it is fixed at a 3 GHz frequency and it's on remote connection, and the power being swept. Now obviously this is not going to show you as fast as it is sweeping because the display doesn't update as fast as that, but you can clearly see that the system is exactly like it was when we started, all in one place. So the next component I like to characterize is this LNA. This is a broadband amplifier, and it's supposed to have simultaneously fairly good noise. So I'm going to try and using it as an LNA. Now because it's so broadband, I don't expect this noise figure to be very good. It's not going to be something like a dB. It's going to be much, much worse than that, but nonetheless, it might be good enough for this application. So we would like to characterize that. Now, in order to measure the noise figure of the amplifier, I'm going to use this SNS N4002A noise source from Keysight, and this is a noise source that goes from 10 MHz to 26.5 GHz, and it has an ENR range of about 12 to 17 dB. And the nice thing about the SNS noise sources are that all the ENR table values are stored electronically inside the noise source, and as soon as you connect it to the instrument like I have here, all the ENR table values will be downloaded into the spectrum analyzer, and you don't have to do that manually. This is a big advantage because that's a very, very annoying thing to have to do each time you connect something, and sometimes table gets lost and you could enter it by mistake. It also has temperature compensation built into it. The SNS noise source like this one, the 26.5 peak one, is about $4,000. So we can go ahead and use that to measure the noise of our LNA. Now, as to remind ourselves, the LNA sits right over here, and then it's going to be followed by a double sideband mixer. So I'm also interested to measure the noise figure combination of the LNA and the double sideband mixer, because this will tell me how much of the noise figure of the mixer is still visible after the LNA is connected, if the LNA gain is not high enough or its noise figure is sufficiently low, for example. So that will be one thing that I'm very interested in figuring out, and those are the two things we're going to do using this noise source. Now we have to set it up, of course, and connect it to the instrument and go through the calibration process, but let's go through that and see how the instrument handles how easy it is to measure this type of noise sources using the EXA. So let's go ahead and configure the EXA for noise figure measurement, and we can do that by pressing the mode button and select the noise figure application. Now this has a lot of applications built into it because this is a fully loaded unit. You can see there's 6 pages in here. We're going to continue down the pages until we see noise figure, and here it is. Here's our noise figure application. We're going to click on that, and there it is. It switches to the noise figure application. You should notice how fast it is, and this is because all the applications were loaded at the time of startup, and you can switch back and forth between them very, very quickly. Now obviously this noise figure measurement right now is meaningless because the unit is not calibrated. You can see that the calibration is invalid right now. Now what is the range of frequencies I want to measure? I've already entered that. I'd like to measure this amplifier from 500 MHz all the way up to 8 GHz, and that's actually going to operate at around 6 GHz, but this is going to give us a very good view of its noise figure as a function of frequency. Well, now that we have this input frequency, how do we calibrate this system? Well, let's just check a couple of things to make sure everything is in order. Let's make sure that the noise source is working. If I click on the ENR, you can see that I can go under noise source setup, and in fact the noise source has been selected. It's an SNS noise source and it's been detected, and all the ENR table has already automatically been loaded into the instrument. I don't have to worry about any of that. That's great. Now let's click on mode setup, and under mode setup we can go under DUT setup, and here the instrument would tell us what we need to do in order to do our calibration and to do our measurement. So it's showing us this view here. It's saying if you want to calibrate the instrument for an amplifier measurement, remember our DUT is an amplifier, you can select other things, and we will do that later. And if you want to just measure an amplifier but at the same input-output frequency, it's really straightforward. Just connect the noise source to the input of the EXA and then calibrate. And if I want to do the measurement, well, you're going to have to insert your DUT between the noise source and the instrument itself. So it's really, really straightforward. Now that we know how to do this, I've already done that. I'm already in the calibration mode. I've already connected the noise source to the input of the EXA. Now we can go under measurement setup, and we can actually click calibrate. Now, there's one other thing I want to make sure. Yeah, I just wanted to make sure that we have enough points. I have set 25 points, so it's going to do 25 points between 800 to 8 gigahertz, which is great. Now back to measurement setup, and I'm going to click on calibrate. Now it's asking me, are you sure you want to calibrate? Indeed I am. Now it's going to go through the calibration, and it will go through different frequencies, and it's going to de-embed the impact. Oh, interesting. That actually failed. It's never failed before. That's unusual. Let's try it one more time. I wonder why it failed. Maybe a bug or something wrong with the application. It never happened before. Here we go. Now it's working. I'm not sure what happened there. I didn't change
BB,
it.
BlackBerry,
Anyway,
BlackBerry
so, you can
at
see
the
that
highs
this
now,
is how
$9.33, up 5%. Seeing the
wherever it's connected between
March
noise
$10
source
call sweep now on BlackBerry BB.
you can see
Bravo,
that we're
bravo.
basically sitting at the error floor of the noise figure personality capabilities. It's telling me that the gain is 0 dB, which is correct. It's saying the noise figure sometimes goes below 0, but this is within the accuracy of the unit. So we have no problem over there. We can go ahead and now disconnect the noise source from the instrument. And if I do that, obviously the noise figure is
Kellogg's out with a press release now about new 5-year agreement for USRTEC employees, letter K.
to connect the amplifier between the units. So let's take a look
Kellogg.
at how we can do that. And here is our measurement setup. The noise source connected to the input of the LNA, the output of the LNA taken directly to the input of the EXA. So everything is ready, it's not plugged in yet, and as soon as I apply power, we should be able to see the effect on the noise figure. Let's take a look. So let's go ahead and apply power to the LNA and see the effect on the noise figure. Here we go. It's plugged in, so the instrument is going to automatically auto-scale everything, and there it is, it did that. And I've already placed 2 markers on the noise figure and the gain. Now if you look at the gain of this amplifier at the very low frequencies is about 37 dB, which is exactly what it should be. This is correct. But this gives us confidence in our noise figure measurement. Now if I continue, you can see the gain is dropping linearly with dB, roughly, and then there's a notch in the frequency response. And that notch in fact is real. It's a problem with the output matching network of this particular LNA. So at about 6 gigahertz, we have 18.2 dB of gain. And if you look at the noise figure is pretty good at low frequencies, just under 3 dB. And at the frequency of interest at around 5.8 gigahertz, the noise figure is in fact around 4.7 dB, which is not that great, but it's also not terrible. It should be able to do what we want with it. Now the question is, how is the noise figure of the system going to be affected by the mixer? And then the only way to do that is to connect these guys together and find out the effect of this mixer on the noise figure of this LNA. The other thing to note is that the input, the gain drop here, this notch does not show up in the noise figure, and this is indication that this notch is emitted from the output matching network and not at the input. Otherwise, you would have seen that added to the noise figure. So everything looks good, I would say. Now we can move on and try and measure the combination of the LNA and our mixer noise figure together. So now our setup is becoming more complicated. Now I'm going to measure the noise figure of the mixer along with the multiplier and the LNA, and that's going to be our noise figure of our receiver, pretty much very close to what it's going to be in the final setup. So let's take a look and see what's going on. The output of the EXG, which is our synthesizer, goes through the doubler, then goes through an amplifier, and the amplifier output is going to be the LO signal. This means that the synthesizer only needs to sweep at half the frequency because we have a doubler. And the output of that goes directly to the LO of our mixer. And I'll show you the mixer a little bit closer. The mixer is an Avantech mixer which works between 2 to 8 gigahertz. And the input, RF input to the mixer comes from our LNA as to be expected.
PPG announcing $2.7 million investment for powder coatings expansion in Brazil. That's Papa Golf PPG.
So we're getting closer to the final system. Now we can go and take a look at the screen to see what's going on. Let me just give you a quick close look here as well, so you can see that indeed we have our mixer and LNA connection made and the LNA has been turned on. So if we go and look at the screen, I can show you how the instrument needs to be configured in order to be able to do this measurement. And here we are back again at the DUT setup menu, and you can see that once I've chosen the down converter option here, this DUT has been updated to show us what the down converter noise figure measurement setup should look like. And indeed, it's very straightforward. We have the noise source again connected to our mixer and the LO being applied to the DUT and the IF then taken back onto the EXA. And here's a spectral view of what that's going to look like. I'm measuring the upper sideband noise figure here. I'm not going to go into too much detail with the differences. I'm assuming that if you're watching this that you're somewhat familiar with these concepts already. And I'm doing a sweep on the LO frequency, which means that the RF frequency can also be swept. And this is going to result in a constant IF frequency. I've chosen an IF frequency of 333 megahertz. This is the first stage of the super heterodyne down conversion of a receiver, so this is a good frequency, roughly where we want to use it, so we can start with this. It's not a problem. And since our RF is swept from 5 gigahertz to 7 gigahertz, right around the frequency we want to use the receiver as, the LO can be swept between these two frequencies. But let's not forget that we do have a multiplier, which means that the LO should run at half this frequency. And in fact, we can easily set that up also, because the LO is going to be provided using the EXG. The noise source personality can also control an external source, and in fact, this is exactly what's going on. And if I go under mode setup, and if I go under external LO setup, and I can go ahead and change the LO setup here, you can see that I've chosen the LO power to be 10 dBm, and we know this from the previous measurement we did where we measured the multiplier's efficiency and so on, and I have set the LO to have a multiplication factor of 1/2. So it's going to sweep the LO at half the frequency of the RF, exactly as to be expected because we have a built-in doubler. Now if I go under measurement, everything's taken care of, and I've done a measurement right over here, and you can see that the gain is lower than it used to be, and that's correct because this mixer is a passive mixer and it's going to have some conversion loss, and around this frequency you can see that we have a couple of dB of conversion loss. We're at about 60 dB of gain, and the same dip that you saw in the frequency responsive of the LNA is still present here as it should, and the noise figure luckily hasn't been much affected. We're around about 4.7 dB, 4.8 dB like we were before, except for the fact that we have a little spike over here which I could not get rid of, and I suspect it has to do with the interaction between the mixer and the LNA. You can see it lines up right over here when the output of the LNA is not very well matched, and I suspect that because the input of the mixer is also not very well matched, that there is going to be some interaction and some problem rising. But this is exactly the type of result you're looking for to find potential problems, and now you can go back, measure these components individually, and potentially find what's going on and correct it. But for the purposes of this experiment, we know that this is going to be a fairly reasonable receiver. It's not earth-shattering or anything, but nonetheless we can easily measure it. You can see the software is definitely designed to allow us to do this very quickly. So now that we have this portion, let's now turn our attention a little bit toward the transmitter and see what we can do over there. Now if you recall, the very first stage of our transmitter is a single sideband block here, which has a built-in arbitrary waveform generator giving us our first stage of up conversion. And for that, I'm going to use this SignalHound VSG25A, which is basically that block built into a box that you can program and configure from your computer. And this thing works from 100 megahertz all the way up to 2.5 gigahertz, and we intend to use it around 500 megahertz or so. So there's a lot of stuff that you can use the EXA for to characterize this alone. And we're going to take a look at some of those things to get an idea of how well this thing actually performs. And once we have characterized this, then we have a fairly good idea of what the starting point of our transmitter is. So as we go along the chain here, we can see the degradation of the signal due to the impairments of all the other blocks. So let's go ahead, hook this up to the EXA and turn it on and see what we can do with it. Here we go, I've gone ahead and connected the VSG25A directly to the EXA, and I've actually reviewed SignalHound products in the past, so I recommend that you go and check them out. I was impressed with their other products, so now we're going to characterize this. And this is also a USB controlled instrument, and it has its own software that runs on the computer. So let's go ahead and launch the software, see what kind of stuff we can do with it, and then that will help us to plan out how we're going to characterize it using the EXA. And here's a quick look at the software for this vector signal generator. I'm not going to dwell on it too much. I apologize for filming the screen. I just wanted to show you where I will be controlling the unit from. So I'm going to use this to generate multi-tones as well as various constellations, so we can use the EXA to characterize the performance of this vector generator. So let's go back to the EXA and see what we get. Now, since we intend to use the SignalHound vector generator at around 500 megahertz, it makes sense to start by looking at the signal at 500 meg. And that's exactly what I've done. I've configured it to generate a tone at 500 meg, and let's go ahead and enable that tone. And the power is set to 9 dBm. So let's increase the amplitude over here to 10 dBm. And you can see that this vector signal generator actually puts out quite a lot of tones outside of its own main fundamental tone. So it might be good to put a filter after this before we feed it to the double sideband filter, in order to make sure that these tones don't interfere with the double sideband filter's performance, because they are still within its bandwidth. So let's go ahead and change the frequency span a little bit. look at only the frequencies that we are interested in, and up to 5 GHz you can see the tones there. Now I've also configured the instrument to generate 2 tones at 10 MHz apart, centered at 500 meg, in order to be able to measure the output OIP3 performance of the vector modulator. And I can go ahead and enable that as well. And as soon as I do that, we see a whole bunch of other tones indicating further that indeed having some filtering would be beneficial. Let's focus a little bit closer at around 500 MHz. So I'm going to put a center frequency of 500 MHz, and I'm going to change the span to be small enough such that we can begin to see the tones. There they are. And let's reduce the resolution bandwidth to 30 kHz. And look at how fast this instrument is. I mean, we are spanning 100 MHz with a 30 kHz resolution bandwidth and video bandwidth. It only takes 2.7 milliseconds, which is great. Very fast. I really like that. And of course, if I go ahead and do a peak search, you can see that one of our main tones is at 495, and then the other one, I can click on that, and let me just actually move it. Where are we going around? Should be. There it is. Oh, it's very hard to get it. Come on, you can do it. There it is. 505 MHz sitting on these 2 locations. So it sounds perfect, and we can see our intermodulation products. Another thing to note is that it's asymmetric, and it has to do with the phase of the internal DACs as well as how the frequency planning architecture is. But this asymmetry can be sometimes problematic, but you can see that our lower sideband doesn't exactly look like the upper sideband. So now I want to calculate the third order intercept point. Well, there are a lot of built-in measurements into the EXA, and you can see a whole list of them over here, and there is also a second page, and there is a built-in TOI. So if I go and select that, the instrument actually resets its x-axis and vertical axis and so on, which can be a little bit annoying. So let's go ahead and change the reference amplitude to 10 dBm and reduce the span once again so we can see our tone, reduce the resolution bandwidth down to 30 kHz, and the instrument automatically picks our intermodulation products and our main tones and does all the calculation for us. And it's saying that the third order intercept point is about 25 dBm at the output, which is not too bad. It's reasonable, and you can see that our third order intermodulation products are 40 dBc below the fundamental. And this gives us some really important information about how the system will behave in the presence of modulation, which is what we are interested in using. So if I go ahead and now reconfigure the vector modulator for to produce a QAM modulation, we should be able to observe that as well. And that's in fact exactly what I've done. I'm going to go ahead and enable the modulation. Now the modulation is going to be a 64 QAM at 25 mega symbols per second with a root raised cosine filter coefficient of 0.35. So you should know exactly what that looks like. You can go ahead and apply it, and there it is. Now let's get out of this measurement capability because we don't want to do this inside this measurement. Let's go back to the spectrum analyzer, and you can clearly see our spectrum centered at 500 MHz with the modulation on top of it, and the third order modulation products on the sides are going to occupy the adjacent channels. Now we can go ahead again and use some of the built-in functionality to measure some of the properties of the spectrum. If I want to find out how much power is being transmitted in this modulation, I can do that by using the measurement function channel power. Now I've already configured channel power by entering the center frequency and the integration width that I'm interested in, and you can see that it's integrating over a 35 MHz bandwidth, and it's saying that the power is 8.1 dBm, which makes sense. I'm transmitting 9 dBm, and there's some losses and so on involved, and the power spectral density is also given to me. I can also go under display and enable the bar graph so you can see exactly the portion of the spectrum that's being integrated. And this is an important measurement, obviously, because you want to know how much power you're going to transmit. Well, and how much bandwidth am I occupying with this transmission? Well, we can also measure that really easily by clicking on measure and going to occupy bandwidth. And you can see that I've already configured this as well by centering it at 500 MHz. And you can see that it says that the occupied bandwidth is 29.2 MHz, and that will include 99% of the total transmit power, and it matches the measurement we were doing before. It also tells me that at a 30 dB drop, so 30 dB below the main power transmit, you can see that I'm occupying 33.8 MHz. All of these are configurable, obviously, through different measurement setup configuration. So if I go ahead and change my modulation filter at the vector generator, instead of having a 0.35 alpha for the root raised cosine, and I go to 0.22, I expect the occupied bandwidth to get smaller. Let's try it out. There you go, and indeed you can see that in fact it does go down. So it is perfectly consistent. You can quickly do these measurements right on the spot. So how much power am I putting out in my adjacent channels that you can see here, and that's of course undesired. Well, I can measure that too because we have adjacent channel power measurement, and I've already configured it, and there it is. You can see that I'm measuring the channel of interest, which is my channel. There's some guard banding between my channel and the adjacent channels, and it is calculating the total power in the adjacent channels, and it's giving it to me here in the table. And since I have only one carrier here, it's doing it only for one carrier, but you can do it for as many carriers as you want. And not to mention that you can actually give it a radio standard. Any of the radio standards that are currently used in the industry, you can configure, and then it will do all the settings for you, which can be a huge advantage. Since this is a completely custom carrier, we're just doing something ourselves. That's why I've configured it manually myself. Now, because I'm putting out so much power in the adjacent channels, I can go ahead and reduce the transmit power so that the nonlinearities don't generate so many intermodulation products. So I'm transmitting 9 dBm. Let's go ahead and transmit 3 dBm instead, and take a look at what happens. You can see that in dBc, we have our adjacent channel power significantly improved, and this is to be expected. So perhaps maybe this is where we want to operate to avoid putting out a lot of emissions in the adjacent channels, and this would be a good start. And well, now let's get serious. Let's go ahead and launch the VSA software from Keysight, which this instrument natively supports, and see what it looks like. Now I've already loaded the VSA and configured it so that I don't have to show it on the camera here, but I want you to see how fast it is. So everything is already loaded, so I can press mode and I can say I want the VSA, and it just comes right back up. And look at how fast it is. I mean, this is direct hardware access. I am analyzing 4096 symbols of the 64 QAM constellation, and I'm doing all the calculations, everything live here on the screen while simultaneously doing a screen capture, and it is ridiculously fast. And of course it's because it's directly connected to the baseband processor board that I showed you, and the performance of this vector signal generator is not too bad. You can see here at the bottom left, I'm looking at the spectrum centered at 500 megahertz, and I'm looking at a power of 2 dBm because I reduced my power transmitter to 3 dBm from the instrument to reduce the adjacent channel power as we just saw. And here's our constellation. Looks really clean, and here is our EVM as a function of symbols. You can see I'm stopping at 4095 or 96 symbols over here, and this shape of it, there's a reason why this shape is present. I'm gonna let you think about that. You can talk about it in the comment section, but there's a very subtle reason why this happens. And if you look over here, this is our modulation performance, and if you look, we have an EVM of 1% and an SNR of 40 dB. For 64 QAM, an SNR of 40 dB is just essentially error-free. So this is a completely error-free transmission, very clean constellation coming from the VSG25A. Pretty impressive. And you can see the effect of the noise, phase noise on this is completely non-apparent at all, because the phase noise at 500 megahertz for the VSG25A is very low. And I can go right back directly to the spectrum analyzer, and it just comes right back up. It's pretty convenient. I really enjoy the fact that you can jump back and forth so easily between these softwares, and it's up and running for you. So now that we have this, and we know that the phase noise is not a problem at 500 megahertz, but there's no guarantee that it's not a problem at 6 gigahertz, because we still have to have a PLL to drive our double sideband mixer, which follows this. So now let's go and take a look at the PLL and characterize its phase noise. And here's a look at the PLL we will be using. This is a product from Hittite. It's an HMC 700 series product. It's actually a 2-chip solution where you have the PLL core in one IC and the VCO in a different one. And you can see the block diagram right over here. We have an external VCO, and the loop filter is of course also external. The phase frequency detector, all the different fractional dividers and prescalers and so on are what's on the PLL, of course. And then you have the crystal reference from the outside, which is a 50 megahertz, and I have the evaluation board right there. Let's take a close look at it. And here it is, the main Hittite HMC 700 part sits right there. That's the PLL core. We have our external VCO right there, which completes the loop in the feedback path right there. Here's a 50 megahertz crystal externally, which has a very good low phase noise, and that's used as a reference for the whole system. And this is the VCO output. This board right here is just used to configure this, and this runs from a single 5.5 volt power supply, and you can program it using SPI with this SPI to USB converter with a GUI that runs on the computer. Now the reason we want to use this and play around with it, I want to find out what configurations of the PLL chip is going to give us the best phase noise, so we can program the chip like that. This supports both fractional and as well as integer divisions in the PLL loop, so we can see what the impact of that is on the PLL performance itself. I'm interested mostly in the integrated jitter, which has the highest impact on the EVM of our constellation. So let's go ahead, plug it in, take a look at it. And here is our setup in action. I have the synthesizer directly connected to the instrument, and here I'm running the GUI software that allows me to configure the synthesizer IC. And you can see that I can load different configurations on there, and we can examine the impact of those settings on the phase noise of the PLL. And here is our tone, of course. You can see it is locked at 6 GHz, and you can see the second and the third harmonic of our output of our PLL, which is not that important for us. So I want to see the phase noise here. Well, we have a built-in phase noise personality. It's one of the applications available. So let's go under mode and let's advance until we find phase noise, and here it is. Here's our phase noise personality, and we click on that, and I've already configured it. The configuration is pretty straightforward by giving it a standard frequency. So what I'm doing here is I'm sweeping the phase noise, measuring it from 100 Hz offset all the way up to 100 MHz of offset, and you can see a very classic PLL shape of the phase noise. I have the marker set at 1 kHz, and you can see we're measuring about minus
mRNA Moderna. Bloomberg reporting Moderna target of SEC complaint filed by Oxfam over the vaccine. That's mRNA. Michael Romeo November Alpha.
That will just give us a nice measurement of the phase noise every decade offset from the carrier. And you can see that this is actually a very good PLL. We are reasonably close to the limit of the instrument itself. So part of the limitation here is now becoming the EXA. So if you're looking for really good phase noise measurement, the EXA may not necessarily be what you're looking for. Of course, remember that this is a very clean PLL, and having a
ARDS Maxim Cantor reiterating their overweight and $18 price target. That's Alpha Romeo Delta Sandy. Maxim reiterating their $13 price target and buy rating. That's Alpha Romeo Delta Sandy ARDS.
Phase noise. Now we can find out. So let's go ahead and do that calculation. I'm going to go under marker function, and I'm going to choose integrated RMS noise in degrees. Now I like to look at it in seconds, so I'm going to change the unit to seconds. There it is, and I need to adjust the band under which this calculation is being performed. So I'm going to set the left band all the way up to at 100 Hz, so all the way to the left, and the band on the right at 100 MHz, which is all the way to the right. And you can see that it's giving me an integrated jitter at 200
NWG
times per second for this entire band, which is respectable. That's not too bad. And so now we can go ahead and
NatWest pleads pleads unit guilty to manipulating treasury markets.
Equipped with that, and that's going to improve the noise floor here a little bit. And I can go under mode setup, and there is noise reduction right here. I'm going to go ahead and enable that. And if you pay attention,
Says NatWest Markets PLC pleaded guilty Tuesday to wire and securities fraud, admitting that its traders in London, Singapore, and Connecticut engaged in a number of schemes between 2008 and 2018 to manipulate U.S. Treasury markets.
And you're taking a look at these numbers. Let's go ahead and change the PLL mode to jump from fractional n to an integer type of approach. I'm going to go ahead and load that. And there it is. And you can see the PLL will reset, and check it out. You can see the behavior actually changed significantly. Our phase noise improved by about 3 dB at 1 kHz offset, and improved universally all the way to the PLL bandwidth here. And you can see that jitter peaking actually...
NVAX Novavax CEO says we'll have data on efficacy against Omicron in days. That's November Victor Alpha X-ray NVAX.
Which means that I would like to use the PLL under this condition. So this is a very quick overview, of course, of the phase noise personality. There is also phase noise cancellation, which I'm not using, which you can have a reference phase noise button and subtract and do all kind of fancy calculations. This is just an overview for you to see how quickly you can get some really important measurements about the shape of your the signal looks like at the end of our transmitter, and then finally build the whole system. And here we have our transmitter put all together. At the very beginning we have the IQ modulator up to 500 MHz, so it's running at 500 MHz right now, and it has the quantum constellation on top of it, going on to a low pass filter, and finally to the double sideband mixer. Now the LO of the mixer comes originally from the synthesizer that we just measured, and I've configured the synthesizer with settings that gave us the best integrated jitter based on the phase noise measurement. The output of that is amplified before it is applied to the double sideband mixer so that it would be within the LO requirements of the mixer. The output of that, which is our RF transmitter, has around 6.5 GHz. It's going to be amplified by this PA before it is finally sent to the network to the spectrum analyzer right now. And all these things are configured obviously with different computers around the lab, providing the settings and the modulation format and so on these different things. And the power supply for the PAs and the LO amplifier and the synthesizer are coming from different places. The power supply of the PA is provided by the Keithley power supply right there. You can see 12 volts consuming 53 milliamps. And all the way on the left over here, the power supply for the synthesizer and the LO amplifier.
KSS Coles,
and I've separated those two power
just off the highs now, 48.86, seeing the January $51 call on Kilo Sandy KSS.
Expected to be, and if it has still a reasonably good quality. And here's the spectrum of our transmitter. It looks like a horror show. Someone's got to call the FCC. There is tones everywhere. Obviously, this is a prototype. I didn't use any filters, and as I pointed out at the very beginning of the video, this is the consequence of that. And it's interesting to see that there are harmonics and signals generated all the way up to near 26.5 GHz. That's pretty amazing considering that the components, none of them are rated really more than 10 GHz or so. So nonetheless, this is our upper sideband and lower sideband signals centered right around 6.5 GHz, which is the tones that we are interested in. So we can actually zoom in a little bit and take a closer look and see if it is what we want. So let's go and set our center frequency to 6.5 GHz, which would be right around the frequency I'm interested in looking, and I'm going to change the span and reduce it significantly, and eventually we will see our spectrum. But you just saw how many other, I'm occupying everything under the sun, so obviously you cannot transmit this and it will never pass mask emission test and so on. But nonetheless, for our experiment, it's good enough, and you can see our main spectrum. So how much has the EVM degraded because of all these components and lack of filtering and using really just things that are off the shelf, not really optimized very well for each other? Well, we can easily find out by going under mode and going back to the VSA and running it again. Now this time the difference is that the VSA is no longer centered at 500 MHz, right now it's centered at 6.5 GHz. So indeed we are looking at the upper sideband of our transmitted signal exactly as it should be. And take a look, you can see our SNR has dropped quite a bit by more than 10 dB, and our EVM is 4 times larger. So it is, you can see that the quality of this constellation has degraded. And if you look closely, you can see at the edges and there's some smearing, and that is obviously the effect of the phase noise. So indeed, the integrated jitter that we have at 6.5 GHz is having some impact and some degradation on the EVM, as to be expected. Now, a few other things to note is that I'm transmitting just under 0 dBm of total power at around 6.5 GHz. Obviously, there is a whole bunch of other spectrum, as I said, and those also have power, but the power of interest is in this region. And a few other things to note is that the EVM, as a function of symbol, as we can see, it has a certain degree of periodicity to it. It's not completely white. There's a deterministic aspect to the EVM error, and this is very useful to see. I know where it comes from, but I'm going to leave it to you to discuss in the comment section if you can decipher why we have this deterministic way of the EVM degrading. And this is undesired, of course, because you don't want that. You want a perfectly white EVM so that your channel is basically a WGN. But nonetheless, you can see
TREB, Trebia Acquisition, saying a big block.
Build the receive section and see if the full chain can finally recover the signal. And finally, we have
coming in, Tango Romeo Echo Bravo, Trebia Acquisition.
Horn antennas. So I'm going to give you a close look at the receive side, since that's the part we haven't seen yet, and then we'll follow the whole setup from the beginning to the end with the camera, and then take a look at the performance. And here is our receive side. As we saw before, we have have the EXG synthesizer generating a half rate LO, which goes through our doubler, followed by an amplifier, and then fed into the LO port of the double sideband mixer on the down convert side. The signal comes from an antenna up here and then goes through the LNA, fed to the RF port, and the first IF coming out is then fed to this final IQ demodulator. You haven't seen this board before, so I'm going to talk about it a little bit afterwards. But this demodulator has its own built-in PLL. As a result, it's going to need an external reference, and I'm using a 100 MHz current-controlled crystal oscillator as a reference of that PLL. So this whole thing is going to do all of our final IQ demodulation. And all the different power supplies are scattered throughout the lab. We have two power supplies here to power the final demodulator, this power supply powering the PA for the LO driver, and finally a laptop over there which runs the GUI that controls the final IQ demodulator. So let's take a look at a block diagram of this so that we can have all the information and fully appreciate what's going on in this setup. And here is the block diagram of the final demodulator. You can see that indeed it has a VCO core in the middle here and all the required components for a PLL. So there is a PLL enclosed in this section. It also has an LO output and input, which we're ignoring at the moment, but you can see that the output of the VCO drives the divider and a quadrature divider, which generates two IQ signals, feeding the two mixers with the RF input coming over here with the I and the Q outputs. So this is basically the reverse of what this signal hound component does, and this would undo the IQ modulated signal initially originated from the VSG25A. So now that you have a good idea of what this looks like, we can follow the setup from the beginning and the end, and it should all come together. And once again, from the beginning, here's the power supply for our transmitter, and we can follow that, and we can see indeed the transmitter section here as I described before. The output of the PA goes through this horn antenna, and this horn antenna then transmits all the way to this receive horn antenna. The signal from that is fed to the LNA and the receive chain that I just showed you, and here is again the reference for the PLL inside the receiver. We have various power supplies scattered all around the lab powering different sections, and here's the laptop that controls the software for this receiver. Then the final signal from that is taken over here and passed through a low pass filter before it is given directly to our EXG. And you can already see, in fact, the signal, half of the baseband signal being received over here, and that's because the final receiver is a 0 IF receiver, and that's exactly what we would expect. And you can here, of course, also see the EXG generating our half rate LO, and everything looks really good. So the only thing we need to go back is to go ahead and take a look over here and see if that signal indeed matches what it is that we're transmitting from the IQ modulator from the very beginning of the chain. And here's our final spectrum, and you can see indeed that we have half the IQ signal, so the upper sideband being displayed here. Now remember what is actually happening. On our transmitter we have our first upconverter at 500 MHz, then I'm using a 6 GHz LO that puts our signal at 6.5 GHz, then I'm using a 5.6 GHz down converter on the sliding IF, and that puts our second IF down converter to 900 MHz. Now in order for us to be able to see the I and Q separately, I can't just set the receiver PLL to 900 MHz, which is what I've done over here. That's why you only see half the signal. Now, on a different X-series spectrum analyzer, if you have the option with the IQ analysis built on directly onto the front panel, you can actually take I and Q and put them directly onto the spectrum analyzer and have the baseband section process that information for you. But because we don't have that option, that's actually not available on the EXA series, we can only look at either I or Q, and this is in fact the I that I'm looking at. But what if I want to actually demodulate this and take a look at it? Well, I can always change the PLL that's built into the final down converter. Let's shift that PLL by 50 MHz from 900 MHz to 950, and I can go ahead and enter that number over here and run the code, and we should see the baseband signal shift, and there it is. In fact, now we again have our full I section, which is over here, and the Q section be within the analysis window of the spectrum analyzer. So now we can go back under mode and bring the VSA back up, and in fact, let me just make sure, there we go, we can actually bring the VSA back up, and now I can adjust the center frequency and say that
EXPE and buy from Investors Business Daily, Echo X-Ray Papa Echo, EXPE.
And it actually works. We have a complete
Shares getting some volume here now, off the highs 177.
And we have our received constellation. Obviously the constellation isn't going to look as nice as it did on the transmitter, and that's to be expected. And in fact we're receiving a very, very small amount of power. And I can change our marker here and center our marker at 50 megahertz. And we can see that the total received power from the IF is minus 28 dBm. So it's a very small IF signal, and that's because we don't have a baseband amplifier in this system, and it is normally required in a wireless system like this. But we have an EVM about 5.5%, our SNR is 25 dB, which is, it's okay. I mean, we can still recover with forward error correction this constellation. But it looks good, and if I go ahead and block the beam with my hand, you can see that I'm just right now passing my hand in front of the horn antenna, and you can clearly see the attenuation, and if the noise gets high enough, you can see the SNR of the signal will degrade as to be expected. Now 6.5 GHz still partially passes through my hand, so I can't completely block it, but I can certainly block some of it. So now you have a complete system, and you can appreciate every step of the way what kind of characteristic of each component is contributing to this final constellation, which is ultimately what we're looking for. And there you have it, a whole bunch of different experiments for the EXA signal analyzer. And I know I mentioned that I will take a look at the wideband IF output, but in the interest of time I'm going to leave that for a different video. But the idea is that the wideband IF output can actually have bandwidths over 400 megahertz instantaneous bandwidth, depending on if the right options are installed. And you can take that and connect it to something like the S-series oscilloscope, which I've reviewed before, and then you can do your digital analysis directly on that, and you're not limited by the 40 megahertz internal analysis bandwidth.
RIVN, Rivian, more call activity now. The weekly $97 calls on Romeo India Victor November, RIVN.
And I suggest that you go and take a look at if one of the particular application interests you, go and look at the data sheet so if you can get some more information about it. And as always, if you like the video, please leave me a comment or rate the video and let me know. And if you happen to purchase these instruments or if you get useful information from them, let other companies such as Keysight know. I don't get any money from them, I don't get any portion of the sale of these instruments, but it would allow me to have a good relationship with them to be able to bring you videos like this in the future of advanced instruments. So, until next time.
S&P futures near the highs now, 4609, up more than 50. JAGX, Jaguar, FDA approval. Canalevia for dogs, that's from Jaguar Animal Health, getting FDA approval. JAGX, Juliet Alpha Golf X-Ray. JAGX getting a pop here, $1.32. CURI, Curiosity debuts Smart Bundle Enhanced Premium Tier. That's Charlie Uniform Romeo India. CURI. RIO Rio Tinto to acquire Rincon Mining Lithium Project. That's Romeo India Oscar. $825 million. That's RIO. Israel reporting the first death linked to Omicron variant, that from I-24. Now report that the governor of Minnesota, Tim Walz, has tested positive. NKLA Nikola Motor says the first Nikola tree delivery was made last Friday to our customer, making these zero-emission trucks the cleanest in the entire drayage fleet. That's NKLA Nikola. Portugal government says people must work from home beginning next Monday. JAGX Jaguar Health, the January 250 call sweep now in JAGX, following that FDA approval being circulated. Juliet Alpha Golf X-ray. Shares of Jaguar Health popping to the highs at $1.74 off of that earlier news. JAGX. Josh Brown on CNBC mentioning he purchased more Amazon shares. Letter M, Macy's, more call activity today. The March $24 call sweep on letter M. Infectious disease specialist Fauci says on MSNBC, Biden to leverage Defense Production Act to spur 200 million to 500 million COVID tests to market. Stephen Weiss buys more Bank of America. That's Bravo Alpha Charlie BAC. Bank of America shares off the highs now, 44.37. AMD Advanced Micro Devices getting a pop here to the highs, 139.88 Alpha Michael Delta. AMD. CBIO granted U.S. patent for factor 7 polypeptides that are modified and uses thereof. Charlie Bravo, India Oscar, CBIO. S&P futures hitting 46.22 at the high. AMD, Alpha Michael Delta, is seeing some call activity now. Weekly 140 calls on AMD. Advanced Micro Devices, AMD. Stephen Weiss buying On Semiconductor, ON. Oscar November, ON on Semiconductor. Shares near the highs were 63.85. That's ON. RADA, none under $10 buy from Zax, Romeo Alpha Delta Alpha. RADA Electronics, getting a pop to the high, $9.34. Shares up about 7%. Romeo Alpha Delta Alpha RADA. New York City Mayor-elect Eric Adams has postponed his mayoral inauguration due to COVID-19 surge in New York City. Says it's been postponed to a later date due to the rise in coronavirus cases. CCL Carnival seeing activity in the March 22.5 call sweep. MTTR Matterport share is getting a spike on volume, getting mentioned from Josh Brown, says he owns Matterport. That's Michael Tango Tango Romeo, MTTR. Seeing now the January $25 call sweep on MTTR. That's Michael Tango Tango Romeo, MTTR. DKS Dick's Sporting Goods ticking a bit higher now in some volume. Stephen Weiss owns Dick's Sporting Goods, says he would buy more. Delta Kilo Sandy DKS. AAPL, Apple, Moody's upgrading Apple to a AAA outlook stable. That's Alpha Alpha Papa Lima, AAPL, Apple. Final trades on CNBC, CVS, letter T, JBL, and AMZN. BEAT hot beam shares popping to the highs, $4.20 on volume. Bravo Echo Alpha Michael, Bravo Echo Alpha Tango, BEAT. SHPW Shapeways granted European patent. Systems and methods for identifying three-dimensional objects. Shapeways popping to the highs, $3.78, SHPW. Airbnb, April $240 call sweep on Alpha Bravo, November Bravo, Airbnb. DGLY, Digital Ally, getting a spike in volume here. Delta Golf Lima Yankee, DGLY. AP reporting the U.S. Homeland Security agents to test use of body cameras. Shares of Digital Ally popping on that headline and pulling back now. Delta Golf Lima Yankee. HIVE Hive blockchain, the January $3 call is active now. Shares just off the highs at $2.81. Hotel India, Victor Echo. JAGX, Jaguar Health, now out with a press release from that earlier FDA approval announcement. FDA conditional approval of Canalevia CA1 Personally, treatment for chemotherapy-induced diarrhea in dogs to receive any type of approval from the FDA. That's Juliet Alpha Golf X-Ray, JAGX, out with a press release now. Shares at a high of $1.89 earlier. Now $1.65, up about 42% for JAGX. AERC, AeroClean Technologies, moving again now on volume, Alpha Echo Romeo Charlie, $13.10 popping here now on volume, AERC. RBLX, Roblox moving to the highs here, 102.67, 4%, Romeo Bravo Lima X-Ray, RBLX. STRN, Strand & Company, shares dropping to the lows, $4.92, and getting a bounce here on volume. That's Sandy Tango Romeo November. STRN. AAPL, Apple Insider reporting their marketing vice president, Nick Law, reportedly leaving the company. Alpha Alpha Papa Lima, AAPL. Biden team weighing short of COVID isolation for the vaccinated. Vaccinated healthcare workers could return to work sooner. Issue under discussion, but no decision has been made. WPRT, Westport. Shares getting a pop here. Westport Fuel Systems. Positive comments on CNBC from, reported from Oppenheimer on WPRT. Shares popping to the high, $2.43. WFC, Wells Fargo, delaying return to office plans given the changing external environment. That in a statement. That's Whiskey Foxtrot Charlie, WFC. Coming up after the close, earnings from BB BlackBerry, AIR, AAR, CAMP CalAmp. Coming up at 4:30 p.m., the API Weekly Crude and Gasoline Stocks. Reporter Amichai Stein, tweeting majority in immunization committee in Israel votes for provision of a fourth vaccine dose to at-risk groups, vaccine suppressed adults over age 60 and healthcare workers that in Israel. ISPC, iSpecimen shares off the highs now, 15.20, hit a high of $16, heavy volume now. That's India Sandy Papa Charlie, ISPC.
I noticed the lights were on and I thought you might be home. I wasn't sure.
LMT, RTX, Lockheed Martin, Raytheon. Reuters reporting U.S. State Department approves potential sale of Javelin missiles to Lithuania. That's Lima Michael Tango and Romeo Tango X-ray, LMT and RTX. QDEL, Keydell CEO Douglas Bryant on Biden administration efforts to increase COVID testing tells Benzinga, we are anticipating continued strong demand approaching the holidays based on the recent rise in infection rates. Keydell CEO tells Benzinga company is working to increase manufacturing capacity to the run rate of 70 million tests per month by the end of 2021. Keydell CEO says part of increase is dedicated to fulfilling a 12-month federal government contract estimated at about 100 million quick view at-home over-the-counter COVID-19 tests. That's Quebec Delta Echo Lima, QDEL. NXST, Nexstar Media, launching Next Gen TV at WHTM TV in Harrisburg, Pennsylvania. That's November X-Ray Sandy Tango. NXST. KRMD, Cornmill Medical Systems, received FDA 510K clearance for use of Freedom 60 with 2 additional SCIG drugs. That's Kilo Romeo Michael Delta, KRMD, LGND, Ligand, and GSK. Expand global collaboration and license agreement. That's Lima Golf November Delta, Golf Sandy Kilo, LGND, and GSK. BRTX, Biorestorative Therapies, announcing CRO agreement with PRC Clinical for its BRTX 100 Phase 2 clinical trial to treat chronic lumbar disc disease. That's Bravo Romeo Tango X-ray, BRTX. BRTX, Biorestorative Therapies, getting a pop here, $7 at the highs. Bravo Romeo Tango X-ray on that agreement for its BRTX 100 Phase 2 clinical trial to treat chronic lumbar disc disease. That's Bravo Romeo Tango X-ray, BRTX. GRTX, Galera Therapeutics, moving here as well. Golf Romeo Tango X-ray, GRTX. UTSI granted U.S. patent methods and apparatus for routing packet and segment routing network based on IPv6. That's Uniform Tango Sandy, India. PIK, KidPick reporting loss of 22 cents, revenue of 5.574 million. That's Papa India Kilo, PIK. CAMP, CalAmp reporting a loss of 8 cents. The estimate was 8 cents in earnings. Sales of 69 million, revenue of 69 million is below the 79 million estimate for Charlie Alpha Michael Papa, CAMP. KidPick reporting a loss of 29 cents on revenue 5.574 million. That's Papa India Kilo, PIK. AAR announcing $150 million stock buyback program. That's Alpha India Romeo, AIR. Nevro announcing settlement of litigation with NA2 Medical. That's November Victor Romeo Oscar. BK Technologies announcing record bookings. That's Bravo Kilo Tango India. BKTI. EIGR, Iger Biopharmaceuticals, announced first patient enrolled in Limit 2 Phase 3 study of PEG interferon lambda in patients with chronic hepatitis delta virus infection. That's Echo India Golf Romeo, EIGR. ACST, Alpha Charlie Sandy Tango, initiated at Oppenheimer with an outperform rating and $6 price target. Casti share spiking to $1.48. That's up 37 cents after hours. That's Alpha Charlie Sandy Tango. ACST. ACST, Casti continuing higher, $1.51 for Alpha Charlie Sandy Tango, ACST. AIR, Alpha India Romeo, reporting 53 cents. Alpha India Romeo, AIR, or it's a AAR company, AIR the symbol, 54 cents. That's a penny short. Sales of $437 million is also short on Alpha India Romeo, AIR, that's AAR Corporation. Alpha India Romeo, AIR. SRE, Sempra announcing agreement to sell 10% interest in Sempra Infrastructure Partners. That's Sandy Romeo Echo, Sandy Romeo Echo Tango, SRET, SRE. $1.785 billion in cash on that deal for SRET. SRE, Sempra out with guidance. Backs full year earnings of $8.10 to $8.70. That's versus the $8.23 estimate for Sandy Romeo Echo SRE. CTO Realty Growth announced the acquisition of a mixed-use property in Santa Fe, New Mexico, and sale of a single-tenant property in Falls Church, Virginia. That's Charlie Tango Oscar CTO. NFE signs MOU with Mauritania for fast LNG and gas power project. That's November Foxtrot Echo, NFE. BBBY, Bed Bath & Beyond, to announce their fiscal 2021 Q3 earnings results on January 6th. That's Bravo, Bravo, Bravo Yankee. BBBY. CAC, Camden National Corporation, announcing an 11% increase in its Q4 dividend to 40 cents per share. That's up from 36 cents for Charlie Alpha Charlie CAC. WEX naming Carlos Carrido as its COO for international operations. That's WEX, Whiskey Echo X-Ray. WEX. KKR announcing record intra-quarter monetization activity update for Q4. That's Kilo Romeo. Says the period from October 1st to December 21st, 2021, the company earned realized performance income, including realized incentive fees and total realized investment income, in excess for $1.15 billion, a record quarterly figure for KKR as a public company. That's Kilo Romeo, KKR. President Biden tweeting, starting this week, the federal government will set up emergency testing sites in areas that need additional testing capacity. Before Christmas, the first several of these federal testing sites will be up and running in New York City, with many more to come. That from President Biden. KPRX, Kiora Pharmaceutical spiking here, Kilo Papa Romeo X-ray, KPRX. Coming up at 4:30, the API data. Crude ticking slightly lower following the release of the API data. Waiting for those numbers now. DIS Disney. Disney extends Chief Financial Officer Christine McCarthy's contract through June 2024. Delta India Sandy DIS. MSG Entertainment names David Burns Executive Vice President and CFO. That's Michael Sandy Golf Echo. MSGE, ALNY, Analam publishes third annual Patient Access Philosophy Report demonstrating steady access to approved therapies as company enters new geographies. That's Alpha Lima November Yankee, ALNY. API data, crude, a draw of 3.67 million. Gasoline, a build of 3.701 million. Distillate, a draw of 849,000. GILD and RCOS, Gilead and Arcus Biosciences complete closing of option exercise for 3 clinical stage programs and new research collaboration. That's Golf India Lima Delta and Romeo Charlie Uniform Sandy. MRAI, MarPi hit a high of $4.77, 13D filing from Eli David, reporting a 4.5% stake, and another 13D from Yaron Itan, a 4.2% stake. That's Michael Romeo Alpha India, MRAI. ABT, Abbott Laboratories. Abbott Laboratories spokesperson on Biden administration efforts to increase COVID testing tells Benzinga in January we'll be making 70 million Binax Now rapid tests and can scale significantly further in the months ahead. That's Alpha Bravo Tango ABT company commenting to Benzinga on their COVID testing production. ABT. KNBE getting a pop here after hours, 23.75, up 75 cents. Kilo November Bravo Echo. NVAX, the World Health Organization, SAGE, issues interim recommendations for Novavax COVID-19 vaccine. SAGE recommends additional third dose of NVX-CoV-2373 administered to immunocompromised persons. Recommendation follows grant of the WHO emergency use listing for Novavax vaccine. That's NVAX, November Victor Alpha X-ray, NVAX. BRTX, biorestorative therapies, getting a pop here to the high now. $7.20 after the company announcing CRO agreement with PRC clinical trial for BRTX 100 for treatment of chronic lumbar disc disease. That's BRTX. $7.39 at the high for BRTX. THO, Thor Industries, announcing $250 million share buyback authorization. That's Tango Hotel Oscar, THO. ATKR, Atcor announcing acquisition of 4-Star Industries, Alpha Tango Kilo Romeo ATKR. AGCO, Atco agrees to acquire Aperio Systems, that's Alpha Golf Charlie Oscar, AGCO. RKLY, Rockley Photonics provides business update following U.S. Bureau of Industry and Security action relating to its joint venture partner, that's Romeo Kilo Lima Yankee. RKLY. NVAX, Novavax announcing initiation of Prevent-19 COVID-19 vaccine phase 3 trial booster study. That's November Victor Alpha X-ray, NVAX.
Thank you.